to knowledge-based intelligent systems, in which we consider what it means to be intelligent and whether machines could be such a thing. 1.1 Intelligent machines, or what machines can do. Philosophers have been trying for over 2,000 years to understand and resolve two big questions of the universe: how does a human mind work, and can non-humans have minds? However, these questions are still unanswered. Some philosophers have picked up the computational approach originated by computer scientists and accepted the idea that machines can do everything that humans can do. Others have openly opposed this idea, claiming that such highly sophisticated behavior as love, creative discovery and moral choice will always be beyond the scope of any machine. The nature of philosophy allows for disagreements to remain unresolved. In fact, engineers and scientists have already built machines that we can call intelligent. So what does the word intelligence mean? Let us look at a dictionary definition. 1. Someone's intelligence is their ability to understand and learn things. 2. Intelligence is the ability to think and understand instead of doing things by instinct or automatically. Essential English Dictionary, Collins, London, 1990. Thus, according to the first definition, intelligence is the quality possessed by humans. But the second definition suggests a completely different approach and gives some flexibility. It does not specify whether it is someone or something that has the ability to think and understand. Now we should discover what thinking means. Let us consult our dictionary again. Thinking is the activity of using your brain to consider a problem or to create an idea. Essential English Dictionary, Collins, London, 1990. 2. Introduction to Knowledge-Based Intelligent Systems. So, in order to think, someone or something has to have a brain, or in other words, an organ that enables someone or something to learn and understand things, to solve problems and to make decisions. So we can define intelligence as the ability to learn and understand, to solve problems and to make decisions. The very question that asks whether computers can be intelligent, or whether machines can think, came to us from the dark ages of artificial intelligence from the late 1940s. The goal of artificial intelligence (AI) as a science is to make machines do things that would require intelligence if done by humans. Bowden, 1977. Therefore, the answer to the question, can machines think, was vitally important to the discipline. However, the answer is not a simple yes or no, but rather a vague or fuzzy one. Your everyday experience and common sense would have told you that some people are smarter in some ways than others. Sometimes we make very intelligent decisions, but sometimes we also make very silly mistakes. Some of us deal with complex mathematical and engineering problems but are moronic in philosophy and history. Some people are good at making money, while others are better at spending it. As humans, we all have the ability to learn and understand, to solve problems and to make decisions. However, our abilities are not equal and lie in different areas. Therefore, we should expect that if machines can think, some of them might be smarter than others in some ways. One of the earliest and most significant papers on machine intelligence, Computing Machinery and Intelligence, was written by the British mathematician Alan Turing over 50 years ago. Turing, 1950. However, it has stood up well to the test of time, and Turing's approach remains universal. Alan Turing began his scientific career in the early 1930s by rediscovering the central limit theorem. In 1937 he wrote a paper on computable numbers, in which he proposed the concept of a universal machine. Later, during the Second World War, he was a key player in deciphering Enigma, the German military encoding machine. After the war, Turing designed the automatic computing engine. He also wrote the first program capable of playing a complete chess game. It was later implemented on the Manchester University computer. Turing's theoretical concept of the universal computer and his practical experience in building code-breaking systems equipped him to approach the key fundamental question of artificial intelligence. He asked, is there thought without experience? Is there mind without communication? Is there language without living? Is there intelligence without life? All these questions, as you can see, are just variations on the fundamental question of artificial intelligence: can machines think? Turing did not provide definitions of machines and thinking, he just avoided semantic arguments by inventing a game, the Turing imitation game. Instead of asking, can machines think? Turing said we should ask, can machines pass a behavior test for intelligence? He predicted that by the year 2000, a computer could be programmed to have a conversation with a human interrogator for 5 minutes and would have a 30% chance of deceiving the interrogator that it was a human. Turing defined the intelligent behavior of a computer as the ability to achieve the human-level performance in cognitive tasks. In other intelligent machines 3. Figure 1.1 Turing imitation game, Phase 1. Words. A computer passes the test if interrogators cannot distinguish the machine from a human on the basis of the answers to their questions. The imitation game proposed by Turing originally included 2 phases. In the first phase, shown in Figure 1.1, the interrogator, a man and a woman, are each placed in separate rooms and can communicate only via a neutral medium such as a remote terminal. The interrogator's objective is to work out who is the man and who is the woman by questioning them. The rules of the game are that the man should attempt to deceive the interrogator that he is the woman, while the woman has to convince the interrogator that she is the woman. In the second phase of the game, shown in Figure 1.2, the man is replaced by a computer program to deceive the interrogator as the man did. It would even be programmed to make mistakes and provide fuzzy answers in the way a human would. If the computer can fool the interrogator as often as the man did, we may say this computer has passed the intelligent behavior test. Physical simulation of a human is not important for intelligence. Hence, in the Turing test the interrogator does not see, touch or hear the computer and is therefore not influenced by its appearance or voice. However, the interrogator is allowed to ask any questions, even provocative ones, in order to identify the machine. The interrogator may, for example, ask both the human and the Figure 1.2 Turing imitation game, Phase 2. 4. Introduction to knowledge-based intelligent systems. Machine to perform complex mathematical calculations, expecting that the computer will provide a correct solution and will do it faster than the human. Thus, the computer will need to know when to make a mistake and when to delay its answer. The interrogator also may attempt to discover the emotional nature of the human, and thus, he might ask both subjects to examine a short novel or poem or even painting. Obviously, the computer will be required here to simulate a human's emotional understanding of the work. The Turing test has 2 remarkable qualities that make it really universal. By maintaining communication between the human and the machine via terminals, the test gives us an objective standard view on intelligence. It avoids debates over the human nature of intelligence and eliminates any bias in favor of humans. The test itself is quite independent from the details of the experiment. It can be conducted either as a 2-phase game as just described, or even as a single-phase game in which the interrogator needs to choose between the human and the machine from the beginning of the test. The interrogator is also free to ask any question in any field and can concentrate solely on the content of the answers provided. Turing believed that by the end of the 20th century it would be possible to program a digital computer to play the imitation game. Although modern computers still cannot pass the Turing test, it provides a basis for the verification and validation of knowledge-based systems. A program thought intelligent in some narrow area of expertise is evaluated by comparing its performance with the performance of a human expert. Our brain stores the equivalent of over 1018 bits and can process information at the equivalent of about 1015 bits per second. By 2020, the brain will probably be modeled by a chip the size of a sugar cube, and perhaps by then there will be a computer that can play even win the Turing imitation game. However, do we really want the machine to perform mathematical calculations as slowly and inaccurately as humans do? From a practical point of view, an intelligent machine should help humans to make decisions, to search for information, to control complex objects, and finally to understand the meaning of words. There is probably no point in trying to achieve the abstract and elusive goal of developing machines with human-like intelligence. To build an intelligent computer system, we have to capture, organize and use human expert knowledge in some narrow area of expertise. 1.2 The history of artificial intelligence, or from the Dark Ages to knowledge-based systems. Artificial intelligence as a science was founded by 3 generations of researchers. Some of the most important events and contributors from each generation are described next. The history of artificial intelligence. 5. 1.2.1 The Dark Ages, or the birth of artificial intelligence 1943-56. The first work recognized in the field of artificial intelligence (AI) was presented by Warren McCulloch and Walter Pitts in 1943. McCulloch had degrees in philosophy and medicine from Columbia University and became the director of the Basic Research Laboratory in the Department of Psychiatry at the University of Illinois. His research on the central nervous system resulted in the first major contribution to AI, a model of neurons of the brain. McCulloch and his co-author Walter Pitts, a young mathematician, proposed a model of artificial neural networks in which each neuron was postulated as being in binary state, that is, in either on or off condition. McCulloch and Pitts, 1943. They demonstrated that their neural network model was, in fact, equivalent to the Turing machine, and proved that any computable function could be computed by some network of connected neurons. McCulloch and Pitts also showed that simple network structures could learn. The neural network model stimulated both theoretical and experimental work to model the brain in the laboratory. However, experiments clearly demonstrated that the binary model of neurons was not correct. In fact, a neuron has highly nonlinear characteristics and cannot be considered as a simple two-state device. Nonetheless, McCulloch, the second, founding father, of AI after Alan Turing, had created the cornerstone of neural computing and artificial neural networks (ANN). After a decline in the 1970s, the field of ANN was revived in the late 1980s. The third founder of AI was John von Neumann, the brilliant Hungarian-born mathematician. In 1930, he joined the Princeton University, lecturing in mathematical physics. He was a colleague and friend of Alan Turing. During the Second World War, von Neumann played a key role in the Manhattan Project that built the nuclear bomb. He also became an advisor for the Electronic Numerical Integrator and Calculator ENIAC project at the University of Pennsylvania and helped to design the Electronic Discrete Variable Automatic Computer (EDVAC), a stored program machine. He was influenced by McCulloch and Pitts's neural network model. When Marvin Minsky and Dean Edmonds, two graduate students in the Princeton Mathematics Department, built the first neural network computer in 1951, von Neumann encouraged and supported them. Another of the first-generation researchers was Claude Shannon. He graduated from Massachusetts Institute of Technology (MIT) and joined Bell Telephone Laboratories in 1941. Shannon shared Alan Turing's ideas on the possibility of machine intelligence. In 1950, he published a paper on chess-playing machines, which pointed out that a typical chess game involved about 10,120 possible moves. Shannon, 1950. Even if the new von Neumann-type computer could examine one move per microsecond, it would take 310,106 years to make its first move. Thus Shannon demonstrated the need to use heuristics in the search for the solution. Princeton University was also home to John McCarthy, another founder of AI. He convinced Martin Minsky and Claude Shannon to organize a summer 6. Introduction to Knowledge-Based Intelligent Systems workshop at Dartmouth College, where McCarthy worked after graduating from Princeton. In 1956, they brought together researchers interested in the study of machine intelligence, artificial neural nets and automata theory. The workshop was sponsored by IBM. Although there were just 10 researchers, this workshop gave birth to a new science called artificial intelligence. For the next 20 years the field of AI would be dominated by the participants at the Dartmouth workshop and their students. 1.2.2 The Rise of Artificial Intelligence, or the Era of Great Expectations 1956–late 1960s. The early years of AI are characterized by tremendous enthusiasm, great ideas and very limited success. Only a few years before, computers had been introduced to perform routine mathematical calculations, but now AI researchers were demonstrating that computers could do more than that. It was an era of great expectations. John McCarthy, one of the organizers of the Dartmouth workshop and the inventor of the term, artificial intelligence, moved from Dartmouth to MIT. He defined the high-level language Lisp, one of the oldest programming languages. Fortran is just 2 years older, which is still in current use. In 1958, McCarthy presented a paper, Programs with Common Sense, in which he proposed a program called the Advice Taker to search for solutions to general problems of the world. McCarthy, 1958. McCarthy demonstrated how his program could generate, for example, a plan to drive to the airport, based on some simple axioms. Most importantly, the program was designed to accept new axioms, or in other words new knowledge, in different areas of expertise without being reprogrammed. Thus the Advice Taker was the first complete knowledge-based system incorporating the central principles of knowledge representation and reasoning. Another organizer of the Dartmouth workshop, Marvin Minsky, also moved to MIT. However, unlike McCarthy with his focus on formal logic, Minsky developed an anti-logical outlook on knowledge representation and reasoning. His theory of frames Minsky, 1975, was a major contribution to knowledge engineering. The early work on neural computing and artificial neural networks started by McCulloch and Pitts was continued. Learning methods were improved and Frank Rosenblatt proved the perceptron convergence theorem, demonstrating that his learning algorithm could adjust the connection strengths of a perceptron. Rosenblatt, 1962. One of the most ambitious projects of the era of great expectations was the General Problem Solver (GPS). Newell and Simon, 1961, 1972. Alan Newell and Herbert Simon from the Carnegie Mellon University developed a general-purpose program to simulate human problem-solving methods. GPS was probably the first attempt to separate the problem-solving technique from the data. It was based on the technique now referred to as means-ends analysis. The history of artificial intelligence. 7. Newell and Simon postulated that a problem to be solved could be defined in terms of states. The means-ends analysis was used to determine a difference between the current state and the desirable state or the goal state of the problem, and to choose and apply operators to reach the goal state. If the goal state could not be immediately reached from the current state, a new state closer to the goal would be established and the procedure repeated until the goal state was reached. The set of operators determined the solution plan. However, GPS failed to solve complicated problems. The program was based on formal logic and therefore could generate an infinite number of possible operators, which is inherently inefficient. The amount of computer time and memory that GPS required to solve real-world problems led to the project being abandoned. In summary, we can say that in the 1960s, AI researchers attempted to simulate the complex thinking process by inventing general methods for solving broad classes of problems. They used the general-purpose search mechanism to find a solution to the problem. Such approaches, now referred to as weak methods, applied weak information about the problem domain. This resulted in weak performance of the programs developed. However, it was also a time when the field of AI attracted great scientists who introduced fundamental new ideas in such areas as knowledge representation, learning algorithms, neural computing and computing with words. These ideas could not be implemented then because of the limited capabilities of computers, but 2 decades later they have led to the development of real-life practical applications. It is interesting to note that Lotfi Zadeh, a professor from the University of California at Berkeley, published his famous paper, Fuzzy Sets, also in the 1960s. Zadeh, 1965. This paper is now considered the foundation of the fuzzy set theory. 2 decades later, fuzzy researchers have built hundreds of smart machines and intelligent systems. By 1970, the euphoria about AI was gone, and most government funding for AI projects was cancelled. AI was still a relatively new field, academic in nature, with few practical applications apart from playing games. Samuel, 1959, 1967, Greenblatt et al., 1967. So, to the outsider, the achievements would be seen as toys, as no AI system at that time could manage real-world problems. 1.2.3 Unfulfilled Promises, or the Impact of Reality. Late 1960s, early 1970s. From the mid-1950s, AI researchers were making promises to build all-purpose intelligent machines on a human-scale knowledge base by the 1980s, and to exceed human intelligence by the year 2000. By 1970, however, they realized that such claims were too optimistic. Although a few AI programs could demonstrate some level of machine intelligence in 1 or 2 toy problems, almost no AI projects could deal with a wider selection of tasks or more difficult real-world problems. 8. Introduction to Knowledge-Based Intelligent Systems. The main difficulties for AI in the late 1960s were Because AI researchers were developing general methods for broad classes of problems, early programs contained little or even no knowledge about a problem domain. To solve problems, programs applied a search strategy by trying out different combinations of small steps, until the right one was found. This method worked for toy problems, so it seemed reasonable that, if the programs could be scaled up to solve large problems, they would finally succeed. However, this approach was wrong. Easy, or tractable, problems can be solved in polynomial time, i.e. for a problem of size n, the time or number of steps needed to find the solution is a polynomial function of n. On the other hand, hard or intractable problems require times that are exponential functions of the problem size. While a polynomial time algorithm is considered to be efficient, an exponential time algorithm is inefficient, because its execution time increases rapidly with the problem size. The theory of NP-completeness. Cook, 1971, Karp, 1972, developed in the early 1970s, showed the existence of a large class of nondeterministic polynomial problems, NP problems, that are NP-complete. A problem is called NP if its solution, if one exists, can be guessed and verified in polynomial time. Non-deterministic means that no particular algorithm is followed to make the guess. The hardest problems in this class are NP-complete. Even with faster computers and larger memories, these problems are hard to solve. Many of the problems that AI attempted to solve were too broad and too difficult. A typical task for early AI was machine translation. For example, the National Research Council, USA, funded the translation of Russian scientific papers after the launch of the first artificial satellite, Sputnik, in 1957. Initially, the project team tried simply replacing Russian words with English, using an electronic dictionary. However, it was soon found that translation requires a general understanding of the subject to choose the correct words. This task was too difficult. In 1966, all translation projects funded by the US government were cancelled. In 1971, the British government also suspended support for AI research. Sir James Lighthill had been commissioned by the Science Research Council of Great Britain to review the current state of AI. Lighthill, 1973. He did not find any major or even significant results from AI research, and therefore saw no need to have a separate science called artificial intelligence. 1.2.4 The technology of expert systems, or the key to success, early 1970s, mid-1980s. Probably the most important development in the 1970s was the realization that the problem domain for intelligent machines had to be sufficiently restricted. Previously, AI researchers had believed that clever search algorithms and reasoning techniques could be invented to emulate general, human-like, problem-solving methods. A general-purpose search mechanism could rely on the history of artificial intelligence. 9. Elementary reasoning steps to find complete solutions and could use weak knowledge about domain. However, when weak methods failed, researchers finally realized that the only way to deliver practical results was to solve typical cases in narrow areas of expertise by making large reasoning steps. The DENDRAL program is a typical example of the emerging technology. Buchanan et al., 1969. DENDRAL was developed at Stanford University to analyze chemicals. The project was supported by NASA, because an unmanned spacecraft was to be launched to Mars and a program was required to determine the molecular structure of Martian soil, based on the mass spectral data provided by a mass spectrometer. Edward Feigenbaum, a former student of Herbert Simon, Bruce Buchanan, a computer scientist, and Joshua Lederberg, a Nobel Prize winner in genetics, formed a team to solve this challenging problem. The traditional method of solving such problems relies on a generate and test technique. All possible molecular structures consistent with the mass spectrogram are generated first, and then the mass spectrum is determined or predicted for each structure and tested against the actual spectrum. However, this method failed because millions of possible structures could be generated. The problem rapidly became intractable even for decent-sized molecules. To add to the difficulties of the challenge, there was no scientific algorithm for mapping the mass spectrum into its molecular structure. However, analytical chemists, such as Lederberg, could solve this problem by using their skills, experience and expertise. They could enormously reduce the number of possible structures by looking for well-known patterns of peaks in the spectrum, and thus provide just a few feasible solutions for further examination. Therefore, Feigenbaum's job became to incorporate the expertise of Lederberg into a computer program to make it perform at a human expert level. Such programs were later called expert systems. To understand and adopt Lederberg's knowledge and operate with his terminology, Feigenbaum had to learn basic ideas in chemistry and spectral analysis. However, it became apparent that Feigenbaum used not only rules of chemistry but also his own heuristics, or rules of thumb, based on his experience and even guesswork. Soon Feigenbaum identified one of the major difficulties in the project, which he called the knowledge acquisition bottleneck, how to extract knowledge from human experts to apply to computers. To articulate his knowledge, Lederberg even needed to study basics in computing. Working as a team, Feigenbaum, Buchanan and Lederberg developed DENDRAL, the first successful knowledge-based system. The key to their success was mapping all the relevant theoretical knowledge from its general form to highly specific rules. Cookbook recipes. Feigenbaum et al., 1971. The significance of DENDRAL can be summarized as follows. DENDRAL marked a major paradigm shift in AI, a shift from general-purpose, knowledge-sparse, weak methods to domain-specific, knowledge-intensive techniques. 10. Introduction to knowledge-based intelligent systems. The aim of the project was to develop a computer program to attain the level of performance of an experienced human chemist. Using heuristics in the form of high-quality specific rules of thumb elicited from human experts, the DENDRAL team proved that computers could equal an expert in narrow, defined, problem areas. The DENDRAL project originated the fundamental idea of the new methodology of expert systems knowledge engineering, which encompassed techniques of capturing, analyzing and expressing in rules and experts' know-how. DENDRAL proved a useful analytical tool for chemists and was marketed commercially in the United States. The next major project undertaken by Feigenbaum and others at Stanford University was in the area of medical diagnosis. The project, called MYCIN, started in 1972. It later became the PhD thesis of Edward Shortliff, 1976. MYCIN was a rule-based expert system for the diagnosis of infectious blood diseases. It also provided a doctor with therapeutic advice in a convenient, user-friendly manner. MYCIN had a number of characteristics common to early expert systems, including MYCIN could perform at a level equivalent to human experts in the field and considerably better than junior doctors. MYCIN's knowledge consisted of about 450 independent rules of if-then form derived from human knowledge in a narrow domain through extensive interviewing of experts. The knowledge incorporated in the form of rules was clearly separated from the reasoning mechanism. The system developer could easily manipulate knowledge in the system by inserting or deleting some rules. For example, a domain-independent version of MYCIN called EMYCIN, Empty MYCIN, was later produced at Stanford University, Van Mel, 1979, Van Mel et al., 1981. It had all the features of the MYCIN system except the knowledge of infectious blood diseases. EMYCIN facilitated the development of a variety of diagnostic applications. System developers just had to add new knowledge in the form of rules to obtain a new application. MYCIN also introduced a few new features. Rules incorporated in MYCIN reflected the uncertainty associated with knowledge, in this case with medical diagnosis. It tested rule conditions, the if part, against available data or data requested from the physician. When appropriate, MYCIN inferred the truth of a condition through a calculus of uncertainty called certainty factors. Reasoning in the face of uncertainty was the most important part of the system. Another probabilistic system that generated enormous publicity was Prospector, an expert system for mineral exploration developed by the Stanford Research Institute, Duda et al., 1979. The project ran from 1974 to The History of Artificial Intelligence. 11. 1983. 9 experts contributed their knowledge and expertise. To represent their knowledge, Prospector used a combined structure that incorporated rules in a semantic network. Prospector had over 1,000 rules to represent extensive domain knowledge. It also had a sophisticated support package including a knowledge acquisition system. Prospector operates as follows. The user, an exploration geologist, is asked to input the characteristics of a suspected deposit, the geological setting, structures, kinds of rocks and minerals. Then the program compares these characteristics with models of ore deposits and, if necessary, queries the user to obtain additional information. Finally, Prospector makes an assessment of the suspected mineral deposit and presents its conclusion. It can also explain the steps it used to reach the conclusion. In exploration geology, important decisions are usually made in the face of uncertainty, with knowledge that is incomplete or fuzzy. To deal with such knowledge, Prospector incorporated Bayes' rules of evidence to propagate uncertainties through the system. Prospector performed at the level of an expert geologist and proved itself in practice. In 1980, it identified a molybdenum deposit near Mount Tallman in Washington state. Subsequent drilling by a mining company confirmed the deposit was worth over $100 million. You couldn't hope for a better justification for using expert systems. The expert systems mentioned above have now become classics. A growing number of successful applications of expert systems in the late 1970s showed that AI technology could move successfully from the research laboratory to the commercial environment. During this period, however, most expert systems were developed with special AI languages, such as Lisp, Prolog and OPS, based on powerful workstations. The need to have rather expensive hardware and complicated programming languages meant that the challenge of expert system development was left in the hands of a few research groups at Stanford University, MIT, Stanford Research Institute and Carnegie Mellon University. Only in the 1980s, with the arrival of personal computers (PCs) and easy-to-use expert system development tools shells could ordinary researchers and engineers in all disciplines take up the opportunity to develop expert systems. A 1986 survey reported a remarkable number of successful expert system applications in different areas: chemistry, electronics, engineering, geology, management, medicine, process control and military science. Waterman, 1986. Although Waterman found nearly 200 expert systems, most of the applications were in the field of medical diagnosis. 7 years later, a similar survey reported over 2,500 developed expert systems. Durkin, 1994. The new growing area was business and manufacturing, which accounted for about 60% of the applications. Expert system technology had clearly matured. Are expert systems really the key to success in any field? In spite of a great number of successful developments and implementations of expert systems in different areas of human knowledge, it would be a mistake to overestimate the capability of this technology. The difficulties are rather complex and lie in both technical and sociological spheres. They include the following. 12. Introduction to knowledge-based intelligent systems. Expert systems are restricted to a very narrow domain of expertise. For example, Mycin, which was developed for the diagnosis of infectious blood diseases, lacks any real knowledge of human physiology. If a patient has more than one disease, we cannot rely on Mycin. In fact, therapy prescribed for the blood disease might even be harmful because of the other disease. Because of the narrow domain, expert systems are not as robust and flexible as a user might want. Furthermore, expert systems can have difficulty recognizing domain boundaries. When given a task different from the typical problems, an expert system might attempt to solve it and fail in rather unpredictable ways. Expert systems have limited explanation capabilities. They can show the sequence of the rules they applied to reach a solution, but cannot relate accumulated, heuristic knowledge to any deeper understanding of the problem domain. Expert systems are also difficult to verify and validate. No general technique has yet been developed for analyzing their completeness and consistency. Heuristic rules represent knowledge in abstract form and lack even basic understanding of the domain area. It makes the task of identifying incorrect, incomplete or inconsistent knowledge very difficult. Expert systems, especially the first generation, have little or no ability to learn from their experience. Expert systems are built individually and cannot be developed fast. It might take from 5 to 10 person-years to build an expert system to solve a moderately difficult problem. Waterman, 1986. Complex systems such as DENDRAL, Mycin or Prospector can take over 30 person-years to build. This large effort, however, would be difficult to justify if improvements to the expert system's performance depended on further attention from its developers. Despite all these difficulties, expert systems have made the breakthrough and proved their value in a number of important applications. 1.2.5 How to make a machine learn, or the rebirth of neural networks. Mid-1980s onwards. In the mid-1980s, researchers, engineers and experts found that building an expert system required much more than just buying a reasoning system or expert system shell and putting enough rules in it. Disillusion about the applicability of expert system technology even led to people predicting an AI winter, with severely squeezed funding for AI projects. AI researchers decided to have a new look at neural networks. By the late 1960s, most of the basic ideas and concepts necessary for neural computing had already been formulated. Cowan, 1990. However, only in the mid-1980s did the solution emerge. The major reason for the delay was technological. There were no PCs or powerful workstations to model in. The history of artificial intelligence. 13. Experiment with artificial neural networks. The other reasons were psychological and financial. For example, in 1969, Minsky and Papert had mathematically demonstrated the fundamental computational limitations of one-layer perceptrons. Minsky and Papert, 1969. They also said there was no reason to expect that more complex multilayer perceptrons would represent much. This certainly would not encourage anyone to work on perceptrons, and as a result, most AI researchers deserted the field of artificial neural networks in the 1970s. In the 1980s, because of the need for brain-like information processing, as well as the advances in computer technology and progress in neuroscience, the field of neural networks experienced a dramatic resurgence. Major contributions to both theory and design were made on several fronts. Grossberg established a new principle of self-organization, adaptive resonance theory, which provided the basis for a new class of neural networks. Grossberg, 1980. Hopfield introduced neural networks with feedback Hopfield networks, which attracted much attention in the 1980s. Hopfield, 1982. Kohonen published a paper on self-organized maps. Kohonen, 1982. Bardo, Sutton and Anderson published their work on reinforcement learning and its application in control. Bardo et al., 1983. But the real breakthrough came in 1986 when the backpropagation learning algorithm, first introduced by Bryson and Ho in 1969, Bryson and Ho, 1969, was reinvented by Rumelhart and McClelland in Parallel Distributed Processing, Explorations in the Microstructures of Cognition. Rumelhart and McClelland, 1986. At the same time, backpropagation learning was also discovered by Parker, 1987, and LeCun, 1988, and since then has become the most popular technique for training multilayer perceptrons. In 1988, Broomhead and Lowe found a procedure to design layered feedforward networks using radial basis functions, an alternative to multilayer perceptrons. Broomhead and Lowe, 1988. Artificial neural networks have come a long way from the early models of McCulloch and Pitts to an interdisciplinary subject with roots in neuroscience, psychology, mathematics and engineering, and will continue to develop in both theory and practical applications. However, Hopfield's paper, Hopfield, 1982, and Rumelhart and McClelland's book, Rumelhart and McClelland, 1986, were the most significant and influential works responsible for the rebirth of neural networks in the 1980s. 1.2.6 Evolutionary computation, or learning by doing, early 1970s onwards. Natural intelligence is a product of evolution. Therefore, by simulating biological evolution, we might expect to discover how living systems are propelled towards high-level intelligence. Nature learns by doing. Biological systems are not told how to adapt to a specific environment, they simply compete for survival. The fittest species have a greater chance to reproduce, and thereby to pass their genetic material to the next generation. 14. Introduction to knowledge-based intelligent systems. The evolutionary approach to artificial intelligence is based on the computational models of natural selection and genetics. Evolutionary computation works by simulating a population of individuals, evaluating their performance, generating a new population, and repeating this process a number of times. Evolutionary computation combines three main techniques: genetic algorithms, evolutionary strategies, and genetic programming. The concept of genetic algorithms was introduced by John Holland in the early 1970s. Holland, 1975. He developed an algorithm for manipulating artificial chromosomes, strings of binary digits, using such genetic operations as selection, crossover, and mutation. Genetic algorithms are based on a solid theoretical foundation of the schema theorem. Holland, 1975, Goldberg, 1989. In the early 1960s, independently of Holland's genetic algorithms, Ingo Rechenberg and Hans Paul Schwefel, students of the Technical University of Berlin, proposed a new optimization method called evolutionary strategies. Rechenberg, 1965. Evolutionary strategies were designed specifically for solving parameter optimization problems in engineering. Rechenberg and Schwefel suggested using random changes in the parameters, as happens in natural mutation. In fact, an evolutionary strategies approach can be considered as an alternative to the engineer's intuition. Evolutionary strategies use a numerical optimization procedure, similar to a focused Monte Carlo search. Both genetic algorithms and evolutionary strategies can solve a wide range of problems. They provide robust and reliable solutions for highly complex, nonlinear search and optimization problems that previously could not be solved at all. Holland, 1995, Schwefel, 1995. Genetic programming represents an application of the genetic model of learning to programming. Its goal is to evolve not a coded representation of some problem, but rather a computer code that solves the problem. That is, genetic programming generates computer programs as the solution. The interest in genetic programming was greatly stimulated by John Koza in the 1990s. Koza, 1992, 1994. He used genetic operations to manipulate symbolic code representing Lisp programs. Genetic programming offers a solution to the main challenge of computer science, making computers solve problems without being explicitly programmed. Genetic algorithms, evolutionary strategies and genetic programming represent rapidly growing areas of AI, and have great potential. 1.2.7 The new era of knowledge engineering, or computing with words, late 1980s onwards. Neural network technology offers more natural interaction with the real world than do systems based on symbolic reasoning. Neural networks can learn, adapt to changes in a problem's environment, establish patterns in situations where rules are not known, and deal with fuzzy or incomplete information. However, they lack explanation facilities and usually act as a black box. The process of training neural networks with current technologies is slow, and frequent retraining can cause serious difficulties. The history of artificial intelligence. 15. Although in some special cases, particularly in knowledge-poor situations, ANS can solve problems better than expert systems, the two technologies are not in competition now. They rather nicely complement each other. Classic expert systems are especially good for closed system applications with precise inputs and logical outputs. They use expert knowledge in the form of rules and, if required, can interact with the user to establish a particular fact. A major drawback is that human experts cannot always express their knowledge in terms of rules or explain the line of their reasoning. This can prevent the expert system from accumulating the necessary knowledge, and consequently lead to its failure. To overcome this limitation, neural computing can be used for extracting hidden knowledge in large data sets to obtain rules for expert systems. Metzger and Leibowitz, 1994, Zahidi, 1993. ANS can also be used for correcting rules in traditional rule-based expert systems. Omlin and Giles, 1996. In other words, where acquired knowledge is incomplete, neural networks can refine the knowledge, and where the knowledge is inconsistent with some given data, neural networks can revise the rules. Another very important technology dealing with vague, imprecise and uncertain knowledge and data is fuzzy logic. Most methods of handling imprecision in classic expert systems are based on the probability concept. Meisen, for example, introduced certainty factors, while Prospector incorporated Bayes' rules to propagate uncertainties. However, experts do not usually think in probability values, but in such terms as often, generally, sometimes, occasionally and rarely. Fuzzy logic is concerned with the use of fuzzy values that capture the meaning of words, human reasoning and decision-making. As a method to encode and apply human knowledge in a form that accurately reflects an expert's understanding of difficult, complex problems, fuzzy logic provides the way to break through the computational bottlenecks of traditional expert systems. At the heart of fuzzy logic lies the concept of a linguistic variable. The values of the linguistic variable are words rather than numbers. Similar to expert systems, fuzzy systems use if-then rules to incorporate human knowledge, but these rules are fuzzy, such as: if speed is high, then stopping _ distance is long. If speed is low, then stopping _ distance is short. Fuzzy logic or fuzzy set theory was introduced by Professor Lotfi Zadeh, Berkeley's Electrical Engineering Department chairman, in 1965. Zadeh, 1965. It provided a means of computing with words. However, acceptance of fuzzy set theory by the technical community was slow and difficult. Part of the problem was the provocative name, fuzzy, which seemed too lighthearted to be taken seriously. Eventually, fuzzy theory, ignored in the West, was taken seriously in the East by the Japanese. It has been used successfully since 1987 in Japanese-designed dishwashers, washing machines, air conditioners, television sets, copiers and even cars. 16. Introduction to knowledge-based intelligent systems. The introduction of fuzzy products gave rise to tremendous interest in this apparently new technology first proposed over 30 years ago. Hundreds of books and thousands of technical papers have been written on this topic. Some of the classics are Fuzzy Sets, Neural Networks and Soft Computing, Yager and Zadeh, eds. 1994, The Fuzzy Systems Handbook, Cox, 1999, Fuzzy Engineering, Cosco, 1997, Expert Systems and Fuzzy Systems, Negoida, 1985, and also the bestseller science book, Fuzzy Thinking, Cosco, 1993, which popularized the field of fuzzy logic. Most fuzzy logic applications have been in the area of control engineering. However, fuzzy control systems use only a small part of fuzzy logic's power of knowledge representation. Benefits derived from the application of fuzzy logic models in knowledge-based and decision support systems can be summarized as follows: Cox, 1999, Turbin and Aronson, 2000. Improved computational power. Fuzzy rule-based systems perform faster than conventional expert systems and require fewer rules. A fuzzy expert system merges the rules, making them more powerful. Lotfizadeh believes that in a few years most expert systems will use fuzzy logic to solve highly nonlinear and computationally difficult problems. Improved cognitive modeling. Fuzzy systems allow the encoding of knowledge in a form that reflects the way experts think about a complex problem. They usually think in such imprecise terms as high and low, fast and slow, heavy and light, and they also use such terms as very often and almost never, usually and hardly ever, frequently and occasionally. In order to build conventional rules, we need to define the crisp boundaries for these terms, thus breaking down the expertise into fragments. However, this fragmentation leads to the poor performance of conventional expert systems when they deal with highly complex problems. In contrast, fuzzy expert systems model imprecise information, capturing expertise much more closely to the way it is represented in the expert mind, and thus improve cognitive modeling of the problem. The ability to represent multiple experts. Conventional expert systems are built for a very narrow domain with clearly defined expertise. It makes the system's performance fully dependent on the right choice of experts. Although a common strategy is to find just one expert, when a more complex expert system is being built or when expertise is not well defined, multiple experts might be needed. Multiple experts can expand the domain, synthesize expertise and eliminate the need for a world-class expert, who is likely to be both very expensive and hard to access. However, multiple experts seldom reach close agreements. There are often differences in opinions and even conflicts. This is especially true in areas such as business and management where no simple solution exists and conflicting views should be taken into account. Fuzzy expert systems can help to represent the expertise of multiple experts when they have opposing views. Summary. 17. Although fuzzy systems allow expression of expert knowledge in a more natural way, they still depend on the rules extracted from the experts, and thus might be smart or dumb. Some experts can provide very clever fuzzy rules, but some just guess and may even get them wrong. Therefore, all rules must be tested and tuned, which can be a prolonged and tedious process. For example, it took Hitachi engineers several years to test and tune only 54 fuzzy rules to guide the Sendai subway system. Using fuzzy logic development tools, we can easily build a simple fuzzy system, but then we may spend days, weeks and even months trying out new rules and tuning our system. How do we make this process faster, or, in other words, how do we generate good fuzzy rules automatically? In recent years, several methods based on neural network technology have been used to search numerical data for fuzzy rules. Adaptive or neural fuzzy systems can find new fuzzy rules, or change and tune existing ones based on the data provided. In other words, data in rules out, or experience in common sense out. So, where is knowledge engineering heading? Expert, neural and fuzzy systems have now matured and have been applied to a broad range of different problems, mainly in engineering, medicine, finance, business and management. Each technology handles the uncertainty and ambiguity of human knowledge differently, and each technology has found its place in knowledge engineering. They no longer compete, rather they complement each other. A synergy of expert systems with fuzzy logic and neural computing improves adaptability, robustness, fault tolerance and speed of knowledge-based systems. Besides, computing with words makes them more human. It is now common practice to build intelligent systems using existing theories rather than to propose new ones, and to apply these systems to real-world problems rather than to toy problems. 1.3 Summary. We live in the era of the knowledge revolution, when the power of a nation is determined not by the number of soldiers in its army but the knowledge it possesses. Science, medicine, engineering and business propel nations towards a higher quality of life, but they also require highly qualified and skillful people. We're now adopting intelligent machines that can capture the expertise of such knowledgeable people and reason in a manner similar to humans. The desire for intelligent machines was just an elusive dream until the first computer was developed. The early computers could manipulate large databases effectively by following prescribed algorithms, but could not reason about the information provided. This gave rise to the question of whether computers could ever think. Alan Turing defined the intelligent behavior of a computer as the ability to achieve human-level performance in a cognitive task. The Turing test provided a basis for the verification and validation of knowledge-based systems. 18. Introduction to knowledge-based intelligent systems. In 1956, a summer workshop at Dartmouth College brought together 10 researchers interested in the study of machine intelligence, and a new science, artificial intelligence, was born. Since the early 1950s, AI technology has developed from the curiosity of a few researchers to a valuable tool to support humans making decisions. We have seen historical cycles of AI from the era of great ideas and great expectations in the 1960s to the disillusionment and funding cutbacks in the early 1970s, from the development of the first expert systems such as DENDRAL, Mycin and Prospector in the 1970s to the maturity of expert system technology and its massive applications in different areas in the 1980s-90s, from a simple binary model of neurons proposed in the 1940s to a dramatic resurgence of the field of artificial neural networks in the 1980s, from the introduction of fuzzy set theory and its being ignored by the West in the 1960s to numerous, fuzzy, consumer products offered by the Japanese in the 1980s and worldwide acceptance of soft computing and computing with words in the 1990s. The development of expert systems created knowledge engineering, the process of building intelligent systems. Today it deals not only with expert systems but also with neural networks and fuzzy logic. Knowledge engineering is still an art rather than engineering, but attempts have already been made to extract rules automatically from numerical data through neural network technology. Table 1.1 summarizes the key events in the history of AI and knowledge engineering from the first work on AI by McCulloch and Pitts in 1943, to the recent trends of combining the strengths of expert systems, fuzzy logic and neural computing in modern knowledge-based systems capable of computing with words. The most important lessons learned in this chapter are: Intelligence is the ability to learn and understand, to solve problems and to make decisions. Artificial intelligence is a science that has defined its goal as making machines do things that would require intelligence if done by humans. A Maschine ist haut intelligent if it can achieve human-level performance in some cognitive task. To build an intelligent machine, we have to capture, organize and use human expert knowledge in some problem area. The realization that the problem domain for intelligent machines had to be sufficiently restricted marked a major paradigm shift in AI from general-purpose, knowledge-sparse, weak methods to domain-specific, knowledge-intensive methods. This led to the development of expert systems, computer programs capable of performing at a human expert level in a narrow problem area. Expert systems use human knowledge and expertise in the form of specific rules, and are distinguished by the clean separation of the knowledge and the reasoning mechanism. They can also explain their reasoning procedures. Summary 19. Table 1.1a Summary of the main events in the history of AI and knowledge engineering. Period. Key events. The birth of artificial intelligence 1943-56. The rise of artificial intelligence 1956 late 1960s. The disillusionment in artificial intelligence late 1960s early 1970s. The discovery of expert systems early 1970s mid 1980s. The rebirth of artificial neural networks 1965 onwards. McCulloch and Pitts, A Logical Calculus of the Ideas Immanent in Nervous Activity, 1943 Turing, Computing Machinery and Intelligence, 1950 The Electronic Numerical Integrator and Calculator Project. Von Neumann. Shannon, Programming a Computer for Playing Chess, 1950. The Dartmouth College Summer Workshop on Machine Intelligence, Artificial Neural Nets and Automata Theory, 1956. Lisp, McCarthy. The General Problem Solver (GPR) Project, Newell and Simon. Newell and Simon, Human Problem Solving, 1972. Minsky, A Framework for Representing Knowledge, 1975. Cook, The Complexity of Theorem-Proving Procedures, 1971. Karp, Reducibility Among Combinatorial Problems, 1972. The Lighthill Report, 1971. DENDRAL Feigenbaum, Buchanan and Lederberg, Stanford University. Mycin Feigenbaum and Shortliff, Stanford University. Prospector, Stanford Research Institute. Prolog A Logic Programming Language. Kolmorauer. Roussel and Kowalski, France. EMYCIN, Stanford University. Waterman, A Guide to Expert Systems, 1986. Hopfield, Neural Networks and Physical Systems with Emergent Collective Computational Abilities, 1982. Kohonen, Self-Organized Formation of Topologically Correct Feature Maps, 1982. Rumelhart and McClelland, Parallel Distributed Processing, 1986. The First IEEE International Conference on Neural Networks, 1987. Haken, Neural Networks, 1994. Neural Network, MATLAB Application Toolbox, The MathWork, Inc. 20. Introduction to Knowledge-Based Intelligent Systems. Table 1.1 Kant. Period. Key events. Evolutionary computation, early 1970s onwards. Computing with words, late 1980s onwards. Rechenberg, Evolutionsstrategien Optimierung technischer System nach Prinzipien der biologischen Information, 1973. Holland, Adaptation in Natural and Artificial Systems, 1975. Koza, Genetic Programming, On the Programming of the Computers by Means of Natural Selection, 1992. Schwefel, Evolution and Optimum Seeking, 1995. Fogel, Evolutionary Computation Towards a New Philosophy of Machine Intelligence, 1995. Zadeh, Fuzzy Sets, 1965. Zadeh, Fuzzy Algorithms, 1969. Mamdani, Application of Fuzzy Logic to Approximate Reasoning Using Linguistic Synthesis, 1977. Sugano, Fuzzy Theory, 1983. Japanese, Fuzzy, Consumer Products Dishwashers, Washing Machines, Air Conditioners, Television Sets, Copiers. Sendai Subway System, Hitachi, Japan, 1986. Negoita, Expert Systems and Fuzzy Systems, 1985. The first IEEE International Conference on Fuzzy Systems. 1992. Cosco, Neural Networks and Fuzzy Systems, 1992. Cosco, Fuzzy Thinking, 1993. Yager and Zadeh, Fuzzy Sets, Neural Networks and Soft Computing, 1994. Cox, The Fuzzy Systems Handbook, 1994. Cosco, Fuzzy Engineering, 1996. Zadeh, Computing with Words, A Paradigm Shift, 1996. Fuzzy Logic, MATLAB Application Toolbox, The MathWork, Inc. One of the main difficulties in building intelligent machines, or in other words in knowledge engineering, is the knowledge acquisition bottleneck, extracting knowledge from human experts. Experts think in imprecise terms, such as very often and almost never, usually and hardly ever, frequently and occasionally, and use linguistic variables, such as high and low, fast and slow, heavy and light. Fuzzy logic. 2. Rule-based expert systems. In which we introduce the most popular choice for building knowledge-based systems, rule-based expert systems. 2.1 Introduction, or What is Knowledge? In the 1970s, it was finally accepted that to make a machine solve an intellectual problem one had to know the solution. In other words, one has to have knowledge, know-how, in some specific domain. What is knowledge? Knowledge is a theoretical or practical understanding of a subject or a domain. Knowledge is also the sum of what is currently known, and apparently knowledge is power. Those who possess knowledge are called experts. They are the most powerful and important people in their organizations. Any successful company has at least a few first-class experts, and it cannot remain in business without them. Who is generally acknowledged as an expert? Anyone can be considered a domain expert if he or she has deep knowledge of both facts and rules and strong practical experience in a particular domain. The area of the domain may be limited. For example, experts in electrical machines may have only general knowledge about transformers, while experts in life insurance marketing might have limited understanding of a real estate insurance policy. In general, an expert is a skillful person who can do things other people cannot. How do experts think? The human mental process is internal, and it is too complex to be represented as an algorithm. However, most experts are capable of expressing their knowledge in the form of rules for problem solving. Consider a simple example. Imagine, you meet an alien. He wants to cross a road. Can you help him? You are an expert in crossing roads, you've been on this job for several years. Thus you are able to teach the alien. How would you do this? 26 Rule-based expert systems. You explain to the alien that he can cross the road safely when the traffic light is green, and he must stop when the traffic light is red. These are the basic rules. Your knowledge can be formulated as the following simple statements. If the traffic light is green, then the action is go. If the traffic light is red, then the action is stop. These statements represented in the if-then form are called production rules or just rules. The term rule in AI, which is the most commonly used type of knowledge representation, can be defined as an if-then structure that relates given information or facts in the if part to some action in the then part. A rule provides some description of how to solve a problem. Rules are relatively easy to create and understand. 2.2 Rules is a knowledge representation technique. Any rule consists of two parts: the if part, called the antecedent premise or condition, and the then part called the consequent conclusion or action. The basic syntax of a rule is: if less than antecedent greater than, then less than consequent greater than. In general, a rule can have multiple antecedents joined by the keywords and conjunction or disjunction, or a combination of both. However, it is a good habit to avoid mixing conjunctions and disjunctions in the same rule. If less than antecedent 1 greater than, and less than antecedent 2 greater than, and less than antecedent n greater than, then less than consequent greater than. If less than antecedent 1 greater than, or less than antecedent 2 greater than, less than antecedent n greater than, then less than consequent greater than. Rules is a knowledge representation technique. 27. The consequent of a rule can also have multiple clauses. If less than antecedent greater than, then less than consequent 1 greater than, less than consequent 2 greater than, less than consequent m greater than. The antecedent of a rule incorporates two parts: an object, linguistic object, and its value. In our road crossing example, the linguistic object, traffic light, can take either the value green or the value red. The object and its value are linked by an operator. The operator identifies the object and assigns the value. Operators such as is, are, is not, or not are used to assign a symbolic value to a linguistic object. But expert systems can also use mathematical operators to define an object as numerical and assign it to the numerical value. For example, if age of the customer, less than 18, and cash withdrawal, greater than 1,000, then signature of the parent is required. Similar to a rule antecedent, a consequent combines an object and a value connected by an operator. The operator assigns the value to the linguistic object. In the road crossing example, if the value of traffic light is green, the first rule sets the linguistic object action to the value go. Numerical objects and even simple arithmetical expression can also be used in a rule consequent. If taxable income greater than 16,283, then Medicare levy 1/4, taxable income 1/5/100. Rules can represent relations, recommendations, directives, strategies, and heuristics. Durkin, 1994. Relation: if the fuel tank is empty, then the car is dead. Recommendation: if the season is autumn and the sky is cloudy and the forecast is drizzle, then the advice is, take an umbrella. Directive: if the car is dead and the fuel tank is empty, then the action is, refuel the car. 28 Rule-based expert systems. Strategy: if the car is dead, then the action is, check the fuel tank. Step 1 is complete. If Step 1 is complete, and the fuel tank is full, then the action is, check the battery. Step 2 is complete. Heuristic: if the spill is liquid, and the spill pH less than 6, and the spill smell is vinegar, then the spill material is acetic acid. 2.3 The main players in the expert system development team. As soon as knowledge is provided by a human expert, we can input it into a computer. We expect the computer to act as an intelligent assistant in some specific domain of expertise or to solve a problem that would otherwise have to be solved by an expert. We also would like the computer to be able to integrate new knowledge and to show its knowledge in a form that is easy to read and understand, and to deal with simple sentences in a natural language rather than an artificial programming language. Finally, we want our computer to explain how it reaches a particular conclusion. In other words, we have to build an expert system, a computer program capable of performing at the level of a human expert in a narrow problem area. The most popular expert systems are rule-based systems. A great number have been built and successfully applied in such areas as business and engineering, medicine and geology, power systems and mining. A large number of companies produce and market software for rule-based expert system development. Expert system shells for personal computers. Expert system shells are becoming particularly popular for developing rule-based systems. Their main advantage is that the system builder can now concentrate on the knowledge itself rather than on learning a programming language. What is an expert system shell? An expert system shell can be considered as an expert system with the knowledge removed. Therefore, all the user has to do is to add the knowledge in the form of rules and provide relevant data to solve a problem. Let us now look at who is needed to develop an expert system and what skills are needed. In general, there are 5 members of the expert system development team: the domain expert, the knowledge engineer, the programmer, the project. The main players in the expert system development team. 29. Figure 2.1 The main players of the expert system development team. Manager and the end user. The success of their expert system entirely depends on how well the members work together. The basic relations in the development team are summarized in Figure 2.1. The domain expert is a knowledgeable and skilled person capable of solving problems in a specific area or domain. This person has the greatest expertise in a given domain. This expertise is to be captured in the expert system. Therefore, the expert must be able to communicate his or her knowledge, be willing to participate in the expert system development and commit a substantial amount of time to the project. The domain expert is the most important player in the expert system development team. The knowledge engineer is someone who is capable of designing, building and testing an expert system. This person is responsible for selecting an appropriate task for the expert system. He or she interviews the domain expert to find out how a particular problem is solved. Through interaction with the expert, the knowledge engineer establishes what reasoning methods the expert uses to handle facts and rules and decides how to represent them in the expert system. The knowledge engineer then chooses some development software or an expert system shell, or looks at programming languages for encoding the knowledge and sometimes encodes it himself. And finally, the knowledge engineer is responsible for testing, revising and integrating the expert system into the workplace. Thus, the knowledge engineer is committed to the project from the initial design stage to the final delivery of the expert system, and even after the project is completed, he or she may also be involved in maintaining the system. The programmer is the person responsible for the actual programming, describing the domain knowledge in terms that a computer can understand. The programmer needs to have skills in symbolic programming in such AI. 30 Rule-based expert systems. Languages is Lisp, Prolog and OPS5 and also some experience in the application of different types of expert system shells. In addition, the programmer should know conventional programming languages like C, Pascal, Fortran and BASIC. If an expert system shell is used, the knowledge engineer can easily encode the knowledge into the expert system and thus eliminate the need for the programmer. However, if a shell cannot be used, a programmer must develop the knowledge and data representation structures, knowledge base and database control structure, inference engine, and dialog structure user interface. The programmer may also be involved in testing the expert system. The project manager is the leader of the expert system development team, responsible for keeping the project on track. He or she makes sure that all deliverables and milestones are met, interacts with the expert, knowledge engineer, programmer and end user. The end user, often called just the user, is a person who uses the expert system when it is developed. The user might be an analytical chemist determining the molecular structure of soil from Mars. Feigenbaum et al. 1971, a junior doctor diagnosing an infectious blood disease. Shortliff, 1976, an exploration geologist trying to discover a new mineral deposit. Duda et al. 1979, or a power system operator needing advice in an emergency. Negnovitsky, 1996. Each of these users of expert systems has different needs, which the system must meet. The system's final acceptance will depend on the user's satisfaction. The user must not only be confident in the expert system performance but also feel comfortable using it. Therefore, the design of the user interface of the expert system is also vital for the project's success. The end user's contribution here can be crucial. The development of an expert system can be started when all 5 players have joined the team. However, many expert systems are now developed on personal computers using expert system shells. This can eliminate the need for the programmer and also might reduce the role of the knowledge engineer. For small expert systems, the project manager, knowledge engineer, programmer and even the expert could be the same person. But all team players are required when large expert systems are developed. 2.4 Structure of a rule-based expert system. In the early 1970s, Newell and Simon from Carnegie Mellon University proposed a production system model, the foundation of the modern rule-based expert systems. Newell and Simon, 1972. The production model is based on the idea that humans solve problems by applying their knowledge, expressed as production rules, to a given problem represented by problem-specific information. The production rules are stored in the long-term memory and the problem-specific information or facts in the short-term memory. The production system model and the basic structure of a rule-based expert system are shown in Figure 2.2. A rule-based expert system has 5 components: the knowledge base, the database, the inference engine, the explanation facilities, and the user interface. Structure of a rule-based expert system. 31. Figure 2.2 Production system and basic structure of a rule-based expert system. A production system model. Basic structure of a rule-based expert system. The knowledge base contains the domain knowledge useful for problem solving. In a rule-based expert system, the knowledge is represented as a set of rules. Each rule specifies a relation, recommendation, directive, strategy or heuristic and has the if condition then action structure. When the condition part of a rule is satisfied, the rule is said to fire and the action part is executed. The database includes a set of facts used to match against the if condition parts of rules stored in the knowledge base. The inference engine carries out the reasoning whereby the expert system reaches a solution. It links the rules given in the knowledge base with the facts provided in the database. 32 Rule-based expert systems. The explanation facilities enable the user to ask the expert system how a particular conclusion is reached and why a specific fact is needed. An expert system must be able to explain its reasoning and justify its advice, analysis or conclusion. The user interface is the means of communication between a user seeking a solution to the problem and an expert system. The communication should be as meaningful and friendly as possible. These 5 components are essential for any rule-based expert system. They constitute its core, but there may be a few additional components. The external interface allows an expert system to work with external data files and programs written in conventional programming languages such as C, Pascal, Fortran and BASIC. The complete structure of a rule-based expert system is shown in Figure 2.3. The developer interface usually includes knowledge base editors, debugging aids and input-output facilities. All expert system shells provide a simple text editor to input and modify rules, and to check their correct format and spelling. Many expert systems also. Figure 2.3 Complete structure of a rule-based expert system. Fundamental characteristics of an expert system. 33. Include bookkeeping facilities to monitor the changes made by the knowledge engineer or expert. If a rule is changed, the editor will automatically store the change date and the name of the person who made this change for later reference. This is very important when a number of knowledge engineers and experts have access to the knowledge base and can modify it. Debugging aids usually consist of tracing facilities and break packages. Tracing provides a list of all rules fired during the program's execution, and a break package makes it possible to tell the expert system in advance where to stop so that the knowledge engineer or the expert can examine the current values in the database. Most expert systems also accommodate input-output facilities such as runtime knowledge acquisition. This enables the running expert system to ask for needed information whenever this information is not available in the database. When the requested information is input by the knowledge engineer or the expert, the program resumes. In general, the developer interface, and knowledge acquisition facilities in particular, are designed to enable a domain expert to input his or her knowledge directly in the expert system and thus to minimize the intervention of a knowledge engineer. 2.5 Fundamental characteristics of an expert system. An expert system is built to perform at a human expert level in a narrow, specialized domain. Thus, the most important characteristic of an expert system is its high-quality performance. No matter how fast the system can solve a problem, the user will not be satisfied if the result is wrong. On the other hand, the speed of reaching a solution is very important. Even the most accurate decision or diagnosis may not be useful if it is too late to apply, for instance, in an emergency, when a patient dies or a nuclear power plant explodes. Experts use their practical experience and understanding of the problem to find shortcuts to a solution. Experts use rules of thumb or heuristics. Like their human counterparts, expert systems should apply heuristics to guide the reasoning and thus reduce the search area for a solution. A unique feature of an expert system is its explanation capability. This enables the expert system to review its own reasoning and explain its decisions. An explanation in expert systems in effect traces the rules fired during a problem-solving session. This is, of course, a simplification, however a real or human explanation is not yet possible because it requires basic understanding of the domain. Although a sequence of rules fired cannot be used to justify a conclusion, we can attach appropriate fundamental principles of the domain expressed as text to each rule, or at least each high-level rule, stored in the knowledge base. This is probably as far as the explanation capability can be taken. However, the ability to explain a line of reasoning may not be essential for some expert systems. For example, a scientific system built for experts may not be required to provide extensive explanations because the conclusion it reaches. 34 Rule-based expert systems can be self-explanatory to other experts. A simple rule tracing might be quite appropriate. On the other hand, expert systems used in decision-making usually demand complete and thoughtful explanations, as the cost of a wrong decision may be very high. Expert systems employ symbolic reasoning when solving a problem. Symbols are used to represent different types of knowledge such as facts, concepts and rules. Unlike conventional programs written for numerical data processing, expert systems are built for knowledge processing and can easily deal with qualitative data. Conventional programs process data using algorithms, or in other words, a series of well-defined step-by-step operations. An algorithm always performs the same operations in the same order, and it always provides an exact solution. Conventional programs do not make mistakes, but programmers sometimes do. Unlike conventional programs, expert systems do not follow a prescribed sequence of steps. They permit inexact reasoning and can deal with incomplete, uncertain and fuzzy data. Can expert systems make mistakes? Even a brilliant expert is only a human and thus can make mistakes. This suggests that an expert system built to perform at a human expert level also should be allowed to make mistakes. But we still trust experts, although we do recognize that their judgments are sometimes wrong. Likewise, at least in most cases, we can rely on solutions provided by expert systems, but mistakes are possible and we should be aware of this. Does it mean that conventional programs have an advantage over expert systems? In theory, conventional programs always provide the same, correct, solutions. However, we must remember that conventional programs can tackle problems if, and only if, the data is complete and exact. When the data is incomplete or includes some errors, a conventional program will provide either no solution at all or an incorrect one. In contrast, expert systems recognize that the available information may be incomplete or fuzzy, but they can work in such situations and still arrive at some reasonable conclusion. Another important feature that distinguishes expert systems from conventional programs is that knowledge is separated from its processing. The knowledge base and the inference engine are split up. A conventional program is a mixture of knowledge and the control structure to process this knowledge. This mixing leads to difficulties in understanding and reviewing the program code, as any change to the code affects both the knowledge and its processing. In expert systems, knowledge is clearly separated from the processing mechanism. This makes expert systems much easier to build and maintain. When an expert system shell is used, a knowledge engineer or an expert simply enters rules in the knowledge base. Each new rule adds some new knowledge and makes the expert system smarter. The system can then be easily modified by changing or subtracting rules. Forward and backward chaining inference techniques. 35. Table 2.1 Comparison of expert systems with conventional systems and human experts. Human experts. Expert systems. Conventional programs. Use knowledge in the form of rules of thumb or heuristics to solve problems in a narrow domain. In a human brain, knowledge exists in a compiled form, capable of explaining a line of reasoning and providing the details. Use inexact reasoning and can deal with incomplete, uncertain and fuzzy information. Can make mistakes when information is incomplete or fuzzy. Enhance the quality of problem solving via years of learning and practical training. This process is slow, inefficient and expensive. Process knowledge expressed in the form of rules and use symbolic reasoning to solve problems in a narrow domain. Provide a clear separation of knowledge from its processing. Trace the rules fired during a problem-solving session and explain how a particular conclusion was reached and why specific data was needed. Permit inexact reasoning and can deal with incomplete, uncertain and fuzzy data. Can make mistakes when data is incomplete or fuzzy. Enhance the quality of problem solving by adding new rules or adjusting old ones in the knowledge base. When new knowledge is acquired, changes are easy to accomplish. Process data and use algorithms, a series of well-defined operations, to solve general numerical problems. Do not separate knowledge from the control structure to process this knowledge. Do not explain how a particular result was obtained and why input data was needed. Work only on problems where data is complete and exact. Provide no solution at all, or a wrong one, when data is incomplete or fuzzy. Enhance the quality of problem solving by changing the program code, which affects both the knowledge and its processing, making changes difficult. The characteristics of expert systems discussed above make them different from conventional systems and human experts. A comparison is shown in Table 2.1. 2.6 Forward chaining and backward chaining inference techniques. In a rule-based expert system, the domain knowledge is represented by a set of if-then production rules and data is represented by a set of facts about the current situation. The inference engine compares each rule stored in the 36 rule-based expert systems. Figure 2.4 The inference engine cycles via a match-fire procedure. Knowledge base with facts contained in the database. When the if-conditioned part of the rule matches a fact, the rule is fired and its then-action part is executed. The fired rule may change the set of facts by adding a new fact, as shown in Figure 2.4. Letters in the database and the knowledge base are used to represent situations or concepts. The matching of the rule if parts to the facts produces inference chains. The inference chain indicates how an expert system applies the rules to reach a conclusion. To illustrate chaining inference techniques, consider a simple example. Suppose the database initially includes facts A, B, C, D and E, and the knowledge base contains only 3 rules. Rule 1, if Y is true, and distrue then zistrue. Rule 2, if X is true, and bistrue and istrue then yistrue. Rule 3, if A is true, then zistrue. The inference chain shown in Figure 2.5 indicates how the expert system applies the rules to infer fact Z. First, Rule 3 is fired to deduce new fact X from given fact A. Then Rule 2 is executed to infer fact Y from initially known facts B and E, and already known fact X. And finally, Rule 1 applies initially known fact and just obtained fact Y to arrive at conclusion Z. An expert system can display its inference chain to explain how a particular conclusion was reached. This is an essential part of its explanation facilities. Forward and backward chaining inference techniques. 37. Figure 2.5 An example of an inference chain. The inference engine must decide when the rules have to be fired. There are 2 principal ways in which rules are executed. One is called forward chaining and the other backward chaining. Waterman and Hayes Roth, 1978. 2.6.1 Forward chaining. The example discussed above uses forward chaining. Now consider this technique in more detail. Let us first rewrite our rules in the following form. Rule 1, Y and D, C. Rule 2, X and B and E, Y. Rule 3, X. Arrows here indicate the if and then parts of the rules. Let us also add 2 more rules. Rule 4, C, L. Rule 5, L and M, N. Figure 2.6 shows how forward chaining works for this simple set of rules. Forward chaining is the data-driven reasoning. The reasoning starts from the known data and proceeds forward with that data. Each time only the topmost rule is executed. When fired, the rule adds a new fact in the database. Any rule can be executed only once. The match-fire cycle stops when no further rules can be fired. In the first cycle, only 2 rules, Rule 3, A, X and Rule 4, C, L, match facts in the database. Rule 3, X is fired first as the topmost one. The if part of this rule matches fact A in the database, its then part is executed and new fact X is added to the database. Then Rule 4, C, L is fired and fact L is also placed in the database. In the second cycle, Rule 2, X and B and E. Y is fired because facts B, E and X are already in the database, and as a consequence fact Y is inferred and put in the database. This in turn causes Rule 1, Y and D, C to execute, placing fact Z in the database. Cycle 3. Now the match-fire cycles stop because the if part of Rule 5, L and M, N does not match all facts in the database and thus Rule 5 cannot be fired. 38 Rule-based expert systems. Figure 2.6 Forward chaining. Forward chaining is a technique for gathering information and then inferring from it whatever can be inferred. However, in forward chaining, many rules may be executed that have nothing to do with the established goal. Suppose, in our example, the goal was to determine fact Z. We had only 5 rules in the knowledge base and 4 of them were fired. But rule 4, C, L, which is unrelated to fact Z, was also fired among others. A real rule-based expert system can have hundreds of rules, many of which might be fired to derive new facts that are valid, but unfortunately unrelated to the goal. Therefore, if our goal is to infer only one particular fact, the forward chaining inference technique would not be efficient. In such a situation, backward chaining is more appropriate. 2.6.2 Backward chaining. Backward chaining is the goal-driven reasoning. In backward chaining, an expert system has the goal, a hypothetical solution, and the inference engine attempts to find the evidence to prove it. First, the knowledge base is searched to find rules that might have the desired solution. Such rules must have the goal in their then action parts. If such a rule is found and its if condition part matches data in the database, then the rule is fired and the goal is proved. However, this is rarely the case. Thus the inference engine puts aside the rule it is working with, the rule is said to stack, and sets up a new goal, a sub-goal, to prove the if part of this rule. Then the knowledge base is searched again for rules that can prove the sub-goal. The inference engine repeats the process of stacking the rules until no rules are found in the knowledge base to prove the current sub-goal. Forward and backward chaining inference techniques. 39. Figure 2.7 Backward chaining. Figure 2.7 shows how backward chaining works, using the rules for the forward chaining example. In Pass 1, the inference engine attempts to infer fact Z. It searches the knowledge base to find the rule that has the goal, in our case fact Z, in its then part. The inference engine finds and stacks rule 1, Y and D. C. The if part of rule 1 includes facts Y and D, and thus these facts must be established. In Pass 2, the inference engine sets up the sub-goal, fact Y, and tries to determine it. First it checks the database, but fact Y is not there. Then the knowledge base is searched again for the rule with fact Y in its then part. The 40 Rule-based expert systems. Inference engine locates and stacks rule 2, X and B and E. Y. The if part of rule 2 consists of facts X, B and E, and these facts also have to be established. In Pass 3, the inference engine sets up a new sub-goal, fact X. It checks the database for fact X, and when that fails, searches for the rule that infers X. The inference engine finds and stacks rule 3, X. Now it must determine fact A. In Pass 4, the inference engine finds fact A in the database, rule 3, A. X is FI read and new fact X is inferred. In Pass 5, the inference engine returns to the sub-goal fact Y and once again tries to execute rule 2, X and B and E. Y. Facts X, B and E are in the database and thus rule 2 is fired and a new fact, fact Y, is added to the database. In Pass 6, the system returns to rule 1, Y and D. C trying to establish the original goal, fact Z. The if part of rule 1 matches all facts in the database, rule 1 is executed and thus the original goal is finally established. Let us now compare figure 2.6 with figure 2.7. As you can see, 4 rules were FI read when forward chaining was used, but just 3 rules when we applied backward chaining. This simple example shows that the backward chaining inference technique is more effective when we need to infer one particular fact, in our case fact Z. In forward chaining, the data is known at the beginning of the inference process, and the user is never asked to input additional facts. In backward chaining, the goal is set up and the only data used is the data needed to support the direct line of reasoning, and the user may be asked to input any fact that is not in the database. How do we choose between forward and backward chaining? The answer is to study how a domain expert solves a problem. If an expert first needs to gather some information and then tries to infer from it whatever can be inferred, choose the forward chaining inference engine. However, if your expert begins with a hypothetical solution and then attempts to find facts to prove it, choose the backward chaining inference engine. Forward chaining is a natural way to design expert systems for analysis and interpretation. For example, DENDRAL, an expert system for determining the molecular structure of unknown soil based on its mass spectral data, Feigenbaum et al., 1971, uses forward chaining. Most backward chaining expert systems are used for diagnostic purposes. For instance, MySyn, a medical expert system for diagnosing infectious blood diseases. Shortlift, 1976, uses backward chaining. Can we combine forward and backward chaining? Many expert system shells use a combination of forward and backward chaining inference techniques, so the knowledge engineer does not have to choose between them. However, the basic inference mechanism is usually backward chaining. Only when a new fact is established is forward chaining employed to maximize the use of the new data. Media Advisor, a demonstration rule-based expert system. 41. 2.7 Media Advisor, a demonstration rule-based expert system. To illustrate some of the ideas discussed above, we next consider a simple rule-based expert system. The Leonardo expert system shell was selected as a tool to build a decision support system called Media Advisor. The system provides advice on selecting a medium for delivering a training program based on the trainee's job. For example, if a trainee is a mechanical technician responsible for maintaining hydraulic systems, an appropriate medium might be a workshop, where the trainee could learn how basic hydraulic components operate, how to troubleshoot hydraulics problems, and how to make simple repairs to hydraulic systems. On the other hand, if a trainee is a clerk assessing insurance applications, a training program might include lectures on specific problems of the task, as well as tutorials where the trainee could evaluate real applications. For complex tasks, where trainees are likely to make mistakes, a training program should also include feedback on the trainee's performance. Knowledge Base. Media Advisor, a demonstration rule-based expert system. Rule 1. If the environment is papers, or the environment is manuals, the environment is documents, the environment is textbooks, then the stimulus_situation is verbal. Rule 2. If the environment is pictures, or the environment is illustrations, the environment is photographs, the environment is diagrams, then the stimulus_situation is visual. Rule 3. If the environment is machines, or the environment is buildings, the environment is tools, then the stimulus_situation is physical object. Rule 4. If the environment is numbers, or the environment is formulas, the environment is computer programs, then the stimulus_situation is symbolic. 42 Rule-based expert systems. Rule 5. If the job is lecturing, or the job is advising, the job is counseling, then the stimulus_response is oral. Rule 6. If the job is building, or the job is repairing, the job is troubleshooting, then the stimulus_response is hands-on. Rule 7. If the job is writing, or the job is typing, the job is drawing, then the stimulus_response is documented. Rule 8. If the job is evaluating, or the job is reasoning, the job is investigating, then the stimulus_response is analytical. Rule 9. If the stimulus_situation is physical object, and the stimulus_response is hands-on, and feedback is required, then medium is workshop. Rule 10. If the stimulus_situation is symbolic and the stimulus_response is analytical and feedback is required, then medium is lecture tutorial. Rule 11. If the stimulus_situation is visual and the stimulus_response is documented and feedback is not required, then medium is videocassette. Rule 12. If the stimulus_situation is visual and the stimulus_response is oral and feedback is required, then medium is lecture tutorial. Media Advisor, a demonstration rule-based expert system. 43. Rule 13. If the stimulus_situation is verbal and the stimulus_response is analytical and feedback is required, then medium is lecture tutorial. Rule 14. If the stimulus_situation is verbal and the stimulus_response is oral and feedback is required, then medium is role-play exercises. The seek directive sets up the goal of the rule set. Seek medium. Objects. Media Advisor uses 6 linguistic objects: environment, stimulus_situation, job, stimulus_response, feedback, and medium. Each object can take one of the allowed values. For example, object environment can take the value of papers, manuals, documents, textbooks, pictures, illustrations, photographs, diagrams, machines, buildings, tools, numbers, formulas, computer programs. An object and its value constitute a fact. For instance, the environment is machines, and the job is repairing. All facts are placed in the database. Object. Allowed values. Object. Allowed values. Environment. Papers. Manuals. Documents. Textbooks. Pictures. Illustrations. Photographs. Diagrams. Machines. Buildings. Tools. Numbers, formulas. Computer programs. Stimulus_situation. Verbal, visual, physical object. Symbolic. Job. Stimulus_response. Feedback. Lecturing. Advising. Counseling. Building. Repairing. Troubleshooting. Writing. Typing. Drawing. Evaluating. Reasoning. Investigating. Oral, hands-on, documented, analytical. Required. Not required. 44 Rule-based expert systems. Options. The final goal of the rule-based expert system is to produce a solution to the problem based on input data. In Media Advisor, the solution is a medium selected from the list of 4 options. Medium is workshop. Medium is lecture, tutorial. Medium is videocassette. Medium is role-play exercises. Dialogue. In the dialogue shown below, the expert system asks the user to input the data needed to solve the problem, the environment, the job, and feedback. Based on the answers supplied by the user, answers are indicated by arrows. The expert system applies rules from its knowledge base to infer that the stimulus_situation is physical object, and the stimulus_response is hands-on. Rule 9 then selects one of the allowed values of medium. What sort of environment is a trainee dealing with on the job? Machines. Rule 3 if the environment is machines, or the environment is buildings, the environment is tools, then the stimulus_situation is physical object. In what way is a trainee expected to act or respond on the job? Repairing. Rule 6 if the job is building, or the job is repairing, the job is troubleshooting, then the stimulus_response is hands-on. Is feedback on the trainee's progress required during training? Required. Rule 9 if the stimulus_situation is physical object, and the stimulus_response is hands-on, and feedback is required, then medium is workshop. Medium is workshop. Media, a demonstration rule-based expert system. 45. Inference techniques. The standard inference technique in Leonardo is backward chaining with opportunistic forward chaining, which is the most efficient way to deal with the available information. However, Leonardo also enables the user to turn off either backward or forward chaining, and thus allows us to study each inference technique separately. Forward chaining is data-driven reasoning, so we need first to provide some data. Assume that the environment is machines. Environment, instantiated by user input to machines. The job is repairing. Job, instantiated by user input to repairing. Feedback is required. Feedback, instantiated by user input to required. The following process will then happen. Rule 3 fires, stimulus_situation, instantiated by Rule 3 to physical object. Rule 6 fires, stimulus_response, instantiated by Rule 6 to hands-on. Rule 9 fires, medium, instantiated by Rule 9 to workshop. No rules, fire, stop. Backward chaining is goal-driven reasoning, so we need first to establish a hypothetical solution, the goal. Let us, for example, set up the following goal. Medium is workshop. Pass 1. Trying Rule 9. Rule 9 stacked. Pass 2. Trying Rule 3. Rule 3 stacked. Ask environment machines. Trying Rule 3. Pass 3. Trying Rule 9. Rule 9 stacked. Need to find object, stimulus_situation. Object, stimulus_situation, sought as physical object. Need to find object, environment. Object, environment, sought as machines. Environment, instantiated by user input to machines. Stimulus underscore situation, instantiated by rule 3 to physical object. Need to find object, stimulus underscore response. Object, stimulus underscore response status hands-on. 46 rule-based expert systems. Pass 4 trying rule 6. Rule 6 stacked. Ask job repairing. Trying rule 6. Pass 5 trying rule 9. Rule 9 stacked. Ask feedback required. Trying rule 9. Medium is workshop. Need to find object, job. Object, job, sought as, building. Job, instantiated by user input to, repairing. Stimulus underscore response, instantiated by rule 6 to, hands-on. Need to find object, feedback. Object, feedback, sought as, required. Feedback, instantiated by user input to, required. Medium, instantiated by rule 9 to, workshop. It is useful to have a tree diagram that maps a consultation session with an expert system. A diagram for Media Advisor is shown in Figure 2.8. The root node is the goal. When the system is started, the inference engine seeks to determine the goal's value. Goal, medium. Rule 9. Stimulus situation. Rule 10. Question mark. Rule 11. Rule 12. Rule 13. Stimulus response. Rule 14. Feedback. Question mark. Question mark. Rule 1. Rule 2. Rule 3. Question mark. Environment. Rule 4. Ask. Environment. Rule 5. Rule 6. Question mark. Job. Rule 7. Ask. Job. Rule 8. Ask. Feedback. Figure 2.8 tree diagram for the rule-based expert system Media Advisor. Conflict resolution. 47. Does Media Advisor handle all possible situations? When we start to use our expert system more often, we might find that the provided options do not cover all possible situations. For instance, the following dialogue might occur. What sort of environment is a trainee dealing with on the job? Illustrations. In what way is a trainee expected to act or respond on the job? Drawing. Is feedback on the trainee's progress required during training? Required. I am unable to draw any conclusions on the basis of the data. Thus, Media Advisor in its present state cannot handle this particular situation. Fortunately, the expert system can easily be expanded to accommodate more rules until it finally does what the user wants it to do. 2.8 Conflict resolution. Earlier in this chapter, we considered two simple rules for crossing a road. Let us now add a third rule. We will get the following set of rules. Rule 1. If the traffic light is green, then the action is go. Rule 2. If the traffic light is red, then the action is stop. Rule 3. If the traffic light is red, then the action is go. What will happen? The inference engine compares if conditioned parts of the rules with data available in the database, and when conditions are satisfied, the rules are set to fire. The firing of one rule may affect the activation of other rules, and therefore the inference engine must allow only one rule to fire at a time. In our road crossing example, we have two rules, Rule 2 and Rule 3, with the same if part. Thus both of them can be set to fire when the condition part is satisfied. These rules represent a conflict set. The inference engine must determine which rule to fire from such a set. A method for choosing a rule to fire when more than one rule can be fired in a given cycle is called conflict resolution. 48 Rule-based expert systems. If the traffic light is red, which rule should be executed? In forward chaining, both rules would be fired. Rule 2 is fired first as the topmost one, and as a result, its then part is executed and linguistic object action obtains value stop. However, Rule 3 is also fired because the condition part of this rule matches the fact, traffic light, is red, which is still in the database. As a consequence, object action takes new value go. This simple example shows that the rule order is vital when the forward chaining inference technique is used. How can we resolve a conflict? The obvious strategy for resolving conflicts is to establish a goal and stop the rule execution when the goal is reached. In our problem, for example, the goal is to establish a value for linguistic object action. When the expert system determines a value for action, it has reached the goal and stops. Thus, if the traffic light is red, Rule 2 is executed, object action attains value stop and the expert system stops. In the given example, the expert system makes a right decision. However, if we arrange the rules in the reverse order, the conclusion would be wrong. It means that the rule order in the knowledge base is still very important. Are there any other conflict resolution methods? Several methods are in use. Giratano and Riley, 1998, Shirai and Tsuji, 1982. Fire the rule with the highest priority. In simple applications, the priority can be established by placing the rules in an appropriate order in the knowledge base. Usually this strategy works well for expert systems with around 100 rules. However, in some applications, the data should be processed in order of importance. For example, in a medical consultation system, Durkin, 1994, the following priorities are introduced. Goal 1. Prescription is prescription. Rule 1 Meningitis Prescription 1 Priority 100 If infection is meningitis and the patient is a child, then prescription is number_1. And drug recommendation is ampicillin and drug recommendation is gentamicin and display meningitis prescription 1. Rule 2 Meningitis Prescription 2 Priority 90. If infection is meningitis and the patient is an adult, then prescription is number_2. And drug recommendation is penicillin and display meningitis prescription 2. Conflict resolution. 49. Fire the most specific rule. This method is also known as the longest matching strategy. It is based on the assumption that a specific rule processes more information than a general one. For example, Rule 1. If the season is autumn and the sky is cloudy and the forecast is rain, then the advice is, stay home. Rule 2. If the season is autumn, then the advice is, take an umbrella. If the season is autumn, the sky is cloudy and the forecast is rain, then Rule 1 would be fired because its antecedent, the matching part, is more specific than that of Rule 2. But if it is known only that the season is autumn, then Rule 2 would be executed. Fire the rule that uses the data most recently entered in the database. This method relies on time tags attached to each fact in the database. In the conflict set, the expert system first fires the rule whose antecedent uses the data most recently added to the database. For example, Rule 1. If the forecast is rain. 8:16 p.m. November 25, 96. Then the advice is, take an umbrella. Rule 2. If the weather is wet. 10:18 a.m. November 26, 96. Then the advice is, stay home. Assume that the if parts of both rules match facts in the database. In this case, Rule 2 would be fired since the fact weather is wet was entered after the fact forecast is rain. This technique is especially useful for real-time expert system applications when information in the database is constantly updated. The conflict resolution methods considered above are simple and easily implemented. In most cases, these methods provide satisfactory solutions. However, as a program grows larger and more complex, it becomes increasingly difficult for the knowledge engineer to manage and oversee rules in the knowledge base. The expert system itself must take at least some of the burden and understand its own behavior. To improve the performance of an expert system, we should supply the system with some knowledge about the knowledge it possesses, or in other words, metaknowledge. Metaknowledge can be simply defined as knowledge about knowledge. Metaknowledge is knowledge about the use and control of domain knowledge in an expert system. Waterman, 1986. In rule-based expert systems, metaknowledge is represented by metarules. A metarule determines a strategy for the use of task-specific rules in the expert system. 50 Rule-based expert systems. What is the origin of metaknowledge? The knowledge engineer transfers the knowledge of the domain expert to the expert system, learns how problem-specific rules are used, and gradually creates in his or her own mind a new body of knowledge about the overall behavior of the expert system. This new knowledge, or metaknowledge, is largely domain-independent. For example, Metarule 1. Rules supplied by experts have higher priorities than rules supplied by novices. Metarule 2. Rules governing the rescue of human lives have higher priorities than rules concerned with clearing overloads on power system equipment. Can an expert system understand and use metarules? Some expert systems provide a separate inference engine for metarules. However, most expert systems cannot distinguish between rules and metarules. Thus, metarules should be given the highest priority in the existing knowledge base. When fired, a metarule injects some important information into the database that can change the priorities of some other rules. 2.9 Advantages and disadvantages of rule-based expert systems. Rule-based expert systems are generally accepted as the best option for building knowledge-based systems. Which features make rule-based expert systems particularly attractive for knowledge engineers? Among these features are natural knowledge representation. An expert usually explains the problem-solving procedure with such expressions as this: in such and such situation, I do so and so. These expressions can be represented quite naturally as if-then production rules. Uniform structure. Production rules have the uniform if-then structure. Each rule is an independent piece of knowledge. The very syntax of production rules enables them to be self-documented. Separation of knowledge from its processing. The structure of a rule-based expert system provides an effective separation of the knowledge base from the inference engine. This makes it possible to develop different applications using the same expert system shell. It also allows a graceful and easy expansion of the expert system. To make the system smarter, a knowledge engineer simply adds some rules to the knowledge base without intervening in the control structure. Summary. 51. Dealing with incomplete and uncertain knowledge. Most rule-based expert systems are capable of representing and reasoning with incomplete and uncertain knowledge. For example, the rule: if season is autumn, and sky is cloudy, and wind is slow, then forecast is clear. Forecast is drizzle. Forecast is rain. CF 0.1. CF 1.0. CF 0.9. Could be used to express the uncertainty of the following statement: if the season is autumn and it looks like drizzle, then it will probably be another wet day today. The rule represents the uncertainty by numbers called certainty factors FCF 0.1 grams. The expert system uses certainty factors to establish the degree of confidence or level of belief that the rule's conclusion is true. This topic will be considered in detail in Chapter 3. All these features of the rule-based expert systems make them highly desirable for knowledge representation in real-world problems. Are rule-based expert systems problem-free? There are three main shortcomings. Opaque relations between rules. Although the individual production rules tend to be relatively simple and self-documented, their logical interactions within the large set of rules may be opaque. Rule-based systems make it difficult to observe how individual rules serve the overall strategy. This problem is related to the lack of hierarchical knowledge representation in the rule-based expert systems. Ineffective search strategy. The inference engine applies an exhaustive search through all the production rules during each cycle. Expert systems with a large set of rules, over 100 rules, can be slow, and thus large rule-based systems can be unsuitable for real-time applications. Inability to learn. In general, rule-based expert systems do not have an ability to learn from the experience. Unlike a human expert, who knows when to break the rules, an expert system cannot automatically modify its knowledge base, or adjust existing rules or add new ones. The knowledge engineer is still responsible for revising and maintaining the system. 2.10 Summary. In this chapter, we presented an overview of rule-based expert systems. We briefly discussed what knowledge is, and how experts express their knowledge in the form of production rules. We identified the main players in the expert 52 rule-based expert systems. System development team and showed the structure of a rule-based system. We discussed fundamental characteristics of expert systems and noted that expert systems can make mistakes. Then we reviewed the forward and backward chaining inference techniques and debated conflict resolution strategies. Finally, the advantages and disadvantages of rule-based expert systems were examined. The most important lessons learned in this chapter are: Knowledge is a theoretical or practical understanding of a subject. Knowledge is the sum of what is currently known. An expert is a person who has deep knowledge in the form of facts and rules and strong practical experience in a particular domain. An expert can do things other people cannot. The experts can usually express their knowledge in the form of production rules. Production rules are represented as if antecedent then consequent statements. A production rule is the most popular type of knowledge representation. Rules can express relations, recommendations, directives, strategies and heuristics. A computer program capable of performing at a human expert level in a narrow problem domain area is called an expert system. The most popular expert systems are rule-based expert systems. In developing rule-based expert systems, shells are becoming particularly common. An expert system shell is a skeleton expert system with the knowledge removed. To build a new expert system application, all the user has to do is to add the knowledge in the form of rules and provide relevant data. Expert system shells offer a dramatic reduction in the development time of expert systems. The expert system development team should include the domain expert, the knowledge engineer, the programmer, the project manager and the end user. The knowledge engineer designs, builds and tests an expert system. He or she captures the knowledge from the domain expert, establishes reasoning methods and chooses the development software. For small expert systems based on expert system shells, the project manager, knowledge engineer, programmer and even the expert could be the same person. A rule-based expert system has 5 basic components: the knowledge base, the database, the inference engine, the explanation facilities and the user interface. The knowledge base contains the domain knowledge represented as a set of rules. The database includes a set of facts used to match against the if parts of rules. The inference engine links the rules with the facts and carries out the reasoning whereby the expert system reaches a solution. The explanation facilities enable the user to query the expert system about how a particular conclusion is reached and why a specific fact is needed. The user interface is the means of communication between a user and an expert system. 5. Frame-based expert systems, in which we introduce frames as one of the common methods used for representing knowledge in expert systems. Describe how to develop a frame-based expert system and illustrate the theory through an example. 5.1 Introduction, or what is a frame? Knowledge in a computer can be represented through several techniques. In the previous chapters, we considered rules. In this chapter, we will use frames for the knowledge representation. What is a frame? A frame is a data structure with typical knowledge about a particular object or concept. Frames, first proposed by Marvin Minsky in the 1970s. Minsky, 1975, are used to capture and represent knowledge in a frame-based expert system. Boarding passes shown in Figure 5.1 represent typical frames with knowledge about airline passengers. Both frames have the same structure. Each frame has its own name and a set of attributes, or slots, associated with it. Name, weight, height and age are slots in the frame person. Model, processor, memory and price are slots in the frame computer. Each attribute or slot has a value attached to it. In Figure 5.1a, for example, slot carrier has value Qantas Airways SandSlot gate has value 2. In some cases, instead of a particular value, a slot may have a procedure that determines the value. In expert systems, frames are often used in conjunction with production rules. Why is it necessary to use frames? Frames provide a natural way for the structured and concise representation of knowledge. In a single entity, a frame combines all necessary knowledge about a particular object or concept. A frame provides a means of organizing knowledge in slots to describe various attributes and characteristics of the object. Earlier we argued that many real-world problems can be naturally expressed by if-then production rules. However, a rule-based expert system using a 132. Frame-based expert systems. Figure 5.1 Boarding pass frames. Systematic search technique works with facts scattered throughout the entire knowledge base. It may search through the knowledge that is not relevant to a given problem, and as a result, the search may take a great deal of time. If, for example, we are searching for knowledge about Qantas frequent flyers, then we want to avoid the search through knowledge about Air New Zealand or British Airways passengers. In this situation, we need frames to collect the relevant facts within a single structure. Basically, frames are an application of object-oriented programming for expert systems. What is object-oriented programming? Object-oriented programming can be defined as a programming method that uses objects as a basis for analysis, design and implementation. In object-oriented programming, an object is defined as a concept, abstraction or thing with crisp boundaries and meaning for the problem at hand. Rumbaugh et al., 1991. All objects have identity and are clearly distinguishable. Michael Black, Audi 5000 Turbo, IBM Aptiva S35 are examples of objects. An object combines both data structure and its behavior in a single entity. This is in sharp contrast to conventional programming, in which data structure and the program behavior have concealed or vague connections. Object-oriented programming offers a natural way of representing the real world in a computer, and also illuminates the problem of data dependency, which is inherent in conventional programming. Taylor, 1992. When programmers create an object in an object-oriented programming language, they first assign a name to the object, then determine a set of attributes to describe the object's characteristics, and at last write procedures to specify the object's behavior. A knowledge engineer refers to an object as a frame, the term introduced by Minsky, which has become the AI jargon. Today the terms are used as synonyms. Frames is a knowledge representation technique. 133. 5.2 Frames is a knowledge representation technique. The concept of a frame is defined by a collection of slots. Each slot describes a particular attribute or operation of the frame. In many respects, a frame resembles the traditional record that contains information relevant to typical entities. Slots are used to store values. A slot may contain a default value or a pointer to another frame, a set of rules or procedure by which the slot value is obtained. In general, slots may include such information as 1. Frame name. 2. Relationship of the frame to the other frames. The frame IBM Aptiva S35 might be a member of the class computer, which in turn might belong to the class hardware. 3. Slot value. A slot value can be symbolic, numeric or Boolean. For example, in the frames shown in Figure 5.1, the slot name has symbolic values, and the slot gate numeric values. Slot values can be assigned when the frame is created or during a session with the expert system. 4. Default slot value. That default value is taken to be true when no evidence to the contrary has been found. For example, a car frame might have 4 wheels and a chair frame 4 legs as default values in the corresponding slots. 5. Range of the slot value. The range of the slot value determines whether a particular object or concept complies with the stereotype requirements defined by the frame. For example, the cost of a computer might be specified between $750 and $1,500. 6. Procedural information. A slot can have a procedure, a self-contained arbitrary piece of computer code, attached to it, which is executed if the slot value is changed or needed. There are 2 types of procedures often attached to slots. A when changed procedure is executed when new information is placed in the slot. B. When needed procedure is executed when information is needed for the problem solving, but the slot value is unspecified. Such procedural attachments are often called daemons. Frame-based expert systems also provide an extension to the slot value structure through the application of facets. What is a facet? A facet is a means of providing extended knowledge about an attribute of a frame. Facets are used to establish the attribute value, control end-user queries, and tell the inference engine how to process the attribute. In general, frame-based expert systems allow us to attach value, prompt and inference facets to attributes. Value facets specify default and initial values. 134. Frame-based expert systems. Of an attribute, prompt facets enable the end-user to enter the attribute value online during a session with the expert system. And finally, inference facets allow us to stop the inference process when the value of a specified attribute changes. What is the correct level of decomposition of a problem into frames, slots and facets? Decomposition of a problem into frames into slots and facets depends on the nature of the problem itself and the judgment of the knowledge engineer. There is no predefined, correct, representation. Figure 5.2 illustrates frames describing computers. The topmost frame represents the class computer and the frames below describe instances IBM Aptiva S35 and IBM Aptiva S9C. 2 types of attributes are used here. String str for symbolic information and numeric n for numeric data. Note default and initial value facets attached to the slots floppy, power supply, warranty and stock in the class computer. The attribute names, types, default and initial values are the properties inherited by instances. What are the class and instances? The word frame often has a vague meaning. The frame may refer to a particular object, for example the computer IBM Aptiva S35, or to a group of similar objects. To be more precise, we will use the instance frame when referring to a particular object, and the class frame when referring to a group of similar objects. A class frame describes a group of objects with common attributes. Animal, Person, car and computer are all class frames. In AI, however, the abbreviation, class, is often used instead of the term, class frame. Each frame in a frame-based system knows its class. In other words, the frame's class is an implicit property of the frame. For example, instances in Figure 5.2 identify their class in the slot class. If objects are the basis of the frame-based systems, why bother with classes? Grouping objects into classes helps us to represent a problem in an abstract form. Minsky himself described frames as data structures for representing stereotyped situations. In general, we are less concerned with defining strictly and exhaustively the properties of each object, and more concerned with the salient properties typical for the entire class. Let us take, for example, the class of birds. Can a bird fly? A typical answer is yes. Almost all birds can fly, and thus we think of the ability to fly as being an essential property of the class of birds, even though there are birds, such as ostriches, which cannot fly. In other words, an eagle is a better member of the class bird than an ostrich because an eagle is a more typical representative of birds. Frame-based systems support class inheritance. The fundamental idea of inheritance is that attributes of the class frame represent things that are typically true for all objects in the class. However, slots in the instance frames can be filled with actual data uniquely specified for each instance. Consider the simple frame structure represented in Figure 5.3. The class passenger car has several attributes typical for all cars. This class is to heterogeneous of the attributes Villetin, even though we can place certain restrictions upon such attributes as engine type, drivetrain type and transmission type. Note that the attributes are declared as compound C. Compound attributes can assume only one value from a group of symbolic values. For Figure 5.2 computer class and instances 135 frames ASA Nold-Gay representation technique. 136. Frame-based expert systems. Figure 5.3 Inheritance of slot values in a simple frame structure. A. Relations of the car frames, B. Car frames and their slots. Frames is a knowledge representation technique. 137. Example: the attribute engine type can assume the value of either inline 4-cylinder or V6, but not both. The class Mazda is linked to its superclass passenger car by the is a relation. The Mazda inherits all attributes of the superclass and also declares the attribute country of manufacture with the default value Japan attached to it. The class Mazda 626 introduces 3 additional attributes: model, color and owner. Finally, the instance frame Mazda Drive 1216 inherits its country of manufacture from the Mazda frame, as the Mazda 626 does, and establishes single values for all compound attributes. Can an instance frame overwrite attribute values inherited from the class frame? An instance frame can overwrite, or in other words violate, some of the typical attribute values in the hierarchy. For example, the class Mazda 626 has an average fuel consumption of 22 miles per gallon, but the instance Mazda Drive 1216 has a worse figure because it has done a lot of miles. Thus the Mazda Drive 1216 frame remains the instance of the class Mazda 626, with access to the properties further up the hierarchy, even though it violates the typical value in its class. Relationships between frames in such a hierarchy constitute a process of specialization. The class frame on the top of the hierarchy represents some generic concept, class frames further down stand for a more restricted concept, and the instances are closer to exemplification. How are objects related in a frame-based system? Is a relationship the only one available to us? In general, there are 3 types of relationships between objects: generalization, aggregation and association. Generalization denotes a kind of, or, is a relationship between a superclass and its subclasses. For example, a car is a vehicle, or in other words, car represents a subclass of the more general superclass vehicle. Each subclass inherits all features of the superclass. Aggregation is a part of, or part-whole, relationship in which several subclasses representing components are associated with a superclass representing a whole. For example, an engine is a part of a car. Association describes some semantic relationship between different classes which are unrelated otherwise. For example, Mr. Black owns a house, a car and a computer. Such classes as house, car and computer are mutually independent, but they are linked with the frame Mr. Black through the semantic association. Unlike generalization and aggregation relationships, associations usually appear as verbs and are inherently bidirectional. Does a computer own Mr. Black? Of course, the name of a bidirectional association reads in a particular direction. Mr. Black owns a computer, but this direction can be changed to the opposite. The inverse of owns is belongs to, and thus we can anticipate that a computer belongs to Mr. Black. In fact, both directions are equally meaningful and refer to the same association. Figure 5.4 illustrates all three types of relationships between different objects. 138. Frame-based expert systems. Figure 5.4 Three types of relationships among objects: A. Generalization, B. Aggregation, C. Association. 5.3 Inheritance in frame-based systems. Inheritance is an essential feature of frame-based systems. Inheritance can be defined as the process by which all characteristics of a class frame are assumed by the instance frame. A common use of inheritance is to impose default features on all instance frames. We can create just one class frame that contains generic characteristics of some object or concept, and then obtain several instance frames without encoding the class-level characteristics. A hierarchical arrangement of a frame-based system can be viewed as a tree that is turned over. The highest level of abstraction is represented at the top by the root of the tree. Branches below the root illustrate lower levels of abstraction, and leaves at the bottom appear as instance frames. Each frame inherits characteristics of all related frames at the higher levels. Figure 5.5 shows a hierarchy of frames representing zero-emission Z vehicles. The root, Z vehicle, has three branches: electric vehicle, solar vehicle. Inheritance in frame-based systems. 139. Figure 5.5 One parent inheritance in the zero-emission vehicle structure. 140. Frame-based expert systems. And muscle vehicle. Let us now follow just one branch, the electric vehicle branch. It is subdivided into car, motorcycle and scooter. Then car branches into sedan, van and truck, and finally, the leaf, the instance frame Ford EcoStar, appears at the bottom. The instance Ford EcoStar inherits all the characteristics of its parent frame. The instance Ford EcoStar indeed has only one parent, the class frame van. Furthermore, in Figure 5.5, any frame except the root frame Z vehicle has only one parent. In this type of structure, each frame inherits knowledge from its parent, grandparent, great-grandparent, etc. Can a frame have more than one parent? In many problems, it is quite natural to represent objects relating to different worlds. For example, we may wish to create a class of muscle solar electric vehicles. In such vehicles, people can pedal, while an electric drive system is used to travel uphill, and solar panels assist in recharging batteries for the electric system. Thus, the frame muscle solar electric vehicle should combine specific properties of three classes: muscle vehicle, solar vehicle and electric vehicle. The only requirement for multiple parent inheritance is that attributes of all parents must be uniquely specified. In frame-based systems, several classes can use the same attribute names. However, when we use multiple inheritance, all parents must have unique attribute names. If we want, for example, to create a child class muscle solar electric vehicle related to parents muscle vehicle, solar vehicle and electric vehicle, we must get rid of such properties as weight and top speed in the parent classes. Only then can we create the child class. In other words, to create multiple inheritance we must reconsider an entire structure of our system, as can be seen in Figure 5.6. In frame-based systems, inheritance means code reuse, and the job of the knowledge engineer is to group similar classes together and reuse common code. The most important advantage of inheritance is the conceptual simplification, which is achieved by reducing the number of independent and specific features in the expert system. Are there any disadvantages? As is so often the case, much of the appealing simplicity of ideas behind the frame-based systems has been lost in the implementation stage. Brockman and Levesque 1985 argue that if we allow unrestrained overriding of inherited properties, it may become impossible to represent either definitive statements, such as, all squares are equilateral rectangles, or contingent universal conditions, such as, all the squares on Casimir Malevich's paintings are either black, red or white. In general, frame-based systems cannot distinguish between essential properties, those that an instance must have in order to be considered a member of a class, and accidental properties, those that all the instances of a class just happen to have. Instances inherit all typical properties, and because those properties can be overridden anywhere in the frame hierarchy, it may become impossible to construct composite concepts when using multiple inheritance. Inheritance in frame-based systems. 141. Figure 5.6 Multiple inheritance. This appears to undermine the whole idea of the frame knowledge representation. However, frames offer us a powerful tool for combining declarative and procedural knowledge, although they leave the knowledge engineer with difficult decisions to make about the hierarchical structure of the system and its inheritance paths. Appeals to so-called typical properties do not always work, because they may lead us to unexpected results. Thus, although we may use frames to represent the fact that an ostrich is a bird, it is certainly not a typical bird, in the way that an eagle is. Frame-based expert systems, such as Level 5 Object, provide no safeguards against creating incoherent structures. However, 142. Frame-based expert systems. Such systems do provide data and control structures that are more suited for the simulation of human reasoning than any conventional programming language. Furthermore, to combine the power of both techniques of knowledge representation rules and frames, modern frame-based expert systems use rules for interaction with information contained in the frames. 5.4 Methods and daemons. As we have already discussed, frames provide us with a structural and concise means of organizing knowledge. However, we expect an expert system to act as an intelligent assistant. We require it not only to store the knowledge but also to validate and manipulate this knowledge. To add actions to our frames, we need methods and daemons. What are methods and daemons? A method is a procedure associated with a frame attribute that is executed whenever requested. Durkin, 1994. In Level 5 Object, for example, a method is represented by a series of commands similar to a macro in a spreadsheet program. We write a method for a specific attribute to determine the attribute's value or execute a series of actions when the attribute's value changes. Most frame-based expert systems use two types of methods, when changed and WHENNEEDED. In general, a daemon has an if-then structure. It is executed whenever an attribute in the daemon's if statement changes its value. In this sense, daemons and methods are very similar, and the two terms are often used as synonyms. However, methods are more appropriate if we need to write complex procedures. Daemons, on the other hand, are usually limited to if-then statements. Let us now examine a when-changed method. A when-changed method is executed immediately when the value of its attribute changes. To understand how when-changed methods work, we consider a simple problem adapted from Sterling and Shapiro, 1994. We will use the expert system shell Level 5 Object, which offers features commonly found in most frame-based expert systems and object-oriented programming languages. The expert system is required to assist a loan officer in evaluating credit requests from small business ventures. A credit request is to be classified into one of three categories: give credit, deny credit, or consult a superior, based on the collateral and financial rating of the business and the bank's expected yield from the loan. When a loan officer provides a qualitative rating of the expected yield from the loan, the expert system compares the business collateral with the amount of credit requested, evaluates a financial rating based on a weighted sum of the business's net worth to assets, last year's sales growth, gross profit on sales and short-term debt to sales, and finally determines a category for the credit request. The expert system is expected to provide details of any business venture and evaluate the credit request for the business selected by the user, a loan officer. Methods and daemons. 143. Figure 5.7 Input display for the request selection. The input display for the request selection is shown in Figure 5.7. The data on the display change depending on which business is selected. The class action data, shown in Figure 5.8, is used to control the input display. The user can move to the next, previous, first or last request in the list of requests and examine the business data. The when-changed methods here allow us to advance through a list of requests. Note that all attributes in Figure 5.8 are declared as simple s. Simple attributes can assume either a value of true or false. Let us examine the when-changed method attached to the attribute goTo next. How does this method work? In Level 5 Object, any method begins with the reserved words when-changed or WHENNEEDED, which are followed by the reserved word begin and a series of commands to be executed. The reserved word end completes a method. To refer to a particular attribute in a method, we must specify the class name as well as the attribute name. The syntax is less than attribute name greater than of less than class name greater than. For example, the statement goToNext of action data refers to the attribute goToNext of the class action data. The next push button on the input display is attached to the attribute goToNext of the class action data. When we select this push button at runtime, the attribute goToNext receives a value of true, causing the whenChanged method attached to it to execute. The method's first command assigns the 144 frame-based expert systems. Figure 5.8 the class action data and whenChanged methods. Number of the currently selected instance of the class request to the attribute current request number, which is used as a reference point. The find command uses the number stored in current request number to determine the next request in the list. The limit 1 command tells level 5 object to find the first instance that matches the search condition. The where clause. Where request number of request greater than current request number. Locates the first instance of the class request whose number is greater than the value of current request number. The request list is maintained in increasing order to ensure that the proper instance is retrieved. If, for example, the current instance number is 6, then the find command will retrieve the instance with the number 7. Let us now consider the class request and its instances represented in Figure 5.9. The instances, request1 and request2, have the same attributes as the class request, but each instance holds specific values for these attributes. To show the attribute values on the input display, we have to create value boxes, display items that show data, and then attach these value boxes to the appropriate attributes. When we run the application, the value boxes show the attribute. Methods and daemons. 145. Figure 5.9 class request and its instances. 146. Frame-based expert systems. Values of the currently selected instance of the class request and whenChanged methods cause actions to occur. When or when needed methods to be used. In many applications, an attribute is assigned to some initial or default value. However, in some applications, a when needed method can be used to obtain the attribute value only when it is needed. In other words, a when needed method is executed when information associated with a particular attribute is needed for solving the problem, but the attribute value is undetermined. We will return to this method when we discuss rules for our credit evaluation example. 5.5 Interaction of frames and rules. Most frame-based expert systems allow us to use a set of rules to evaluate information contained in frames. Are there any specific differences between rules used in rule-based expert systems and those used in frame-based systems? Every rule has an if-then structure, and every rule relates given information or facts in its if part to some action in its then part. In this sense, there are no differences between rules used in a rule-based expert system and those used in a frame-based system. However, in frame-based systems, rules often use pattern matching clauses. These clauses contain variables that are used for finding matching conditions among all instance frames. How does an inference engine work in a frame-based system? What causes rules to fire? Let us again compare rule-based and frame-based expert systems. In a rule-based expert system, the inference engine links the rules contained in the knowledge base with data given in the database. When the goal is set up, or in other words when an expert system receives the instruction to determine a value for the specified object, the inference engine searches the knowledge base to find a rule that has the goal in its consequent then part. If such a rule is found and its antecedent if part matches data in the database, the rule is fired and the specified object, the goal, obtains its value. If no rules are found that can derive a value for the goal, the system queries the user to supply that value. In a frame-based system, the inference engine also searches for the goal, or in other terms for the specified attribute, until its value is obtained. In a rule-based expert system, the goal is defined for the rule base. In a frame-based system, rules play an auxiliary role. Frames represent here a major source of knowledge, and both methods and daemons are used to add actions to the frames. Thus, we might expect that the goal in a frame-based system can be established either in a method or in a daemon. Let us return to our credit evaluation example. Interaction of frames and rules. 147. Figure 5.10 The credit evaluation class, whenChanged and when needed methods. Suppose we want to evaluate the credit request selected by the user. The expert system is expected to begin the evaluation when the user clicks the Evaluate Credit push button on the input display. This push button is attached to the attribute Evaluate Credit of the class Credit Evaluation shown in Figure 5.10. The attribute Evaluate Credit has the When Changed method attached to it, and when we select the Evaluate Credit push button at runtime, the attribute Evaluate Credit receives a new value, a value of true. This change causes the When Changed method to execute. The pursue command tells Level 5 object to establish the value of the attribute evaluation of the class Credit Evaluation. A simple set of rules shown in Figure 5.11 is used to determine the attribute's value. How does the inference engine work here? Based on the goal, evaluation of credit evaluation, the inference engine finds those rules whose consequence contain the goal of interest and examines them one at a time in the order in which they appear in the rule base. That is, the inference engine starts with Rule 9 and attempts to establish whether the attribute evaluation receives the give credit value. This is done by examining the validity of each antecedent of the rule. In other words, the inference engine attempts to determine first whether the attribute collateral has the value of excellent, and next whether the attribute financial rating is excellent. To determine whether collateral of credit evaluation is excellent, the inference engine examines Rule 1 and Rule 2, and to determine whether financial rating of credit evaluation is excellent, it looks at Rule 8. If all of the rule antecedents are valid, then the inference engine will conclude that evaluation of credit evaluation is give credit. However, if any of the antecedents are invalid, then the conclusion is invalid. In this case, the inference engine will examine the next rule, Rule 10, which can establish a value for the attribute evaluation. 148. Frame-based expert systems. Figure 5.11 Rules for credit evaluation. What happens if collateral of credit evaluation is good? Based on the set of rules provided for credit evaluation, the inference engine cannot establish the value of the attribute evaluation in some cases. This is especially true when the collateral is good and the financial rating of the business is excellent or good. In fact, if we have a look at Figure 5.10, we find BuySmart, a frame-based expert system. 149. Cases that are not represented in the rule base. However, it is not necessary always to rely on a set of rules. We can use the when needed method to establish the attribute value. The when needed method shown in Figure 5.10 is attached to the attribute evaluation. The inference engine executes this method when it needs to determine the value of evaluation. When the when needed method is executed, the attribute evaluation receives the value console to superior. How does the inference engine know where, and in what order, to obtain the value of an attribute? In our case, if the when needed method were executed first, the attribute evaluation would always receive the value console to superior, and no rules would ever be fired. Thus, the inference engine has to obtain the value from the when needed method only if it has not been determined from the rule base. In other words, the search order for the attribute value has to be determined first. It can be done, for example, by means of the search order facet attached to an attribute that tells the inference engine where, and in what order, to obtain the value of this attribute. In Level 5 object, a search order can be specified for every attribute, and in our credit evaluation example, we set the search order for the evaluation value to rules, when needed. It makes certain that the inference engine starts the search from the rule base. 5.6 BuySmart, a frame-based expert system. To illustrate the ideas discussed above, we consider a simple frame-based expert system, BuySmart, which advises property buyers. We will review the main steps in developing frame-based systems, and show how to use methods and daemons to bring frames to life. To aid us in this effort, we will use the Level 5 Object Expert System shell. Are there any differences between the main steps in building a rule-based expert system and a frame-based one? The basic steps are essentially the same. First, the knowledge engineer needs to obtain a general understanding of the problem and the overall knowledge structure. He or she then decides which expert system tool to use for developing a prototype system. Then the knowledge engineer actually creates the knowledge base and tests it by running a number of consultations. And finally, the expert system is expanded, tested and revised until it does what the user wants it to do. The principal difference between the design of a rule-based expert system and a frame-based one lies in how the knowledge is viewed and represented in the system. In a rule-based system, a set of rules represents the domain knowledge useful for problem solving. Each rule captures some heuristic of the problem, and each new rule adds some new knowledge and thus makes the system smarter. The rule-based system can easily be modified by changing, adding or subtracting rules. 150. Frame-based expert systems. In a frame-based system, the problem is viewed in a different manner. Here, the overall hierarchical structure of the knowledge is decided first. Classes and their attributes are identified, and hierarchical relationships between frames are established. The architecture of a frame-based system should not only provide a natural description of the problem, but also allow us to add actions to the frames through methods and daemons. The development of a frame-based system typically involves the following steps. 1. Specify the problem and define the scope of the system. 2. Determine classes and their attributes. 3. Define instances. 4. Design displays. 5. Define when changed and we needed methods and daemons. 6. Define roles. 7. Evaluate and expand the system. Step 1. Specify the problem and define the scope of the system. In our Buy Smart example, we start by collecting some information about properties for sale in our region. We can identify relevant details such as the property type, location, number of bedrooms and bathrooms, and of course, the property price. We also should provide a short description and a nice photo for each property. We expect that some of the properties will be sold and new properties will appear on the market. Thus, we need to build a database that can be easily modified and then accessed from the expert system. Level 5 object allows us to access, modify, delete and perform other actions on data within a DBASE3 database. Can we store descriptions and pictures of the properties within a database? Property descriptions and pictures should be stored separately, descriptions as text files.txt, and pictures as bitmap files.bmp. If we then set up a display that includes a text box and a picture box, we will be able to view a property description and its picture in this display by reading the text file into the text box and the bitmap file into the picture box, respectively. Now we create an external database file, house.dbf, using DBASE3 or Microsoft Excel, as shown in Table 5.1. The next step is to list all possible queries we might think of. What is the maximum amount you want to spend on a property? What type of property do you prefer? Which suburb would you like to live in? How many bedrooms do you want? How many bathrooms do you want? Once the queries are answered, the expert system is expected to provide a list of suitable properties. Step 2. Determine classes and their attributes. Here, we identify the problems principal classes. We begin with the general or conceptual type of classes. For example, we can talk about the concept of a property and describe general features that are common to most properties. We can characterize each property by its location, price, type, number of bedrooms and bathrooms, construction, picture and description. We also need to present contact details of the property, such as its address or phone number. Thus, the class table 5.1 the property database house.dbf area suburb price type bedrooms central suburbs Newtown 164,000 house 3 central suburbs Taruna 150,000 house 3 southern suburbs Kingston 225,000 townhouse 4 central suburbs North Hobart 127,000 house 3 northern suburbs West Muna 89,500 unit 2 central suburbs Taruna 110,000 house 3 central suburbs Lena Valley 145,000 house 3 eastern shore Old Beach 79,500 unit 2 central suburbs South Hobart 140,000 house 3 central suburbs South Hobart 115,000 house 3 eastern shore Cambridge 94,500 unit 2 northern suburbs Glenorchy 228,000 townhouse 4. Bathrooms construction phone picked file text file 1 weatherboard 03 62264212 house 01 BMP house 01.txt 1 brick 03 62261416 house 02 BMP house 02.txt 2 brick 03 62294200 house 03 BMP house 03.txt 1 brick 03 62268620 house 04 BMP house 04.txt 1 weatherboard 03 62254666 house 05 BMP house 05.txt 1 brick 03 62295316 house 06 BMP house 06.txt 1 brick 03 62782317 house 07 BMP house 07.txt 1 brick 03 62497298 house 08 BMP house 08.txt 1 brick 03 62285460 house 09 BMP house 09.txt 1 brick 03 62278937 house 10 BMP House 10.txt 1 brick 03 62481459 House 11. BMP House 11.txt 2 Weatherboard 03 62716347 House 12. BMP House 12.txt 151 BUYSMART, A-frame-based expert system. 152. Frame-based expert systems. Figure 5.12 Class property and its instances. Property can be presented as shown in Figure 5.12. Note that we added the attribute instance number as well. This attribute does not characterize the property but will assist Level 5 object in accessing the external database. Step 3. Define instances. Once we determine the class frame property, we can easily create its instances by using data stored in the DBASE3 database. For most frame-based expert systems like Level 5 object, this task requires us to buy Smart, a frame-based expert system. 153. Tell the system that we want a new instance to be created. For example, to create a new instance of the class property, we can use the following code. Make property with area equals area of DB3 house 1 with suburb equals suburb of DB3 house 1 with price equals price of DB3 house 1 with type equals type of DB3 house 1 with bedrooms equals bedrooms of DB3 house 1 with bathrooms equals bathrooms of DB3 house 1 with construction equals construct of DB3 house 1 with phone equals phone of DB3 house 1 with pict file equals pict file of DB3 house 1 with text file equals text file of DB3 house 1 with instance number equals current instance number. Here, the class DB3 house 1 is used to represent the structure of the external database file house.dbf. Each row in the property database, shown in table 5.1, represents an instance of the class property, and each column represents an attribute. A newly created instance frame receives the values of the current record of the database. Figure 5.12 shows instances that are created from the external database. These instances are linked to the class property, and they inherit all attributes of this class. Step 4. Design displays. Once the principal classes and their attributes are determined, we can design major displays for our application. We need the application title display to present some general information to the user at the beginning of each application. This display may consist of the application title, general description of the problem, representative graphics and also copyright information. An example of the application title display is shown in Figure 5.13. The next display we can think of is the query display. This display should allow us to indicate our preferences by answering the queries presented by the expert system. The query display may look like a display shown in Figure 5.14. Here, the user is asked to select the most important things he or she is looking for in the property. Based on these selections, the expert system will then come up with a complete list of suitable properties. And finally, we should design the property information display. This display has to provide us with the list of suitable properties, an opportunity to move to the next, previous, first or last property in the list, and also a chance to look at the property picture and its description. Such a display may look like the one presented in Figure 5.15. Note that the picture box and text box are included in the display. 154. Frame-based expert systems. Figure 5.13 The application title display. Figure 5.14 The query display. Buy Smart, a frame-based expert system. 155. Figure 5.15 The property information display. How are these displays linked? Level 5 object allows us to link these displays by attaching the Continue push button on the application title display to the query display, and the Search push button on the query display to the property information display. When we run the application, clicking on either the Continue or Search push button will cause a new display to appear. Now we have to bring these displays to life. Step 5. Define when changed and when needed methods and daemons. At this point, we have already created the problem principal classes and their attributes. We also determined the class instances, and established the mechanism for creating these instances from the external database. And finally, we designed static displays for presenting information to the user. We must now develop a way to bring our application to life. There are two ways to accomplish this task. The first one relies on when changed and when needed methods and daemons. The second approach involves pattern matching rules. In frame-based systems, we always first consider an application of methods and daemons. What we need now is to decide when to create instances of the class property. There are two possible solutions. The first one is to create all instances at once when the user clicks on the Continue push button on the application title display, and then remove inappropriate instances step by step based on the user's preferences when he or she selects push buttons on the query display. The second approach is to create only relevant instances after the user has made all selections on the query display. This approach, 156, Frame-based expert systems, illuminates the necessity to remove inappropriate instances of the class property, but may add to the complexity of the system's design. In our design here, we give preference to the first approach. It will provide us with an opportunity to use daemons instead of rules. However, you could use the other approach. Let us now create an additional class, the class action data, shown in Figure 5.16. The when_changed method attached to the attribute load properties allows us to create all instances of the class property. How do we make this method work? To make it work, we attach the Continue push button on the application title display to the attribute load properties. Now when we select this push button at runtime, the attribute load properties receives a value of true, causing its when_changed method to execute and create all instances of the class property. The number of the instances created equals the number of records in the external database. Now the query display appears. Remember that we attach the Continue push button of the application title display to the query display, and the user is required to choose the most desirable features of the property by selecting appropriate push buttons. Each push button here is associated with a daemon that removes inappropriate instances of the class properties. A set of daemons is shown in Figure 5.17. How do daemons work here? A daemon does not go into action until something happens. In our application, it means that a daemon is fired only if the user selects a corresponding push button. Figure 5.16 The when_changed method of the attribute load properties. By Smart, a frame-based expert system. 157. Figure 5.17 Daemons for the query display. Let us consider, for example, daemon 1 associated with the Central Suburbs push button. When the user clicks on the Central Suburbs push button on the query display, daemon 1 is fired. The first command of the daemon consequent tells level 5 object to find the class property. The where clause. Where area of property less than greater than, Central Suburbs. Finds all instances of the class property that do not match the user selection. It looks for any instance where the value of the attribute. 158. Frame-based expert systems. Area is not equal to Central Suburbs. Then, the forget current command removes the current instance of the class property from the application. Once the property features are selected, the user clicks on the search push button on the query display to obtain a list of properties with these features. This list will appear on the property information display. Recall that the search push button is attached to the property information display. Can we view pictures and descriptions of the properties? Let us first create two more attributes, load instance number and goToFirst property, for the class action data as shown in Figure 5.18. Let us also attach the search push button on the query display to the attribute load instance number. Now when we click on the search push button at runtime, the attribute load instance number will receive a value of true, causing its when_changed method to execute. This method determines the total number of instances left in the class property. It also assigns the attribute goToFirst property a value of true, subsequently causing its when_changed method to execute. The method attached to the attribute goToFirst property ensures that we are always positioned at the first property when we enter the property information display. It also loads the value of the attribute pict file into the display's picture box and the value of text file into the text box. As a result, we can see the property picture and its description is shown in Figure 5.15. Figure 5.18 The when_changed methods of the attributes load instance number and goToFirst property. By Smart, a frame-based expert system. 159. Step 6. Define rules. When we design a frame-based expert system, one of the most important and difficult decisions is whether to use rules or manage with methods and daemons instead. This decision is usually based on the personal preferences of the designer. In our application, we use methods and daemons because they offer us a powerful but simple way of representing procedures. On the other hand, in the credit evaluation example considered earlier, we applied a set of rules. In general, however, rules are not effective at dealing with procedural knowledge. Step 7. Evaluate and expand the system. We have now completed the initial design of our BI Smart Expert system. The next task is to evaluate it. We want to make sure that the system's performance meets our expectations. In other words, we want to run a test case. 1. To begin the test, we click on the Continue push button on the application title display. The attribute load properties of the class action data receives a value of true. The when changed method attached to load properties is executed, and all instances of the class property are created. 2. The query display appears, and we make our selections, for example, Central Suburbs Daemon 1. If selected of Central Suburbs push button then find property. Where area of property less than greater than, Central Suburbs, when found. Forget current property find end. House Daemon 5. If selected of House push button then find property. Where type of property less than greater than, House, when found. Forget current property find end. 3 bedrooms. Daemon 10. If selected of 3 bedroom push button then find property. Where bedrooms of property less than greater than 3 when found. Forget current property find end. 160. Frame-based expert systems. Own bathroom. Daemon 12. If selected of 1 bathroom push button then find property. Where bathrooms of property less than greater than 1 when found. Forget current property find end. $200,000. Daemon 18. If selected of $200,000 push button then find property. Where price of property greater than $200,000 when found. Forget current property find end. The daemons remove those property instances whose features do not match our selections. 3. Now we click on the search push button. The attribute load instance number of the class action data receives a value of true. The when changed method attached to load instance number is executed. It determines the number of instances left in the class property, and also assigns the attribute goToFirst property a value of true. Now the when changed method attached to goToFirst property is executed. It finds the first property instance, and assigns the attribute filename of the property picture box a value of house01.bmp, and the attribute filename of the property text box a value of house01.txt. Recall that both the property picture box and property text box have been created on the property information display. 4. The property information display appears. In the example shown in Figure 5.15, we can examine 12 properties that satisfy our requirements. Note that we are positioned at the first property in the property list, the property picture appears in the picture box and the property description in the text box. However, we cannot move to the next, previous or last property in the property list by using the push buttons assigned on the display. To make them functional, we need to create additional attributes in the class action data, and then attach when changed methods as shown in Figure 5.19. Now the BI Smart Expert system is ready for expansion, and we can add new properties to the external database. Summary. 161. Figure 5.19 The when changed methods of the attributes goToNext property, goToPrevious property and goToLast property. 5.7 Summary. In this chapter, we presented an overview of frame-based expert systems. We considered the concept of a frame and discussed how to use frames for knowledge representation. We found that inheritance is an essential feature of the frame-based systems. We examined the application of methods, daemons and rules. Finally, we considered the development of a frame-based expert system through an example. 162. Frame-based expert systems. The most important lessons learned in this chapter are: A frame is a data structure with typical knowledge about a particular object or concept. Frames are used to represent knowledge in a frame-based expert system. A frame contains knowledge of a given object, including its name and a set of attributes also called slots. Name, weight, height and age are attributes of the frame person. Model, processor, memory and price are attributes of the frame computer. Attributes are used to store values. An attribute may contain a default value or a pointer to another frame, set of rules or procedure by which the attribute value is obtained. Frame-based systems can also extend the attribute value structure through the application of facets. Facets are used to establish the attribute value, control end-user queries, and tell the inference engine how to process the attribute. A frame may refer to a group of similar objects, or to a particular object. A class frame describes a group of objects with common attributes. Animal, person, car and computer are all class frames. An instance frame describes a particular object. Frame-based systems support class inheritance, i.e. the process by which all characteristics of a class frame are assumed by the instance frame. The fundamental idea of inheritance is that attributes of the class frame represent things that are typically true for all objects in the class, but slots in the instance frames are filled with actual data that is unique for each instance. A frame can inherit attributes from more than one parent through multiple parent inheritance. Frames communicate with each other by methods and daemons. A method is a procedure associated with a frame attribute. It is executed whenever requested. Most frame-based expert systems use two types of methods, when-changed and whenneeded. The when-changed method is executed when new information is placed in the slot, and the when-needed method is executed when information is needed for solving the problem but the slot value is unspecified. Daemons are similar to methods, and the terms are often used as synonyms. However, methods are more appropriate if we need to write complex procedures. Daemons, on the other hand, are usually limited to if-then statements. In frame-based expert systems, rules often use pattern matching clauses. These clauses contain variables that are used for locating matching conditions among all instance frames. 7. Evolutionary computation, in which we consider the field of evolutionary computation, including genetic algorithms, evolution strategies and genetic programming, and their applications to machine learning. 7.1 Introduction, or can evolution be intelligent? Intelligence can be defined as the capability of a system to adapt its behavior to an ever-changing environment. According to Alan Turing, 1950, the form or appearance of a system is irrelevant to its intelligence. However, from our everyday experience we know that evidences of intelligent behavior are easily observed in humans. But we are products of evolution, and thus by modeling the process of evolution, we might expect to create intelligent behavior. Evolutionary computation simulates evolution on a computer. The result of such a simulation is a series of optimization algorithms, usually based on a simple set of rules. Optimization iteratively improves the quality of solutions until an optimal, or at least feasible, solution is found. But is evolution really intelligent? We can consider the behavior of an individual organism as an inductive inference about some yet unknown aspects of its environment. Fogel et al., 1966. Then if, over successive generations, the organism survives, we can say that this organism is capable of learning to predict changes in its environment. Evolution is a tortuously slow process from the human perspective, but the simulation of evolution on a computer does not take billions of years. The evolutionary approach to machine learning is based on computational models of natural selection and genetics. We call them evolutionary computation, an umbrella term that combines genetic algorithms, evolution strategies and genetic programming. All these techniques simulate evolution by using the processes of selection, mutation and reproduction. 7.2 Simulation of natural evolution. On the 1st of July 1858, Charles Darwin presented his theory of evolution before the Linnean Society of London. This day marks the beginning of a revolution in 220. Evolutionary computation. Biology. Darwin's classical theory of evolution, together with Weismann's theory of natural selection and Mendel's concept of genetics, now represent the neo-Darwinian paradigm. Keaton, 1980, Meyer, 1988. Neo-Darwinism is based on processes of reproduction, mutation, competition and selection. The power to reproduce appears to be an essential property of life. The power to mutate is also guaranteed in any living organism that reproduces itself in a continuously changing environment. Processes of competition and selection normally take place in the natural world, where expanding populations of different species are limited by a finite space. If the process of evolution is to be emulated on a computer, what is being optimized by evolution in natural life? Evolution can be seen as a process leading to the maintenance or increase of a population's ability to survive and reproduce in a specific environment. Hartle and Clark, 1989. This ability is called evolutionary fitness. Although fitness cannot be measured directly, it can be estimated on the basis of the ecology and functional morphology of the organism in its environment. Hoffman, 1989. Evolutionary fitness can also be viewed as a measure of the organism's ability to anticipate changes in its environment. Atmar, 1994. Thus, the fitness, or the quantitative measure of the ability to predict environmental changes and respond adequately, can be considered as the quality that is being optimized in natural life. To illustrate fitness, we can use the concept of adaptive topology, Wright, 1932. We can represent a given environment by a landscape where each peak corresponds to the optimized fitness of a species. As evolution takes place, each species of a given population moves up the slopes of the landscape towards the peaks. Environmental conditions change over time, and thus the species have to continuously adjust their routes. As a result, only the fittest can reach the peaks. Adaptive topology is a continuous function. It simulates the fact that the environment, or natural topology, is not static. The shape of the topology changes over time, and all species continually undergo selection. The goal of evolution is to generate a population of individuals with increasing fitness. But how is a population with increasing fitness generated? Michalowicz 1996 suggests a simple explanation based on a population of rabbits. Some rabbits are faster than others, and we may say that these rabbits possess superior fitness because they have a greater chance of avoiding foxes, surviving and then breeding. Of course, some of the slower rabbits may survive too. As a result, some slow rabbits breed with fast rabbits, some fast with other fast rabbits, and some slow rabbits with other slow rabbits. In other words, the breeding generates a mixture of rabbit genes. If two parents have superior fitness, there is a good chance that a combination of their genes will produce an offspring with even higher fitness. Over time, the entire population of rabbits becomes faster to meet their environmental challenges in the face of foxes. However, environmental conditions could change in favor of, say, fat but smart rabbits. To optimize survival, the genetic structure of the rabbit population will change accordingly. At the same time, faster and smarter rabbits encourage the breeding. Simulation of natural evolution. 221. Of faster and smarter foxes. Natural evolution is a continuous, never-ending process. Can we simulate the process of natural evolution in a computer? Several different methods of evolutionary computation are now known. They all simulate natural evolution, generally by creating a population of individuals, evaluating their fitness, generating a new population through genetic operations, and repeating this process a number of times. However, there are different ways of performing evolutionary computation. We will start with genetic algorithms GAS, as most of the other evolutionary algorithms can be viewed as variations of GAS. In the early 1970s, John Holland, one of the founders of evolutionary computation, introduced the concept of genetic algorithms. Holland, 1975. His aim was to make computers do what nature does. As a computer scientist, Holland was concerned with algorithms that manipulate strings of binary digits. He viewed these algorithms as an abstract form of natural evolution. Holland's GA can be represented by a sequence of procedural steps for moving from one population of artificial chromosomes to a new population. It uses natural selection and genetics-inspired techniques known as crossover and mutation. Each chromosome consists of a number of genes, and each gene is represented by 0 or 1, as shown in Figure 7.1. Nature has an ability to adapt and learn without being told what to do. In other words, nature finds good chromosomes blindly. GAS do the same. Two mechanisms link a GA to the problem it is solving: encoding and evaluation. In Holland's work, encoding is carried out by representing chromosomes as strings of ones and zeros. Although many other types of encoding techniques have been invented, Davis, 1991, no one type works best for all problems. We will use bit strings as the most popular technique. An evaluation function is used to measure the chromosome's performance, or fitness, for the problem to be solved. An evaluation function in GAS plays the same role the environment plays in natural evolution. The GA uses a measure of fitness of individual chromosomes to carry out reproduction. As reproduction takes place, the crossover operator exchanges parts of two single chromosomes, and the mutation operator changes the gene value in some randomly chosen location of the chromosome. As a result, after a number of successive reproductions, the less fit chromosomes become extinct, while those best able to survive gradually come to dominate the population. It is a simple approach, yet even crude reproduction mechanisms display highly complex behavior and are capable of solving some difficult problems. Let us now discuss genetic algorithms in more detail. Figure 7.1, a 16-bit binary string of an artificial chromosome. 222. Evolutionary computation. 7.3 Genetic algorithms. We start with a definition. Genetic algorithms are a class of stochastic search algorithms based on biological evolution. Given a clearly defined problem to be solved in a binary string representation for candidate solutions, a basic GA can be represented as in Figure 7.2. A GA applies the following major steps: Davis, 1991, Mitchell, 1996. Step 1. Represent the problem variable domain as a chromosome of a fixed length. Choose the size of a chromosome population n, the crossover probability Pc and the mutation probability Pm. Step 2. Define a fitness function to measure the performance, or fitness, of an individual chromosome in the problem domain. The fitness function establishes the basis for selecting chromosomes that will be mated during reproduction. Step 3. Randomly generate an initial population of chromosomes of size n. x1, x2, xn. Step 4. Calculate the fitness of each individual chromosome. fx1, fx2, fxn. Step 5. Select a pair of chromosomes for mating from the current population. Parent chromosomes are selected with a probability related to their fitness. Highly fit chromosomes have a higher probability of being selected for mating than less fit chromosomes. Step 6. Create a pair of offspring chromosomes by applying the genetic operators crossover and mutation. Step 7. Place the created offspring chromosomes in the new population. Step 8. Repeat step 5 until the size of the new chromosome population becomes equal to the size of the initial population, n. Step 9. Replace the initial parent chromosome population with the new offspring population. Step 10. Go to step 4, and repeat the process until the termination criterion is satisfied. As we see, a GA represents an iterative process. Each iteration is called a generation. A typical number of generations for a simple GA can range from 50 to over 500. Mitchell, 1996. The entire set of generations is called a run. At the end of a run, we expect to find one or more highly fit chromosomes. Genetic algorithms. 223. Figure 7.2a Basic genetic algorithm. Or any conventional termination criteria used in genetic algorithms. Because GAs use a stochastic search method, the fitness of a population may remain stable for a number of generations before a superior chromosome appears. This makes applying conventional termination criteria problematic. A common practice is to terminate a GA after a specified number of generations, and then examine the best chromosomes in the population. If no satisfactory solution is found, the GIS restarted. A simple example will help us to understand how AGA works. Let us find the maximum value of the function 15x(x2) where a parameter x varies between 0 and 15. For simplicity, we may assume that x takes only integer values. Thus, chromosomes can be built with only 4 GANs. Integer binary code, integer binary code, integer binary code 10001601101111011 20010701111211100 300118100131101 40100910011411110 50101101010151111. Suppose that the size of the chromosome population is 6, the crossover probability Pc equals 0.7, and the mutation probability type equals 0.001. The value chosen for pecan mere fairly typicalingas. The fitness function in our example is defined by fx1 quarter 15xx2. The GA creates an initial population of chromosomes by filling 6 4-bit strings with randomly generate ones and zeros. The initial population might look like that shown in table 7.1. That chromosome's initial locations and fitness function are illustrated in figure 7.3. A real practical problem would typically have a population of thousands of chromosomes. The next step is to calculate the fitness of each individual chromosome. The results are also shown in table 7.1. The average fitness of the initial population is 36. In order to improve it, the initial population is modified by using selection, crossover and mutation, the genetic operators. In natural selection, only the fit test species can survive, breed, and thereby pass their genes on to the next generation. G is a similar approach, but table 7.1 the initial randomly generated population of chromosomes chromosome label chromosome string decoded integer chromosome fitness ratio Percent by 11,100,123,616.5 by 2,010,044,420.2 by 300,011,146.4 by 4,111,014,146.4 by 5,011,175,625.7 x 6,100,195,424.8 EVOLUTIONARYCOMPUTATION 224. Genetic algorithms. 225. Figure 7.3 The fitness function and chromosome locations. A chromosome initial locations, B chromosome final locations. Unlike nature, the size of the chromosome population remains unchanged from one generation to the next. How can we maintain the size of the population constant, and at the same time improve its average fitness? The last column in Table 7.1 shows the ratio of the individual chromosomes' fitness to the population's total fitness. This ratio determines the chromosome's chance of being selected for mating. Thus, the chromosomes X5 and X6 stand a fair chance, while the chromosomes X3 and X4 have a very low probability of being selected. As a result, the chromosome's average fitness improves from one generation to the next. One of the most commonly used chromosome selection techniques is the roulette wheel selection. Goldberg, 1989, Davis, 1991. Figure 7.4 illustrates the roulette wheel for our example. As you can see, each chromosome is given a slice of a circular roulette wheel. The area of the slice within the wheel is equal to the chromosome fitness ratio, see Table 7.1. For instance, the chromosomes X5 and X6, the most fit chromosomes, occupy the largest areas, whereas the chromosomes X3 and X4, the least fit, have much smaller segments in the roulette wheel. To select a chromosome for mating, a random number is generated in the interval 1/2 0, 100, and the chromosome whose segment spans the random number is selected. It is like spinning a roulette wheel where each chromosome has a segment on the wheel proportional to its fitness. The roulette wheel is spun, and Figure 7.4 Roulette wheel selection. 226. Evolutionary computation. When the arrow comes to rest on one of the segments, the corresponding chromosome is selected. In our example, we have an initial population of 6 chromosomes. Thus, to establish the same population in the next generation, the roulette wheel would be spun 6 times. The first 2 spins might select chromosomes X6 and X2 to become parents, the second pair of spins might choose chromosomes X1 and X5, and the last 2 spins might select chromosomes X2 and X5. Once a pair of parent chromosomes is selected, the crossover operator is applied. How does the crossover operator work? First, the crossover operator randomly chooses a crossover point where 2 parent chromosomes break, and then exchanges the chromosome parts after that point. As a result, 2 new offspring are created. For example, the chromosomes X6 and X2 could be crossed over after the second gene in each to produce the 2 offspring, as shown in Figure 7.5. If a pair of chromosomes does not cross over, then chromosome cloning takes place, and the offspring are created as exact copies of each parent. For example, the parent chromosomes X2 and X5 may not cross over. Instead, they create the offspring that are their exact copies, as shown in Figure 7.5. A value of 0.7 for the crossover probability generally produces good results. After selection and crossover, the average fitness of the chromosome population has improved and gone from 36 to 42. What does mutation represent? Mutation, which is rare in nature, represents a change in the gene. It may lead to a significant improvement in fitness, but more often has rather harmful results. So why use mutation at all? Holland introduced mutation as a background operator. Holland, 1975. Its role is to provide a guarantee that the search algorithm is not trapped on a local optimum. The sequence of selection and crossover operations may stagnate at any homogeneous set of solutions. Under such conditions, all chromosomes are identical, and thus the average fitness of the population cannot be improved. However, the solution might appear to become optimal, or rather locally optimal, only because the search algorithm is not able to proceed any further. Mutation is equivalent to a random search, and aids us in avoiding loss of genetic diversity. How does the mutation operator work? The mutation operator flips a randomly selected gene in a chromosome. For example, the chromosome X10 might be mutated in its second gene, and the chromosome X2 in its third gene, as shown in Figure 7.5. Mutation can occur at any gene in a chromosome with some probability. The mutation probability is quite small in nature, and is kept quite low for gas, typically in the range between 0.001 and 0.01. Genetic algorithms assure the continuous improvement of the average fitness of the population, and after a number of generations, typically several hundred. Genetic algorithms. 227. Figure 7.5 The Gauss cycle. The population evolves to a near-optimal solution. In our example, the final population would consist of only chromosomes 0111 and the chromosome's final locations on the fitness function are illustrated in figure 7.3p. 1000. In this example, the problem has only one variable. It is easy to represent. But suppose it is desired to find the maximum of the peak function of two variables. Fx, y1 quarter 1x2 x2 y1 2x3 y3 x2 y2. Where parameters x and y vary between 3 and 3. The first step is to present the problem variables as a chromosome. In other words, we represent parameters x and y as a concatenated binary string, in which each parameter is represented by 8 binary bits. Then, we choose the size of the chromosome population, for instance 6, and randomly generate an initial population. The next step is to calculate the fitness of each chromosome. This is done in two stages. First, a chromosome is decoded by converting it into two real numbers, Zanda, in the interval between 3 and 3. Then the decoded values of fx and y substituted into the peak function, have is decoding then. First, a chromosome, that is a string of 16 bits, is partitioned into two 8-bit strings, and then the strings are reconverted from binary base 2 to decimal base 10, 10,000,1010 2 and a quarter 127 026 025 024 123 022 121 0201 quarter 138 10 and 0011 1011 2 and a quarter 027 026 125 124 123 022 121 120 and a quarter 59 10. Now the range of integers that can be handled be 8 bits. That is the range from 0 to 281, is mapped to the actual range of parameters Zanda, that is the range from 3 to 3, 6 2561 1 quarter 0, 0235294 to obtain the actual values of Zandi. We multiply their decimal values by 0.0235294 and subtract 3 from the results. By 1 quarter 138 100, 0235294 1 quarter 0. 2,470,588 and y1 quarter 59 100, 0235294 1 quarter 1, 6117647 10001010111111 FFL 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 ZFFL FFL 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 ZFFL FFL 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 XY1 quadrillion 101,111,011 EVOLUTIONARYCOMPUTATION 228. Genetic algorithms. 229. When necessary, we can also apply other decoding techniques, such as gray coding. Caruana and Schaefer, 1988. Using decoded values of x and y as inputs in the mathematical function, the GA calculates the fitness of each chromosome. To find the maximum of the peak function, we will use crossover with the probability equal to 0.7 and mutation with the probability equal to 0.001. As we mentioned earlier, a common practice in GAS is to specify the number of generations. Suppose the desired number of generations is 100. That is, the GA will create 100 generations of 6 chromosomes before stopping. Figure 7.6 shows the initial locations of the chromosomes on the surface and contour plot of the peak function. Each chromosome here is represented by a sphere. The initial population consists of randomly generated individuals that are dissimilar or heterogeneous. However, starting from the second generation, crossover begins to recombine features of the best chromosomes, and the population begins to converge on the peak containing the maximum, as shown in Figure 7.6b. From then until the final generation, the GA is searching around this peak with mutation, resulting in diversity. Figure 7.6c shows the final chromosome generation. However, the population has converged on a chromosome lying on a local maximum of the peak function. But we are looking for the global maximum, so can we pursue the search as for the optimal solution? The most serious problem in the use of GAS is concerned with the quality of the results, in particular whether or not an optimal solution is. Figure 7.6 chromosome locations on the surface and contour plot of the peak function. A. Initial population, B. First generation, C. Local maximum solution, D. Global maximum solution. 230. Evolutionary computation. Being reached. One way of providing some degree of insurance is to compare results obtained under different rates of mutation. Let us, for example, increase the mutation rate to 0.01 and rerun the GA. The population might now converge on the chromosomes shown in Figure 7.6d. However, to be sure of steady results we must increase the size of the chromosome population. Figure 7.7 performance graphs for 100 generations of 6 chromosomes, A. Local maximum solution and B. Global maximum solution of the peak function. Genetic algorithms. 231. A surface of a mathematical function of the sort given in Figure 7.6 is a convenient medium for displaying the GA's performance. However, fitness functions for real-world problems cannot be easily represented graphically. Instead, we can use performance graphs. What is a performance graph? Since genetic algorithms are stochastic, their performance usually varies from generation to generation. As a result, a curve showing the average performance of the entire population of chromosomes as well as a curve showing the performance of the best individual in the population is a useful way of examining the behavior of a GA over the chosen number of generations. Figures 7.7 A and B show plots of the best and average values of the fitness function across 100 generations. The x-axis of the performance graph indicates how many generations have been created and evaluated at the particular point in the run, and the y-axis displays the value of the fitness function at that point. The erratic behavior of the average performance curves is due to mutation. The mutation operator allows a GA to explore the landscape in a random manner. Mutation may lead to significant improvement in the population fitness, but more often decreases it. To ensure diversity and at the same time to reduce the harmful effects of mutation, we can increase the size of the chromosome population. Figure 7.8 shows performance graphs for 20 generations of 60 chromosomes. The best and average curves represented here are typical for GAS. As you can see, the average curve rises rapidly at the beginning of the run, but then as the population converges on the nearly optimal solution, it rises more slowly, and finally flattens at the end. Figure 7.8 performance graphs for 20 generations of 60 chromosomes. 7.4 Why genetic algorithms work. The GA techniques have a solid theoretical foundation. Holland, 1975, Goldberg, 1989, Rollins, 1991, Whitley, 1993. That foundation is based in the schema theorem. John Holland introduced the notation of schema. Holland, 1975, which came from the Greek word meaning form. Ashi Mesa set a bit strings of 1s, 0s and asterisks, where each asterisk can assume either value 1 or 0. The 1s and 0s represent the fixed positions of Ashima, while *isks represent wildcards. For example, the schema stands for a set of 4-bit strings. Each string in this set begins with 1 and ends with 0. The Z strings are called instances of the schema. What is the relationship between a schema and a chromosome? It is simple. A chromosome matches Ashima the fixed positions and schema match the corresponding positions in the chromosome. For example, the schema matches the following set of 4-bit chromosomes. Each chromosome here begins with 1 and ends with 0. The set chromosomes are said to be instances of the schema. The number of defined bits non-asterisks, an Ashima called the order. The schema, for example, has 2 defined bits, and T Hughes its order is 2. In short, genetic algorithms manipulate schemata, schemata the plural of the words schema, when they run. IFG is a technique that makes the probability of reproduction proportional to chromosome fitness. The The N according to the schema theorem Holland, 1975 we can predict the presence of a given schema in the next chromosome generation. In other words, we can describe the Gauss behavior in terms of the increase or decrease in the number of instances of a given schema. Goldberg, 1989. Let us assume a total a stone instance of the schema is present in the chromosome initial generation. Now let me bet the number of instances of the schema in the generation I, and caret ff high the average fitness of these instances. We want to calculate the number of instances in the next generation, μ1. As the probability of reproduction is proportional to chromosome fitness, we can easily calculate the expected number of offspring of a chromosome X in the next generation. 1010, 1110, 1100, 1010, 1000 evolutionary computation 232. 7. 1. 233. WHYGENETIC algorithms work. MXE 1 quarter. FXE. Caret. FI. Where FXE is the fitness of the chromosome X, and caret Phi is the average fitness of the chromosome initial generation I. Then, assuming that the chromosome X is an instance of the schema H, we obtain by 1 quarter me X by 1 quarter 1 FXE me 1 quarter caret FI. Since, by definition, by 1 quarter me X caret by 1 quarter 1 FXE FE 1 quarter me, we obtain caret me 1 quarter FE caret semicolon X2H 7 2 7 3 FI me. Thus, a schema with above average fitness will indeed tend to occur more frequently in the next generation of chromosomes, and a schema with below average fitness will tend to occur less frequently. How about effects caused by crossover and mutation? Crossover and mutation can both create and destroy instances of a schema. Here we will consider only destructive effects, that is effects that decrease the number of instances of the schema H. Let us first quantify the destruction caused by the crossover operator. The schema will survive after crossover if at least one of its offspring is also its instance. This is the case when crossover does not occur within the defining length of the schema. What is the defining length of a schema? The distance between the outermost defined bits of a schema is called defining length. For example, the defining length of 1011 of 0110 is 5 and of 10 is 3 is 7. If crossover takes place within the defining length, the schema H can be destroyed and offspring that are not instances of H can be created. Although the schema H will not be destroyed if two identical chromosomes cross over, even when crossover occurs within the defining length. 234. Evolutionary computation. Thus, the probability that the schema H will survive after crossover can be defined as PC H 1 quarter 1%, LD L1 semicolon 7 4, where PC is the crossover probability, and L and LD are, respectively, the length and the defining length of the schema H. It is clear that the probability of survival under crossover is higher for short schemata rather than for long ones. Now consider the destructive effects of mutation. Let PM be the mutation probability for any bit of the schema H, and N be the order of the schema H. Then 1 PM represents the probability that the bit will not be mutated, and thus the probability that the schema H will survive after mutation is determined as PM H 1 quarter 1 PMN 7 5. It is also clear that the probability of survival under mutation is higher for low-order schemata than for high-order ones. We can now amend EQ 7.3 to take into account the destructive effects of crossover and mutation. Caret me 1 quarter FE caret FI me 1% LDL 1 PMN 7 6. This equation describes the growth of a schema from one generation to the next. It is known as the schema theorem. Because EQ 7.6 considers only the destructive effects of crossover and mutation, it gives us a lower bound on the number of instances of the schema H in the next generation. Despite crossover arguably representing a major advantage of GAS, there is as yet no theoretical basis to support the view that a GA will outperform other search and optimization techniques just because crossover allows the combination of partial solutions. Genetic algorithms are a very powerful tool, but need to be applied intelligently. For example, coding the problem as a bit string may change the nature of the problem being investigated. In other words, there is a danger that the coded representation becomes a problem that is different from the one we wanted to solve. To illustrate the ideas discussed above, we consider a simple application of the GATA problems of scheduling resources. Maintenance scheduling with genetic algorithms. 235. 7.5 Case study, maintenance scheduling with genetic algorithms. One of the most successful areas for GA applications includes the problem of scheduling resources. Scheduling problems are complex and difficult to solve. They are usually approached with a combination of search techniques and heuristics. Why are scheduling problems so difficult? First, scheduling belongs to NP-complete problems. Such problems are likely to be unmanageable and cannot be solved by combinatorial search techniques. Moreover, heuristics alone cannot guarantee the best solution. Second, scheduling problems involve a competition for limited resources. As a result, they are complicated by many constraints. The key to the success of the GA lies in defining a fitness function that incorporates all these constraints. The problem we discuss here is the maintenance scheduling in modern power systems. This task has to be carried out under several constraints and uncertainties, such as failures and forced outages of power equipment and delays in obtaining spare parts. The schedule often has to be revised at short notice. Human experts usually work out the maintenance scheduling by hand, and there is no guarantee that the optimum or even near optimum schedule is produced. A typical process of the GA development includes the following steps. 1. Specify the problem, define constraints and optimum criteria. 2. Represent the problem domain as a chromosome. 3. Define fitness function to evaluate the chromosome's performance. 4. Construct the genetic operators. 5. Run the GA and tune its parameters. Step 1. Specify the problem, define constraints and optimum criteria. This is probably the most important step in developing a GA, because if it is not correct and complete, a viable schedule cannot be obtained. Power system components are made to operate continuously throughout their life by means of preventive maintenance. The purpose of maintenance scheduling is to find the sequence of outages of power units over a given period of time, normally a year, such that the security of a power system is maximized. Any outage in a power system is associated with some loss in security. The security margin is determined by the system's net reserve. The net reserve, in turn, is defined as the total installed generating capacity of the system minus the power lost due to a scheduled outage and minus the maximum load forecast during the maintenance period. For instance, if we assume that the total installed capacity is 150 megawatts, and a unit of 20 MW is scheduled for maintenance during the period when the maximum load is predicted to be 100 MW, then the net reserve will be 30 megawatts. Maintenance scheduling must ensure that sufficient net reserve is provided for secure power supply during any maintenance period. Suppose there are 7 power units to be maintained in 4 equal intervals. The maximum loads expected during these intervals are 80, 90, 65 and 70 megawatts. The unit capacities and their maintenance requirements are represented in Table 7.2. The constraints for this problem can be specified as follows. Maintenance of one unit starts at the beginning of an interval and finishes at the end of the same or adjacent interval. The maintenance cannot be boarded or finished earlier than scheduled. The net reserve of the power system must be greater than or equal to 0 to any interval. The optimum criterion here is that the net reserve must be the maximum during any maintenance period. Step 2. Represent the problem domain as a chromosome. Our scheduling problem is essentially an ordering problem, requiring us to list the tasks in a particular order. A complex schedule may consist of a number of overlapping tasks, but not all orderings are legal, since they may violate the constraints. Our job is to represent a complete schedule as a chromosome of a fixed length. An obvious coding scheme that comes to mind is to assign a unit a binary number and to let the chromosome be sequence of these binary numbers. However, an ordering of the units in a sequence is not yet a schedule. Some units can be maintained simultaneously, and we must also incorporate the time required for unit maintenance into the schedule. Thus, rather than ordering units in a sequence, we might build a sequence of maintenance schedules of individual units. The unit schedule can be easily represented as a 4-bit string, where each bit is a maintenance interval. If onetostobe maintained in a particular table 7.2 power units and their maintenance requirements unit number unit capacity, MW number of intervals required for unit maintenance during 1 year 1202, 2152, 3351, 4401, 5151, 6151, 7101 evolutionary computation 236. Interval, the corresponding byte assumes value 1, otherwise it is 0. For example, the string presents a schedule for a unit to be maintained in the second interval. It also shows that the number of intervals required for maintenance of this unit is equal to 1. Thus, a complete maintenance schedule for our problem can be represented as a 28-bit chromosome. However, crossover and mutation operators could easily create binary strings that call for maintaining some units more than once and others not at all. In addition, we could call for maintenance periods that would exceed the number of intervals really required for unit maintenance. A better approach is to change the chromosome syntax. As already discussed, a chromosome is a collection of elementary parts called genes. Traditionally, each gene is represented by only one bit and cannot be broken into smaller elements. For our problem, we can adopt the same concept, but represent a gene by 4 bits. In other words, the smallest indivisible part of each chromosome is a 4-bit string. This representation allows crossover and mutation operators to act according to the theoretical grounding of genetic algorithms. What remains to be done is to produce a pool of genes for each unit. The GA can now create an initial population of chromosomes by filling 7 gene chromosomes with genes randomly selected from the corresponding pools. A sample of such a chromosome is shown in figure 7.9. Step 3. Define fitness function to evaluate the chromosome performance. The chromosome evaluation is a crucial part of the GA, because chromosomes are selected formatting based on their fitness. The fitness function must capture what makes a maintenance schedule either good or bad for user. For our problem we apply a fairly simple function concerned with constraint T violations and the net reserve at each interval. 0100 figure 7.9 A chromosome for the scheduling problem 1100 1100 1000 1000 1000 0110 0110 0100 0100 0100 0011 0011 0010 0010 0010 0001 0001 0001 1000 1000 1000 Unit 1, Unit 2, Unit 3, Unit 4, Unit 5, Unit 6, Unit 7. 237 Maintenance scheduling with genetic algorithms. 238. Evolutionary computation. The evaluation of a chromosome starts with the sum of capacities of the units scheduled for maintenance at each interval. For the chromosome shown in figure 7.9, we obtain interval 1, 020 015 035 140 015 015 110 and a quarter 50. Interval 2, 120 015 035 040 115 015 0101 quarter 35. Interval 3, 120 115 035 040 015 115 0101 quarter 50. Interval 4, 020 115 135 040 015 015 0101 quarter 50. Then these values are subtracted from the total installed capacity of the power system, in our case, 150 megawatts, interval 1, 15,050 and a 4,100th. Interval 2, 15,035 and a 4,115th. Interval 3, 15,050 and a 4,100th. Interval 4, 15,050 and a 4,100th. And finally, by subtracting the maximum loads expected at each interval, we obtain the respective net reserves. Interval 1, 10,080 and a quarter 20. Interval 2, 11,590 and a quarter 25. Interval 3, 10,065 and a quarter 35. Interval 4, 10,070 and a quarter 30. Since all the results are positive, this particular chromosome does not violate any constraint, and thus represents a legal schedule. The chromosome's fitness is determined as the lowest of the net reserves, in our case it is 20. If, however, the net reserve at any interval is negative, the schedule is illegal, and the fitness function returns 0. At the beginning of a run, a randomly built initial population might consist of all illegal schedules. In this case, chromosome fitness values remain unchanged, and selection takes place in accordance with the actual fitness values. Step 4. Construct the genetic operators. Constructing genetic operators is challenging and we must experiment to make crossover and mutation work correctly. That chromosome has to be broken up in a way that is legal for our problem. Since we have already changed the chromosome syntax for this, we can use the GA operators in their classical forms. Each gene in a chromosome is represented by a 4-bit indivisible string, which consists of a possible maintenance schedule for a particular unit. Thus, any random mutation. Maintenance scheduling with genetic algorithms. 239. Figure 7.10 Genetic operators for the scheduling problem, A. The crossover operator, B. The mutation operator. Of a gene or recombination of several genes from two parent chromosomes may result only in changes of the maintenance schedules for individual units, but cannot create unnatural chromosomes. Figure 7.10 shows an example of the crossover application during a run of the GA. The children are made by cutting the parents at the randomly selected point denoted by the vertical line and exchanging parental genes after the cut. Figure 7.10b demonstrates an example of mutation. The mutation operator randomly selects a 4-bit gene in a chromosome and replaces it by a gene randomly selected from the corresponding pool. In the example shown in figure 7.10b, the chromosome is mutated in its third gene, which is replaced by the gene chosen from the pool of genes for the unit 3.0001. Step 5. Run the GA and tune its parameters. It is time to run the GA. First, we must choose the population size and the number of generations to be run. Common sense suggests that a larger population can achieve better solutions than a smaller one, but will work more slowly. In fact, however, the most effective population size depends on the problem being solved, particularly on the problem coding scheme. Goldberg, 1989. The GA can run only a finite number of generations to obtain a solution. Perhaps we could choose a very large population and run it only once, or we could choose a smaller population and run it several times. In any case, only experimentation can give us the answer. 240. Evolutionary computation. Figure 7.11 Performance graphs and the best maintenance schedules created in a population of 20 chromosomes, of 50 generations, b. 100 generations. Maintenance scheduling with genetic algorithms. 241. Figure 7.12 Performance graphs and the best maintenance schedules created in a population of 100 chromosomes, A. Mutation rate is 0.001, B. Mutation rate is 0.01. 242. Evolutionary computation. Figure 7.11 A presents performance graphs and the best schedule created by 50 generations of 20 chromosomes. As you can see, the minimum of the net reserves for the best schedule is 15 megawatts. Let us increase the number of generations to 100 and compare the best schedules. Figure 7.11b presents the results. The best schedule now provides the minimum net reserve of 20 megawatts. However, in both cases, the best individuals appeared in the initial generation, and the increasing number of generations did not affect the final solution. It indicates that we should try increasing the population size. Figure 7.12 shows fitness function values across 100 generations, and the best schedule so far. The minimum net reserve has increased to 25 megawatts. To make sure the quality of the best so far schedule, we must compare results obtained under different rates of mutation. Thus, let us increase the mutation rate to 0.01 and rerun the GA once more. Figure 7.12b presents the results. The minimum net reserve is still 25 megawatts. Now we can confidently argue that the optimum solution has been found. 7.6 Evolution strategies. Another approach to simulating natural evolution was proposed in Germany in the early 1960s. Unlike genetic algorithms, this approach called an evolution strategy was designed to solve technical optimization problems. In 1963, two students of the Technical University of Berlin, Ingo Rechenberg and Hans-Paul Schwefel, were working on the search for the optimal shapes of bodies in a flow. In their work, they used the wind tunnel of the Institute of Flow Engineering. Because it was then a matter of laborious intuitive experimentation, they decided to try random changes in the parameters defining the shape following the example of natural mutation. As a result, the evolution strategy was born. Rechenberg, 1965, Schwefel, 1981. Evolution strategies were developed as an alternative to the engineer's intuition. Until recently, evolution strategies were used in technical optimization problems when no analytical objective function was available, and no conventional optimization method existed, thus engineers had to rely only on their intuition. Unlike GAS, evolution strategies use only a mutation operator. How do we implement an evolution strategy? In its simplest form, termed as a 1-1 evolution strategy, one parent generates one offspring per generation by applying normally distributed mutation. The 1-1 evolution strategy can be implemented as follows. Step 1. Choose the number of parameters n to represent the problem, and then determine a feasible range for each parameter. fx1 minute, x1 max g, fx2 minutes, x2 max g, fxn min, xn max g. Evolution strategies. 243. Define a standard deviation for each parameter and the function to be optimized. Step 2. Randomly select an initial value for each parameter from the respective feasible range. The set of these parameters will constitute the initial population of parent parameters. x1, x2, xn. Step 3. Calculate the solution associated with the parent parameters. By 1/4 fx1, x2, xn. Step 4. Create a new offspring parameter by adding a normally distributed random variable with mean 0 and pre-selected deviation to each parent parameter. x0 I 1/4 she a 0. I 1/4 1, 2, n. 7, 7. Normally distributed mutations with mean 0 reflect the natural process of evolution where smaller changes occur more frequently than larger ones. Step 5. Calculate the solution associated with the offspring parameters. By 0 1/4 fx01, x02, x0n. Step 6. Compare the solution associated with the offspring parameters with the one associated with the parent parameters. If the solution for the offspring is better than that for the parents, replace the parent population with the offspring population. Otherwise, keep the parent parameters. Step 7. Go to step 4, and repeat the process until a satisfactory solution is reached, or a specified number of generations is considered. The 1-1 evolution strategy can be represented as a block diagram shown in Figure 7.13. Why do we vary all the parameters simultaneously when generating a new solution? An evolution strategy here reflects the nature of a chromosome. In fact, a single gene may simultaneously affect several characteristics of the living organism. On the other hand, a single characteristic of an individual may be determined by the simultaneous interactions of several genes. The natural selection acts on a collection of genes, not on a single gene in isolation. Evolution strategies can solve a wide range of constrained and unconstrained nonlinear optimization problems and produce better results than many conventional, highly complex, nonlinear optimization techniques. Schwefel, 1995. Experiments also suggest that the simplest version of evolution strategies that uses a single parent single offspring search works best. 244. Evolutionary computation. Figure 7.13 block diagram of the 1-1 evolution strategy. What are the differences between genetic algorithms and evolution strategies? The principal difference between a GA and an evolution strategy is that the former uses both crossover and mutation whereas the latter uses only mutation. In addition, when we use an evolution strategy we do not need to represent the problem in a coded form. Genetic programming. 245. Which method works best? An evolution strategy uses a purely numerical optimization procedure, similar to a focused Monte Carlo search. GAS are capable of more general applications, but the hardest part of applying a GA is coding the problem. In general, to answer the question as to which method works best, we have to experiment to find out. It is application dependent. 7.7 Genetic programming. One of the central problems in computer science is how to make computers solve problems without being explicitly programmed to do so. Genetic programming offers a solution through the evolution of computer programs by methods of natural selection. In fact, genetic programming is an extension of the conventional genetic algorithm, but the goal of genetic programming is not just to evolve a bit string representation of some problem but the computer code that solves the problem. In other words, genetic programming creates computer programs as the solution, while GAS create a string of binary numbers that represent the solution. Genetic programming is a recent development in the area of evolutionary computation. It was greatly stimulated in the 1990s by John Koza, 1992, 1994. How does genetic programming work? According to Koza, genetic programming searches the space of possible computer programs for a program that is highly fit for solving the problem at hand. Koza, 1992. Any computer program is a sequence of operations functions applied to values arguments, but different programming languages may include different types of statements and operations, and have different syntactic restrictions. Since genetic programming manipulates programs by applying genetic operators, a programming language should permit a computer program to be manipulated as data and the newly created data to be executed as a program. For these reasons, Lisp was chosen as the main language for genetic programming. Koza, 1992. What is Lisp? Lisp, or Lisp processor, is one of the oldest high-level programming languages. Fortran is just 2 years older than Lisp. Lisp, which was written by John McCarthy in the late 1950s, has become one of the standard languages for artificial intelligence. Lisp has a highly symbol-oriented structure. Its basic data structures are atoms and lists. An atom is the smallest indivisible element of the Lisp syntax. The number 21, the symbols and the string, "this is a string," are examples of Lisp atoms. A list is an object composed of atoms and/or other lists. Lisp lists are 246. Evolutionary computation. Written as an ordered collection of items inside a pair of parentheses. For example, the list A, B, C calls for the application of the subtraction function to two arguments, namely the list AB and the atom C. First, Lisp applies the multiplication function to the atoms A and B. Once the list AB is evaluated, Lisp applies the subtraction function to the two arguments, and thus evaluates the entire list ABC. Both atoms and lists are called symbolic expressions or S expressions. In Lisp, all data and all programs are S expressions. This gives Lisp the ability to operate on programs as if they were data. In other words, Lisp programs can modify themselves or even write other Lisp programs. This remarkable property of Lisp makes it very attractive for genetic programming. Any Lisp S expression can be depicted as a rooted point-labeled tree with ordered branches. Figure 7.14 shows the tree corresponding to the S expression ABC. This tree has 5 points, each of which represents either a function or a terminal. The two internal points of the tree are labeled with functions and note that the root of the tree is the function appearing just inside the leftmost opening parenthesis of the S expression. The 3 external points of the tree, also called leaves, are labeled with terminals A, B and C. In the graphical representation, the branches are ordered because the order of the arguments in many functions directly affects the results. How do we apply genetic programming to a problem? Before applying genetic programming to a problem, we must accomplish 5 preparatory steps. Koza, 1994. 1. Determine the set of terminals. 2. Select the set of primitive functions. 3. Define the fitness function. 4. Decide on the parameters for controlling the run. 5. Choose the method for designating a result of the run. Figure 7.14 Graphical representation of the Lisp S expression ABC. Genetic programming. 247. Table 7.310 Fitness cases for the Pythagorean theorem. Side A. Side B. Hypotenuse C. Side A. Side B. Hypotenuse C. 3. 8. 18. 32. 4. 5. 14. 2. 11. 3. 5.830952. 16.124515. 18.110770. 33.837849. 5.000000. 12. 21. 7. 16. 2. 10. 6. 4. 24. 9. 15.620499. 21.840330. 8.062258. 28.844410. 9.219545. The Pythagorean theorem helps us to illustrate these preparatory steps and demonstrate the potential of genetic programming. The theorem says that the hypotenuse, C, of a right triangle with short sides A and B is given by P. C 1/4. FFI 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 A2B2. The aim of genetic programming is to discover a program that matches this function. To measure the performance of the as yet undiscovered computer program, we will use a number of different fitness cases. The fitness cases for the Pythagorean theorem are represented by the samples of right triangles in Table 7.3. These fitness cases are chosen at random over a range of values of variables a and b. Step 1. Determine the set of terminals. The terminals correspond to the inputs of the computer program to be discovered. Our program takes two inputs, a and b. Step 2. Select the set of primitive functions. The functions can be presented by standard arithmetic operations, standard programming operations, standard mathematical functions, logical functions or domain-specific functions. Our program will use 4 standard arithmetic operations, and 1 mathematical function sqrt. Terminals and primitive functions together constitute the building blocks from which genetic programming constructs a computer program to solve the problem. Step 3. Define the fitness function. A fitness function evaluates how well a particular computer program can solve the problem. The choice of the fitness function depends on the problem, and may vary greatly from one problem to the next. For our problem, the fitness of the computer program can be measured by the error between the actual result produced by the program and the correct result given by the fitness case. Typically, the error is not measured over just one fitness case, but instead calculated as a sum of the absolute errors over a number of fitness cases. The closer this sum is to 0, the better the computer program. 248. Evolutionary computation. Step 4. Decide on the parameters for controlling the run. For controlling a run, genetic programming uses the same primary parameters as those used for gas. They include the population size and the maximum number of generations to be run. Step 5. Choose the method for designating a result of the run. It is common practice in genetic programming to designate the best so far generated program as the result of a run. Once these 5 steps are complete, a run can be made. The run of genetic programming starts with a random generation of an initial population of computer programs. Each program is composed of functions, an sqrt, and terminals a and b. In the initial population, all computer programs usually have poor fitness, but some individuals are more fit than others. Just as a fitter chromosome is more likely to be selected for reproduction, so a fitter computer program is more likely to survive by copying itself into the next generation. Is the crossover operator capable of operating on computer programs? In genetic programming, the crossover operator operates on 2 computer programs which are selected on the basis of their fitness. These programs can have different sizes and shapes. The 2 offspring programs are composed by recombining randomly chosen parts of their parents. For example, consider the following 2 Lisp S expressions. sqrt, ab, which is equivalent to p. A2 ab, and semicolon. sqrt bb ab sqrt ab, which is equivalent to p. FFI 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 B to a R B FFIFI A B colon. These 2 S expressions can be presented as rooted, point-labeled trees with ordered branches as shown in Figure 7.15 Internal points of the trees correspond to functions and external points correspond to terminals. Any point, internal or external, can be chosen as a crossover point. Suppose that the crossover point for the first parent is the function, and the crossover. Genetic programming. 249. Figure 7.15 Crossover in genetic programming, a 2 parental S expressions, B 2 offspring S expressions. Point for the second parent is the function sqrt. As a result, we obtain the 2 crossover fragments rooted at the chosen crossover points as shown in Figure 7.15 The crossover operator creates 2 offspring by exchanging the crossover fragments of 2 parents. Thus, the first offspring is created by inserting the crossover fragment of the second parent into the place of the crossover fragment of the first parent. Similarly, the second offspring is created by inserting the crossover fragment of the first parent into the place of the crossover fragment of 250. Evolutionary computation. The second parent. The two offspring resulting from crossover of the two parents are shown in Figure 7.15b. These offspring are equivalent to p. A2 ab. P. B2 a. R. A. An ab. B. Colon. The crossover operator produces valid offspring computer programs regardless of the choice of crossover points. Is mutation used in genetic programming? A mutation operator can randomly change any function or any terminal in the Lisp-S expression. Under mutation, a function can only be replaced by a function and a terminal can only be replaced by a terminal. Figure 7.16 explains the basic concept of mutation in genetic programming. In summary, genetic programming creates computer programs by executing the following steps. Koza, 1994. Step 1. Assign the maximum number of generations to be run and probabilities for cloning, crossover and mutation. Note that the sum of the probability of cloning, the probability of crossover and the probability of mutation must be equal to 1. Step 2. Generate an initial population of computer programs of size n by combining randomly selected functions and terminals. Step 3. Execute each computer program in the population and calculate its fitness with an appropriate fitness function. Designate the best so far individual as the result of the run. Step 4. With the assigned probabilities, select a genetic operator to perform cloning, crossover or mutation. Step 5. If the cloning operator is chosen, select one computer program from the current population of programs and copy it into a new population. If the crossover operator is chosen, select a pair of computer programs from the current population, create a pair of offspring programs and place them into the new population. If the mutation operator is chosen, select one computer program from the current population, perform mutation and place the mutant into the new population. All programs are selected with a probability based on their fitness, i.e., the higher the fitness, the more likely the program is to be selected. Step 6. Repeat step 4 until the size of the new population of computer programs becomes equal to the size of the initial population, n. Genetic programming. 251. Figure 7.16 Mutation in genetic programming. A. Original S expressions, B. Mutated S expressions. Step 7. Replace the current parent population with the new offspring population. Step 8. Go to step 3 and repeat the process until the termination criterion is satisfied. Figure 7.17 is a flowchart representing the above steps of genetic programming. 252. Evolutionary computation. Figure 7.17 flowchart for genetic programming. Genetic programming. 253. Figure 7.18 Fitness history of the best S expression. Let us now return to the Pythagorean theorem. Figure 7.18 shows the fitness history of the best S expression in a population of 500 computer programs. As you can see, in the randomly generated initial population, even the best S expression has very poor fitness. But fitness improves very rapidly, and at the fourth generation the correct S expression is reproduced. This simple example demonstrates that genetic programming offers a general and robust method of evolving computer programs. In the Pythagorean theorem example, we used Lisp-S expressions, but there is no reason to restrict genetic programming only to Lisp-S expressions. It can also be implemented in C, C++, Pascal, Fortran, Mathematica, Smalltalk and other programming languages, and can be applied more generally. What are the main advantages of genetic programming compared to genetic algorithms? Genetic programming applies the same evolutionary approach as a GA does. However, genetic programming is no longer breeding bit strings that represent coded solutions but complete computer programs that solve a particular problem. The fundamental difficulty of GAS lies in the problem representation, that is, in the fixed-length coding. A poor representation limits the power of a GA, and even worse, may lead to a false solution. A fixed-length coding is rather artificial. As it cannot provide a dynamic variability in length, such a coding often causes considerable redundancy and reduces the efficiency of genetic search. In contrast, genetic programming uses high-level building blocks of variable length. Their size and complexity can change during breeding. Genetic programming works well in a large number of different cases. Koza, 1994, and has many potential applications. Are there any difficulties? Despite many successful applications, there is still no proof that genetic programming will scale up to more complex problems that require larger computer programs. And even if it scales up, extensive computer runtimes may be needed. 9. Knowledge engineering and data mining, in which we discuss how to pick the right tool for the job, build an intelligent system and turn data into knowledge. 9.1 Introduction, or what is knowledge engineering? Choosing the right tool for the job is undoubtedly the most critical part of building an intelligent system. Having read this far, you are now familiar with rule and frame-based expert systems, fuzzy systems, artificial neural networks, genetic algorithms, and hybrid neuro-fuzzy and fuzzy evolutionary systems. Although several of these tools handle many problems well, selecting the one best suited to a particular problem can be difficult. Davis's law states, "For every tool there is a task perfectly suited to it." Davis and King, 1977. However, it would be too optimistic to assume that for every task there is a tool perfectly suited to it. In this chapter, we suggest basic guidelines for selecting an appropriate tool for a given task, consider the main steps in building an intelligent system and discuss how to turn data into knowledge. The process of building an intelligent system begins with gaining an understanding of the problem domain. We first must assess the problem and determine what data are available and what is needed to solve the problem. Once the problem is understood, we can choose an appropriate tool and develop the system with this tool. The process of building intelligent knowledge-based systems is called knowledge engineering. It has 6 basic phases. Waterman, 1986, Durkin, 1994. 1. Problem assessment. 2. Data and knowledge acquisition. 3. Development of a prototype system. 4. Development of a complete system. 5. Evaluation and revision of the system. 6. Integration and maintenance of the system. 302. Knowledge engineering and data mining. Figure 9.1 The process of knowledge engineering. The process of knowledge engineering is illustrated in Figure 9.1. Knowledge engineering, despite its name, is still more art than engineering, and a real process of developing an intelligent system is not as neat and clean as Figure 9.1 might suggest. Although the phases are shown in sequence, they usually overlap considerably. The process itself is highly iterative, and at any time we may engage in any development activities. Let us now examine each phase in more detail. Introduction. What is knowledge engineering? 303. 9.1.1 Problem assessment. During this phase we determine the problem's characteristics, identify the project's participants, specify the project's objectives and determine what resources are needed for building the system. To characterize the problem, we need to determine the problem type, input and output variables and their interactions, and the form and content of the solution. The first step is to determine the problem type. Typical problems often addressed by intelligent systems are illustrated in Table 9.1. They include diagnosis, selection, prediction, classification, clustering, optimization and control. The problem type influences our choice of the tool for building an intelligent system. Suppose, for example, we develop a system to detect faults in an electric circuit and guide the user through the diagnostic process. This problem clearly belongs to diagnosis. Domain knowledge in such problems can often be represented by production rules, and thus a rule-based expert system might be the right candidate for the job. Of course, the choice of a building tool also depends on the form and content of the solution. For example, systems that are built for diagnostic tasks usually need explanation facilities, the means that enable them to justify their solutions. Such facilities are an essential component of any expert system, but are not available in neural networks. On the other hand, a neural network might be a good choice for classification and clustering problems where the results are often more important than understanding the system's reasoning process. The next step in the problem assessment is to identify the participants in the project. 2 critical participants in any knowledge engineering project are. Table 9.1 Typical problems addressed by intelligent systems. Problem type. Description. Diagnosis. Selection. Prediction. Classification. Clustering. Optimization. Control. Inferring malfunctions of an object from its behavior and recommending solutions. recommending the best option from a list of possible alternatives, predicting the future behavior of an object from its behavior in the past, assigning an object to one of the defined classes, dividing a heterogeneous group of objects into homogeneous subgroups, improving the quality of solutions until an optimal one is found, governing the behavior of an object to meet specified requirements in real time. 304. Knowledge engineering and data mining. The knowledge engineer, a person capable of designing, building and testing an intelligent system, and the domain expert, a knowledgeable person capable of solving problems in a specific area or domain. Then we specify the project's objectives, such as gaining a competitive edge, improving the quality of decisions, reducing labor costs, and improving the quality of products and services. Finally, we determine what resources are needed for building the system. They normally include computer facilities, development software, knowledge and data sources, human experts, textbooks, manuals, websites, databases and examples, and, of course, money. 9.1.2 Data and Knowledge Acquisition. During this phase we obtain further understanding of the problem domain by collecting and analyzing both data and knowledge, and making key concepts of the system's design more explicit. Data for intelligent systems are often collected from different sources, and thus can be of different types. However, a particular tool for building an intelligent system requires a particular type of data. Some tools deal with continuous variables, while others need to have all variables divided into several ranges, or to be normalized to a single range, say from 0 to 1. Some handle symbolic textual data, while others use only numerical data. Some tolerate imprecise and noisy data, while others require only well-defined, clean data. As a result, the data must be transformed, or massaged, into the form useful for a particular tool. However, no matter which tool we choose, there are three important issues that must be resolved before massaging the data. Berry and Leinoff, 1997. The first issue is incompatible data. Often the data we want to analyze store text in EBCDIC coding and numbers in packed decimal format, while the tools we want to use for building intelligent systems store text in the ASCII code and numbers as integers with a single or double precision floating point. This issue is normally resolved with data transport tools that automatically produce the code for the required data transformation. The second issue is inconsistent data. Often the same facts are represented differently in different databases. If these differences are not spotted and resolved in time, we might find ourselves, for example, analyzing consumption patterns of carbonated drinks using data that do not include Coca-Cola just because they were stored in a separate database. The third issue is missing data. Actual data records often contain blank fields. Sometimes we might throw such incomplete records away, but normally we would attempt to infer some useful information from them. In many cases, we can simply fill the blank fields in with the most common or average values. In other cases, the fact that a particular field has not been filled in might itself provide us with very useful information. For example, in a job application form, a blank field for a business phone number might suggest that an applicant is currently unemployed. Introduction. What is knowledge engineering? 305. Our choice of the system building tool depends on the acquired data. As an example, we can consider a problem of estimating the market value of a property based on its features. This problem can be handled by both expert system and neural network technologies. Therefore, before deciding which tool to apply, we should investigate the available data. If, for instance, we can obtain recent sale prices for houses throughout the region, we might train a neural network by using examples of previous sales rather than develop an expert system using knowledge of an experienced appraiser. The task of data acquisition is closely related to the task of knowledge acquisition. In fact, we acquire some knowledge about the problem domain while collecting the data. What are the stages in the knowledge acquisition process? Usually we start with reviewing documents and reading books, papers and manuals related to the problem domain. Once we become familiar with the problem, we can collect further knowledge through interviewing the domain expert. Then we study and analyze the acquired knowledge, and repeat the entire process again. Knowledge acquisition is an inherently iterative process. During a number of interviews, the expert is asked to identify 4 or 5 typical cases, describe how he or she solves each case and explain, or, think out loud, the reasoning behind each solution. Russell and Norvig, 2002. However, extracting knowledge from a human expert is a difficult process. It is often called the knowledge acquisition bottleneck. Quite often experts are unaware of what knowledge they have and the problem-solving strategy they use, or are unable to verbalize it. Experts may also provide us with irrelevant, incomplete or inconsistent information. Understanding the problem domain is critical for building intelligent systems. A classical example is given by Donald Michie, 1982. A cheese factory had a very experienced cheese tester who was approaching retirement age. The factory manager decided to replace him with an intelligent machine. The human tester tested the cheese by sticking his finger into a sample and deciding if it felt right. So it was assumed the machine had to do the same test for the right surface tension. But the machine was useless. Eventually, it turned out that the human tester subconsciously relied on the cheese's smell rather than on its surface tension and used his finger just to break the crust and let the aroma out. The data and knowledge acquired during the second phase of knowledge engineering should enable us to describe the problem-solving strategy at the most abstract, conceptual level and choose a tool for building a prototype. However, we must not make a detailed analysis of the problem before evaluating the prototype. 9.1.3 Development of a prototype system. This actually involves creating an intelligent system or, rather, a small version of it and testing it with a number of test cases. 306. Knowledge engineering and data mining. What is a prototype? A prototype system can be defined as a small version of the final system. It is designed to test how well we understand the problem, or in other words to make sure that the problem-solving strategy, the tool selected for building a system, and techniques for representing acquired data and knowledge are adequate to the task. It also provides us with an opportunity to persuade the skeptics and, in many cases, to actively engage the domain expert in the system's development. After choosing a tool, massaging the data and representing the acquired knowledge in the form suitable for that tool, we design and then implement a prototype version of the system. Once it is built, we examine, usually together with the domain expert, the prototype's performance by testing it with a variety of test cases. The domain expert takes an active part in testing the system, and as a result becomes more involved in the system's development. What is a test case? A test case is a problem successfully solved in the past for which input data and an output solution are known. During testing, the system is presented with the same input data and its solution is compared with the original solution. What should we do if we have made a bad choice of the system building tool? We should throw the prototype away and start the prototyping phase over again. Any attempt to force an ill-chosen tool to suit a problem it wasn't designed for would only lead to further delays in the system's development. The main goal of the prototyping phase is to obtain a better understanding of the problem, and thus by starting this phase with a new tool, we waste neither time nor money. 9.1.4 Development of a complete system. As soon as the prototype begins functioning satisfactorily, we can assess what is actually involved in developing a full-scale system. We develop a plan, schedule and budget for the complete system, and also clearly define the system's performance criteria. The main work at this phase is often associated with adding data and knowledge to the system. If, for example, we develop a diagnostic system, we might need to provide it with more rules for handling specific cases. If we develop a prediction system, we might need to collect additional historical examples to make predictions more accurate. The next task is to develop the user interface, the means of delivering information to a user. The user interface should make it easy for users to obtain any details they need. Some systems may be required to explain its reasoning process and justify its advice, analysis or conclusion, while others need to represent their results in a graphical form. The development of an intelligent system is, in fact, an evolutionary process. As the project proceeds and new data and knowledge are collected and added to. Introduction. What is knowledge engineering? 307. The system, its capability improves and the prototype gradually evolves into a final system. 9.1.5 Evaluation and revision of the system. Intelligent systems, unlike conventional computer programs, are designed to solve problems that quite often do not have clearly defined, right, and wrong solutions. To evaluate an intelligent system is, in fact, to assure that the system performs the intended task to the user's satisfaction. A formal evaluation of the system is normally accomplished with the test cases selected by the user. The system's performance is compared against the performance criteria that were agreed upon at the end of the prototyping phase. The evaluation often reveals the system's limitations and weaknesses, so it is revised and relevant development phases are repeated. 9.1.6 Integration and maintenance of the system. This is the final phase in developing the system. It involves integrating the system into the environment where it will operate and establishing an effective maintenance program. By integrating, we mean interfacing a new intelligent system with existing systems within an organization and arranging for technology transfer. We must make sure that the user knows how to use and maintain the system. Intelligent systems are knowledge-based systems, and because knowledge evolves over time, we need to be able to modify the system. But who maintains the system? Once the system is integrated in the working environment, the knowledge engineer withdraws from the project. This leaves the system in the hands of its users. Thus, the organization that uses the system should have in-house expertise to maintain and modify the system. Which tool should we use? As must be clear by now, there is no single tool that is applicable to all tasks. Expert systems, neural networks, fuzzy systems and genetic algorithms all have a place and all find numerous applications. Only 2 decades ago, in order to apply an intelligent system or, rather, an expert system, one had first to find a good problem, a problem that had some chance for success. Knowledge engineering projects were expensive, laborious and had high investment risks. The cost of developing a moderate-sized expert system was typically between $250,000 and $500,000. Simon, 1987. Such classic expert systems as DENDRAL and Myson took 20 to 40 person-years to complete. Fortunately, the last few years have seen a dramatic change in the situation. Today, most intelligent systems are built within months rather than years. We use commercially available expert system shells, fuzzy, neural network and evolutionary computation toolboxes, and run our applications on standard PCs. And most. 308. Knowledge engineering and data mining. Importantly, adopting new intelligent technologies is becoming problem-driven, rather than curiosity-driven as it often was in the past. Nowadays an organization addresses its problems with appropriate intelligent tools. In the following sections, we discuss applications of different tools for solving specific problems. 9.2 Will an expert system work for my problem? Case Study 1. Diagnostic Expert Systems. I want to develop an intelligent system that can help me to fix malfunctions of my Mac computer. Will an expert system work for this problem? There is an old but still useful test for prime candidates for expert systems. It is called the phone call rule. Firebaugh, 1988. Any problem that can be solved by your in-house expert in a 10 to 30-minute phone call can be developed as an expert system. Diagnosis and troubleshooting problems. Of course, computer diagnosis is one of them, have always been very attractive candidates for expert system technology. As you may recall, medical diagnosis was one of the first areas to which expert systems were applied. Since then, diagnostic expert systems have found numerous applications, particularly in engineering and manufacturing. Diagnostic expert systems are relatively easy to develop. Most diagnostic problems have a finite list of possible solutions, involve a rather limited amount of well-formalized knowledge, and often take a human expert a short time, say, an hour, to solve. To develop a computer diagnostic system, we need to acquire knowledge about troubleshooting in computers. We might find and interview a hardware specialist, but for a small expert system there is a better alternative: to use a troubleshooting manual. It provides step-by-step procedures for detecting and fixing a variety of faults. In fact, such a manual contains knowledge in the most concise form that can be directly used in an expert system. There is no need to interview an expert, and thus we can avoid the knowledge acquisition bottleneck. Computer manuals often include troubleshooting sections, which consider possible problems with the system startup, computer peripherals, hard disk, keyboard, monitor, printer, disk drives, floppy disk, CD-ROM files, and network and file sharing. In our example, we will consider only troubleshooting the Mac system startup. However, once the prototype expert system is developed, you can easily expand it. Figure 9.2 illustrates the troubleshooting procedure for the Macintosh computer. As you can see, troubleshooting here is carried out through a series of visual inspections, or tests. We first collect some initial information. The system does not start, infer from it whatever can be inferred, gather additional information, power cords are okay, power strip is okay, etc., and finally identify. Will an expert system work for my problem? 309. Figure 9.2 Troubleshooting the system startup for Macintosh computers. The cause of the system's malfunction. This is essentially data-driven reasoning, which can be best realized with the forward-chaining inference technique. The expert system should first ask the user to select a particular task, and once the task is selected, the system should direct troubleshooting by asking the user for additional information until the fault is found. Let us develop a general rule structure. In each rule, we need to include a clause that identifies the current task. Since our prototype is limited to the 310. Knowledge engineering and data mining. Mac system startup, the first clause of all rules will identify this task. For example, Rule 1 if task is system startup, then ask problem rule 2. If task is system startup, and problem is system does not start, then ask test power chords. Rule 3 if task is system startup, and problem is system does not start, and test power chords is okay, then ask test power strip. All the other rules will follow this structure. A set of rules to direct troubleshooting when the Mac system does not start in Leonardo code is shown in figure 9.3. Now we are ready to build a prototype, or in other words to implement the initial set of rules using an expert system development tool. How do we choose an expert system development tool? In general, we should match the features of the problem with the capabilities of the tool. These tools range from high-level programming languages such as Lisp, Prolog, OPS, C and Java, to expert system shells. High-level programming languages offer a greater flexibility and can enable us to meet any project requirements, but they do require high-level programming skills. On the other hand, shells, although they do not have the flexibility of programming languages, Prometheus with the built-in inference engine, explanation facilities and the user interface. We do not need any programming skills to use C shell, we just enter listen English in the shell's knowledge base. This makes shells particularly useful for rapid prototyping. So how do we choose a shell? The appendix provides some details of a few commercial expert systems shells currently available on the market. This can help you to choose an appropriate tool. However, the internet is rapidly becoming the most valuable source of information. Many vendors have websites, and you can even try and evaluate their products over the web. In general, when selecting an expert system shell, you should consider how the shell represents knowledge, rules or frames, what inference mechanism it uses, forward or backward chaining, whether the shell supports inexact reasoning and if so what technique it uses, Bayesian reasoning, certainty factors or fuzzy logic, whether the shell has an open architecture allowing access to. Will an expert system work for my problem? 311. Figure 9.3 Rules for a prototype of the Mac troubleshooting expert system. External data files and programs, and how the user will interact with the expert system, graphical user interface, hypertext. Today you can buy an expert system shell for less than $500 and run it on your PC or Mac. You can also obtain an expert system shell for free, for example, Clips. However, you should clearly understand your license obligations, especially whether you need to have a distribution license allowing the end user to use your expert system once it is developed. 312. Knowledge engineering and data mining. An important area for consideration in choosing a tool is the stability of the company supplying the tool. What are indicators of a company's stability? There are several important indicators, such as the year founded, number of employees, total gross income from intelligent systems products, and number of products sold. Similar indicators represent the stability of a particular product. When was the product officially released? How many versions have been released? How many installations have been made? These are important questions for determining the development stage of the product. However, probably the best method for evaluating both products and vendors is to obtain a list of users, successful applications and installation sites. Just a few minutes on the phone with the tool's user brings to light the strengths and weaknesses of the product and its supplier. Case Study 2. Classification Expert Systems. I want to develop an intelligent system that can help me to identify different classes of sailboats. Will an expert system work for this problem? This is a typical classification problem. To identify a boat means to assign it to one of the defined classes and, as we discussed earlier, such problems can be handled well by both expert systems and neural networks. If you decide to build an expert system, you should start with collecting some information about mast structures and sail plans of different sailing vessels. As an example, consider Figure 9.4, which shows 8 classes of sailboats. Each boat can be uniquely identified by its sail plans. Figure 9.4 8 classes of sailing vessels. Will an expert system work for my problem? 313. Figure 9.5 Rules for the boat classification expert system. A set of rules in Leonardo Code for the sailing vessel classification is shown in Figure 9.5. During a dialogue session with the user, the system obtains the number and position of masts on the unknown vessel as well as the shape of its mainsail, and then uniquely identifies each of the 8 boats shown in Figure 9.4. No doubt when the sky is blue and the sea is calm, this system will help us to identify a sailboat. But this is not always the case. On a rough sea or in foggy conditions, it is difficult, or even impossible, to see clearly the position of masts and the shape of the mainsail. Despite the fact that solving real-world classification problems often involves inexact and incomplete data such as these, we still can use the expert system approach. However, we need to deal with uncertainties. Let us apply the certainty factors theory to our problem. This. 314. Knowledge engineering and data mining. Figure 9.6 Uncertainty management in the boat classification expert system. Will an expert system work for my problem? 315. Theory, as you may recall, can manage incrementally acquired evidence, as well as information with different degrees of belief. Figure 9.6 shows a complete set of rules for solving the sailing vessel classification problem with certainty factors. The expert system is required to classify a boat, or in other words to establish certainty factors for a multi-valued object boat. To apply the evidential reasoning technique, the expert system prompts the user to input not only the object value but also the certainty associated with this value. For example, using the Leonardo scale from 0 to 1, we might obtain the following dialogue. The user's answers are indicated by arrows. Also note the propagation of certainty factors through the set of rules. What is the number of masts? 2. To what degree do you believe that the number of masts is 2? Enter a numeric certainty between 0 and 1.0 inclusive. 0.9. Rule. For if the number of masts is 2, then boat is jib-headed ketch. Boat is gaff-headed ketch. Boat is jib-headed yawl. Boat is gaff-headed yawl. CF 0.1. CF 0.1. CF 0.1. CF 0.1. Boat is gaff-headed schooner. CF 0.1. Boat is staysail schooner. CF 0.1. CF boat is jib-headed ketch. 1/4 CF number of masts is 2, 0.1 1/4 0.9 0.1 1/4 0.09 CF boat is gaff-headed ketch. 1/4 0.9 0.1 1/4 0.09 CF boat is jib-headed yawl. 1/4 0.9 0.1 1/4 0.09 CF boat is gaff-headed yawl. 1/4 0.9 0.1 1/4 0.09 CF boat is gaff-headed schooner. 1/4 0.9 0.1 1/4 0.09 CF boat is staysail schooner. 1/4 0.9 0.1 1/4 0.09. Boat is jib-headed ketch. Gaff-headed ketch. Jib-headed yawl. Gaff-headed yawl. Gaff-headed schooner. Staysail schooner. What is the position of the main mast? Aft the short mast. CF 0.09. CF 0.09. CF 0.09. CF 0.09. CF 0.09. CF 0.09. To what degree do you believe that the main mast position is aft the short mast? Enter a numeric certainty between 0 and 1.0 inclusive. 0.7. Rule. 6 if the number of masts is 2 and the main mast position is aft the short mast, then boat is gaff-headed schooner. CF 0.4 boat is staysail schooner. CF 0.4. 316. Knowledge engineering and data mining. CF rule. 6 boat is gaff-headed schooner. 1/4 of a minute CF the number of masts is 2 CF the main mast position is aft the short mast, 0.41 quarter of a minute 0.9, 0.7, 0.4 a quarter 0.28. CF rule. 6 boat is, staysail schooner, 1 quarter of a minute 0.9, 0.7, 0.4 a quarter 0.28. CF boat is, gaff-headed schooner, 1 quarter CF rule, 4 CF rule, 6 1 CF rule, 4 1 quarter 0.09, 0.28, 1 0.09, 1 quarter 0.34. CF boat is, staysail schooner, 1 quarter 0.09, 0.28, 1 0.09, 1 quarter 0.34. Boat is gaff-headed schooner. Staysail schooner. Jib-headed ketch. Gaff-headed ketch. Jib-headed yawl. Gaff-headed yawl. What is the position of the short mast? Forward of the helm. CF 0.34. CF 0.34. CF 0.09. CF 0.09. CF 0.09. CF 0.09. To what degree do you believe that the short mast position is forward of the helm? Enter a numeric certainty between 0 and 1.0 inclusive. 0.6. Rule. 7 if the number of masts is 2 and the short mast position is forward of the helm, then boat is jib-headed ketch. Boat is gaff-headed ketch. CF 0.4. CF 0.4. CF rule. 7 boat is jib-headed ketch, 1 quarter of a minute CF the number of masts is 2 CF the short mast position is forward of the helm, 0.41 quarter of a minute 0.9, 0.6 0.4 a quarter 0.24. CF rule. 7 boat is gaff-headed ketch, equals min 0.9, 0.6 0.4 a quarter 0.24. CF boat is jib-headed ketch, 1 quarter CF rule, 6 CF rule, 7 1 CF rule, 6 1 quarter 0.09, 0.24, 1 0.09, 1 quarter 0.30. CF boat is gaff-headed ketch, 1 quarter 0.09, 0.24, 1 0.09, 1 quarter 0.30. Boat is gaff-headed schooner. Staysail schooner. Jib-headed ketch. Gaff-headed ketch. Jib-headed yawl. Gaff-headed yawl. What is the shape of the mainsail? Triangular. CF 0.34. CF 0.34. CF 0.30. CF 0.30. CF 0.09. CF 0.09. To what degree do you believe that the shape of the mainsail is triangular? Enter a numeric certainty between 0 and 1.0 inclusive. 0.8. Will a fuzzy expert system work for my problem? 317. Rule. 9 if the number of masts is 2 and the shape of the mainsail is triangular, then boat is jib-headed ketch. Boat is jib-headed yawl. CF 0.4. CF 0.4. CF rule. 9 boat is jib-headed ketch, 1 quarter of a minute CF the number of masts is 2 CF the shape of the mainsail is triangular, 0.41 quarter of a minute 0.9, 0.8, 0.4 a quarter 0.32. CF rule. 9 boat is jib-headed yawl, 1 quarter of a minute 0.9, 0.8, 0.4 a quarter 0.32. CF boat is jib-headed ketch, equals CF rule. 7 CF rule. 9 1 CF rule. 7 1 quarter 0.30, 0.32, 1 0.30, 1 quarter 0.52. CF boat is jib-headed yawl, 1 quarter 0.09, 0.32, 1 0.09, 1 quarter 0.38. Boat is jib-headed ketch. Jib-headed yawl. Gaff-headed schooner. Staysail schooner. Gaff-headed ketch. Gaff-headed yawl. CF 0.52. CF 0.38. CF 0.34. CF 0.34. CF 0.30. CF 0.09. Now we can conclude that the boat is probably a jib-headed ketch and almost certainly not a gaff-headed ketch or gaff-headed yawl. 9.3 Will a fuzzy expert system work for my problem? We need to decide which problem is a good candidate for fuzzy technology. The basic approach here is simple. If you cannot define a set of exact rules for each possible situation, then use fuzzy logic. While certainty factors and Bayesian probabilities are concerned with the imprecision associated with the outcome of a well-defined event, fuzzy logic concentrates on the imprecision of the event itself. In other words, inherently imprecise properties of the problem make it a good candidate for fuzzy technology. Fuzzy systems are particularly well suited for modeling human decision-making. We often rely on common sense and use vague and ambiguous terms while making important decisions. Doctors, for example, do not have a precise threshold in mind when they decide whether a patient in a post-operative recovery area should be sent to a general hospital floor. Although hypothermia is a significant concern after surgery and the patient's body temperature often plays a vital role in the doctor's decision, such factors as the stability of the patient's blood pressure and his or her perceived comfort at discharge are also taken into account. A doctor makes an accurate assessment not from the precision of a single parameter, say, a body temperature, but rather from evaluating several parameters, some of which are expressed in ambiguous terms, for instance, the patient's willingness to leave the post-operative recovery unit. 318. Knowledge engineering and data mining. Although most fuzzy technology applications are still reported in control and engineering, an even larger potential exists in business and finance. Von Altrock, 1997. Decisions in these areas are often based on human intuition, common sense and experience, rather than on the availability and precision of data. Decision-making in business and finance is too complex and too uncertain to lend itself to precise analytical methods. Fuzzy technology provides us with a means of coping with the soft criteria and fuzzy data that are often used in business and finance. Case Study 3. Decision Support Fuzzy Systems. I want to develop an intelligent system for assessing mortgage applications. Will a fuzzy expert system work for this problem? Mortgage application assessment is a typical problem to which decision support fuzzy systems can be successfully applied. Von Altrock, 1997. To develop a decision support fuzzy system for this problem, we first represent the basic concept of mortgage application assessment in fuzzy terms, then implement this concept in a prototype system using an appropriate fuzzy tool, and finally test and optimize the system with selected test cases. Assessment of a mortgage application is normally based on evaluating the market value and location of the house, the applicant's assets and income, and the repayment plan, which is decided by the applicant's income and bank's interest charges. Where do membership functions and rules for mortgage loan assessment come from? To define membership functions and construct fuzzy rules, we usually need the help of experienced mortgage advisors and also bank managers, who develop the mortgage granting policies. Figures 9.7 to 9.14 show fuzzy sets for linguistic variables used in our problem. Triangular and trapezoidal membership functions can adequately represent the knowledge of the mortgage expert. Figure 9.7 Fuzzy sets of the linguistic variable market value. Will a fuzzy expert system work for my problem? 319. Figure 9.8 Fuzzy sets of the linguistic variable location. Figure 9.9 Fuzzy sets of the linguistic variable house. Figure 9.10 Fuzzy sets of the linguistic variable asset. Figure 9.11 Fuzzy sets of the linguistic variable income. 320. Knowledge engineering and data mining. Figure 9.12 Fuzzy sets of the linguistic variable applicant. Figure 9.13 Fuzzy sets of the linguistic variable interest. Figure 9.14 Fuzzy sets of the linguistic variable credit. Next we obtain fuzzy rules. In our case, we simply adapt some of the basic rules used by Von Altrock in his fuzzy model for mortgage loan assessment. Von Altrock, 1997. These rules are shown in Figure 9.15. Complex relationships between all variables used in the fuzzy system can be represented best by the hierarchical structure shown in Figure 9.16. To build our system, use the MATLAB Fuzzy Logic Toolbox, one of the most popular fuzzy tools currently on the market. The last phase in the development of a prototype system is its evaluation and testing. Will a fuzzy expert system work for my problem? 321. Figure 9.15 Rules for mortgage loan assessment. To evaluate and analyze the performance of a fuzzy system, we can use the output surface viewer provided by the Fuzzy Logic Toolbox. Figures 9.17 and 9.18 represent three-dimensional plots of the fuzzy system for mortgage loan assessment. Finally, the mortgage experts would try the system with several test cases. Decision support fuzzy systems may include dozens, and even hundreds, of rules. For example, a fuzzy system for credit risk evaluation developed by BMW. 322. Knowledge engineering and data mining. Figure 9.16 Hierarchical fuzzy model for mortgage loan assessment. Banken Inform software used 413 fuzzy rules. GU Diaresis L. Lich, 1996. Large knowledge bases are usually divided into several modules in a manner similar to that shown in Figure 9.16. In spite of the often large number of rules, decision support fuzzy systems can be developed, tested and implemented relatively quickly. For instance, it took just 2 person-years to develop and implement the fuzzy system for credit risk evaluation. Compare this effort with the 40 person-years it took to develop Myson. Figure 9.17 Three-dimensional plots for Rule Base 1 and Rule Base 2. Will a neural network work for my problem? 323. Figure 9.18 Three-dimensional plots for Rule Base 3. 9.4 Will a neural network work for my problem? Neural networks represent a class of very powerful, general-purpose tools that have been successfully applied to prediction, classification and clustering problems. They are used in a variety of areas, from speech and character recognition to detecting fraudulent transactions, from medical diagnosis of heart attacks to process control and robotics, from predicting foreign exchange rates to detecting and identifying radar targets. And the areas of neural network applications continue to expand rapidly. The popularity of neural networks is based on their remarkable versatility, abilities to handle both binary and continuous data, and to produce good results in complex domains. When the output is continuous, the network can address prediction problems, but when the output is binary, the network works as a classifier. Case Study 4. Character Recognition Neural Networks. I want to develop a character recognition system. Will a neural network work for this problem? Recognition of both printed and handwritten characters is a typical domain where neural networks have been successfully applied. In fact, optical character recognition systems were among the first commercial applications of neural networks. What is optical character recognition? It is the ability of a computer to translate character images into a text file, using special software. It allows us to take a printed document and put it into a computer in editable form without the need of retyping the document. To capture the character images we can use a desktop scanner. It either passes light-sensitive sensors over the illuminated surface of a page or moves a page through the sensors. The scanner processes the image by dividing it into hundreds of pixel-sized boxes per inch and representing each box by either 1, if the box is filled, or 0, if the box is empty. The resulting matrix of dots is called a bitmap. Bitmaps can be stored, displayed and printed by a computer. 324. Knowledge engineering and data mining. Figure 9.19 Bitmaps for digit recognition. But we cannot use a word processor to edit the text. The patterns of dots have to be recognized as characters by the computer. This is the job for a neural network. Let us demonstrate an application of a multi-layer feedforward network for printed character recognition. For simplicity, we can limit our task to the recognition of digits from 0 to 9. In this application, each digit is represented by a 59 bitmap, as shown in Figure 9.19. In commercial applications, where a better resolution is required, at least 16 16-bit maps are used. Zarada, 1992. How do we choose the architecture of a neural network for character recognition? The architecture and size of a neural network depend on the complexity of the problem. For example, handwritten character recognition is performed by rather complex multi-layer networks that may include 3, or even 4, hidden layers and hundreds of neurons. Zarada, 1992. Haken, 1999. However, for the printed digit recognition problem, a 3-layer network with a single hidden layer will give sufficient accuracy. The number of neurons in the input layer is decided by the number of pixels in the bitmap. The bitmap in our example consists of 45 pixels, and thus we need 45 input neurons. The output layer has 10 neurons, 1 neuron for each digit to be recognized. How do we determine an optimal number of hidden neurons? Simulation experiments indicate that the number of neurons in the hidden layer affects both the accuracy of character recognition and the speed of training the network. Complex patterns cannot be detected by a small number of hidden neurons, however too many of them can dramatically increase the computational burden. Will a neural network work for my problem? 325. Another problem is overfitting. The greater the number of hidden neurons, the greater the ability of the network to recognize existing patterns. However, if the number of hidden neurons is too big, the network might simply memorize all training examples. This may prevent it from generalizing, or producing correct outputs when presented with data that was not used in training. For instance, the overfitted character recognition network trained with Helvetica font examples might not be able to recognize the same characters in the Times New Roman font. The practical approach to preventing overfitting is to choose the smallest number of hidden neurons that yields good generalization. Thus, at the starting point, an experimental study could begin with as little as 2 neurons in the hidden layer. In our example, we will examine the system's performance with 2, 5, 10 and 20 hidden neurons and compare results. The architecture of a neural network with 5 neurons in the hidden layer for the character recognition problem is shown in Figure 9.20. Neurons in the hidden and output layers use a sigmoid activation function. The neural network is trained with the back propagation algorithm with momentum. The momentum constant is set to 0.95. The input and output training patterns are shown in Table 9.2. The binary input vectors representing the bit maps of the respective digits are fed directly into the network. The network's performance in our study is measured by the sum of squared errors. Figure 9.21 demonstrates the results. As can be seen from Figure 9.21a, a neural network with 2 neurons in the hidden layer cannot converge to a solution, while the networks with 5, 10 and 20 hidden neurons learn relatively fast. In fact, they converge in less than 250 epochs. Each epoch represents an entire pass through all training examples. Also note that the network with 20 hidden neurons shows the fastest convergence. Once the training is complete, we must test the network with a set of test examples to see how well it performs. Figure 9.20 Neural network for printed digit recognition. 326. Table 9.2 Input and desired output patterns for the digit recognition neural network. Input patterns rows in the pixel matrix. Digit. Desired output. 123,456,789 patterns. 10010001100 10100 00100 00100 00100 00100 00100 00100 100000000 2011110 10001 00001 00001 00010 00100 01000 10000 11111 0100000 3011110 10001 00001 00001 00010 00001 00001 10001 01110 0010000 40010 00110 00110 01010 01010 10010 11111 00010 00010 00010 51111 10000 10000 11110 10001 00001 00001 10001 01110 00010 60111 10001 10000 10000 1110 10001 10001 10001 01110 00010 71111 00001 00010 00010 00010 00010 01000 01000 01000 00000 80111 10001 10001 10001 0110 10001 10001 10001 0110 0000000 90111 10001 10001 10001 0111 00001 00001 10001 0110 0000010 Knowledge engineering and data mining. 00111 10001 1001 1001 1001 1001 1001 1001 0110 0000001 Will a neural network work for my problem? 327. Figure 9.21 Training and Performance Evaluation of the Digit Recognition 3-Layer Neural Networks, of Learning Curves, B. Performance Evaluation. What are the test examples for character recognition? Are they the same that were used for neural network training? A test set has to be strictly independent from the training examples. Thus, to test the character recognition network, we must present it with examples that include noise, the distortion of the input patterns. This distortion can be created, for instance, by adding some small random values chosen from a normal distribution to the binary input vectors representing bitmaps of the 10 digits. We evaluate the performance of the printed digit recognition networks with 1000 test examples, 100 for each digit to be recognized. The results are shown in Figure 9.21b. Although the average recognition error of the network with 20 hidden neurons is the lowest, the results do not demonstrate significant differences between the networks with 10 and 20 hidden neurons. Both networks can sustain similar levels of noise without sacrificing their recognition performance. On this basis, we may conclude that for the digit recognition problem described here, the use of 10 hidden neurons is adequate. Can we improve the performance of the character recognition neural network? A neural network is as good as the examples used to train it. Therefore, we can attempt to improve digit recognition by feeding the network with noisy examples of digits from 0 to 9. The results of such an attempt are shown in Figure 9.22. As we expected, there is some improvement in the performance of the digit recognition network trained with noisy data. This case study illustrated one of the most common applications of multilayer neural networks trained with the backpropagation algorithm. Modern character recognition systems are capable of processing different fonts in English, French, Spanish, Italian, Dutch and several other languages with great accuracy. Optical character recognition is routinely used by office workers, lawyers, insurance clerks, journalists, in fact anybody who wants to take a printed or even. 328. Knowledge engineering and data mining. Figure 9.22 Performance evaluation of the digit recognition network trained with noisy examples. Handwritten document and load it into their computer as an editable file. Handwritten digit recognition systems are widely used in processing zip codes on mail envelopes. LeCun et al., 1990. Case Study 5. Prediction Neural Networks. I want to develop an intelligent system for real estate appraisal. Will a neural network work for this problem? Real estate appraisal is a problem of predicting the market value of a given house based on the knowledge of the sales prices of similar houses. As we mentioned earlier, this problem can be solved with expert systems as well as neural networks. Of course, if we choose to apply a neural network, we will not be able to understand how an appraisal of a particular house is reached. A neural network is essentially a black box to the user and rules cannot be easily extracted from it. On the other hand, an accurate appraisal is often more important than understanding how it was done. In this problem, the inputs, the house location, living area, number of bedrooms, number of bathrooms, land size, type of heating system, etc., are well defined, and normally even standardized for sharing the housing market information between different real estate agencies. The output is also well defined. We know what we are trying to predict. Most importantly, there are many examples we can use for training the neural network. These examples are the features of recently sold houses and their sales prices. Will a neural network work for my problem? 329. Choosing training examples is critical for an accurate prediction. A training set must cover the full range of values for all inputs. Thus, in the training set for real estate appraisal, we should include houses that are large and small, expensive and inexpensive, with and without garages, etc. And the training set has to be sufficiently large. But how do we determine when the size of a training set is sufficiently large? A network's ability to generalize is influenced by three main factors: the size of the training set, the architecture of the network, and the complexity of the problem. Once the network architecture is decided, the issue of generalization is resolved by the adequacy of the training set. An appropriate number of training examples can be estimated with Widrow's rule of thumb, which suggests that, for a good generalization, we need to satisfy the following condition. Widrow and Stearns, 1985, Haken, 1999. N1/4. Northwest E. 9, 1. Where n is the number of training examples, northwest is the number of synaptic weights in the network, and e is the network error permitted on test. Thus, if we allow an error of, say, 10%, the number of training examples should be approximately 10 times bigger than the number of weights in the network. In solving prediction problems, including real estate appraisal, we often combine input features of different types. Some features, such as the house's condition and its location, can be arbitrarily rated from 1 least appealing to 10 most appealing. Some features, such as the living area, land size and sales price, are measured in actual physical quantities, square meters, dollars, etc. Some features represent counts, number of bedrooms, number of bathrooms, etc., and some are categories, type of heating system. A neural network works best when all its inputs and outputs vary within the range between 0 and 1, and thus all the data must be massaged before we can use them in a neural network model. How do we massage the data? Data can be divided into 3 main types: continuous, discrete and categorical. Berry and Leinoff, 1997, and we normally use different techniques to massage different types of data. Continuous data vary between 2 preset values, minimum and maximum, and can be easily mapped, or massaged, to the range between 0 and 1 as massaged value 1/4, actual value, minimum value, maximum value, minimum value 9, 2. For instance, if the living areas of the houses in training examples range between 59 and 231 square meters, we might set the minimum value to 50 and the maximum to 250 square meters. Any value lower than them must map to the minimum, and any value higher than the maximum to the maximum. Thus, a living area of, say, 121 square meters would be massaged as massaged value 121 and a quarter 12150, 25050 1/4 0. 355. This method works well for most applications. Discrete data, such as the number of bedrooms and the number of bathrooms, also have maximum and minimum values. For example, the number of bedrooms usually ranges from 0 to 4. Massaging discrete data, simple, we assign an equal space to each possible value on the interval from 0 to 1, as shown in figure 9.23. A neural network can now handle a feature like the number of bedrooms as a single input. For example, a 3-bedroom house would be represented by the input value of 0.75. This approach is sufficient for most applications with discrete features that have up to a dozen possible values. However, if there are more than a dozen values, a discrete feature should be treated like a continuous one. Categorical data, such as gender and marital status, can be massaged by using one-of-n coding. Berry and Leinoff, 1997. This method implies that each categorical value is handled as a separate input. For example, marital status, which can be either single, divorced, married or widowed, would be represented by 4 inputs. Each of these inputs can have a value of either 0 or 1. Thus, a married person would be represented by an input vector 1/20010. Let us know construct a feed-forward neural network for real estate appraisal. Figure 9.24 represents a simplified model that was set up by using training examples with features of the houses recently sold in Hobart. In this model, the input layer, which includes 10 neurons, passes massaged input values to the hidden layer. All input features, except type of heating system, are treated as single inputs. The type of heating system represents a categorical type of data, which is massaged with one-of-n coding. Figure 9.23 Massaging discrete data KNOWLEDGENGINERINGANDDATAMINING 330. Will a neural network work for my problem? 331. Figure 9.24 Feedforward neural network for real estate appraisal. The hidden layer includes 2 neurons, and the output layer is represented by a single neuron. Neurons in the hidden and output layers apply sigmoid activation functions. The neural network for real estate appraisal determines the value of a house, and thus the network output can be interpreted in dollars. But how do we interpret the network output? In our example, the network output is represented by continuous values in the range between 0 and 1. Thus, to interpret the results, we can simply reverse the procedure we used for massaging continuous data. Suppose, for instance, that in the training set, sales prices range between $52,500 and $225,000, and the output value is set up so that $50,000 maps to 0 and $250,000 maps to 1. Then, if the network output is 0.3546, we can compute that this value corresponds to actual value 0, 3,546 and a quarter 0, $3,546 $250, $000 $50, $000 $50, $000 quarter $120, $920. How do we validate results? To validate results, we use a set of examples never seen by the network. Before training, all the available data are randomly divided into a training set and a test set. Once the training phase is complete, the network's ability to generalize is tested against examples of the test set. A neural network is opaque. We cannot see how the network derives its results. But we still need to grasp relationships between the network inputs and the results it produces. Although current research into rule extraction from trained neural networks will eventually bring adequate outcomes, the nonlinear characteristics of neurons may prevent the network from producing simple and understandable rules. Fortunately, to understand the importance of a particular input to the network output, we do not need rule extraction. Instead, we can use a simple technique called sensitivity analysis. Sensitivity analysis determines how sensitive the output of a model is to a particular input. This technique is used for understanding internal relationships in opaque models, and thus can be applied to neural networks. Sensitivity analysis is performed by measuring the network output when each input is set. 332. Knowledge engineering and data mining. One at a time to its minimum and then its maximum values. Changes in some inputs may have little effect on the network output. The network is not sensitive to these inputs. Changes in other inputs have a much greater effect on the network output. The network is sensitive to these inputs. The amount of change in the network output represents the network's sensitivity to a respective input. In many cases, sensitivity analysis can be as good as the rules extracted from the trained neural network. Case Study 6. Classification neural networks with competitive learning. I want to develop an intelligent system that can divide a group of iris plants into classes and then assign any iris plant to one of these classes. I have a dataset with several variables, but I have no idea how to separate it into different classes because I cannot find any unique or distinctive features in the data. Will a neural network work for this problem? Neural networks can discover significant features in input patterns and learn how to separate input data into different classes. A neural network with competitive learning is a suitable tool to accomplish this task. The competitive learning rule enables a single-layer neural network to combine similar input data into groups or clusters. This process is called clustering. Each cluster is represented by a single output. In fact, clustering can be defined as the process of dividing an input space into regions, each of which is associated with a particular output. Principe et al. 2000. For this case study, we will use a data set of 150 elements that contains 3 classes of iris plants: Iris setosa, versicolor and virginica. Fisher, 1950. Each plant in the data set is represented by 4 variables: sepal length, sepal width, petal length and petal width. The sepal length ranges between 4.3 and 7.9 centimeters, sepal width between 2.0 and 4.4 centimeters, petal length between 1.0 and 6.9 centimeters, and petal width between 0.1 and 2.5 centimeters. In a competitive neural network, each input neuron corresponds to a single input, and each competitive neuron represents a single cluster. Thus, the network for the iris plant classification problem will have 4 neurons in the input layer and 3 neurons in the competitive layer. The network's architecture is shown in Figure 9.25. However, before the network is trained, the data must be massaged and then divided into training and test sets. The iris plant data are continuous, vary between some minimum and maximum values, and thus can easily be massaged to the range between 0 and 1 using EQ. 9.2. Massaged values can then be fed to the network as its inputs. The next step is to generate training and test sets from the available data. The 150-element iris data is randomly divided into a training set of 100 elements and a test set of 50 elements. No, we can train the competitive neural network to divide input vectors into 3 classes. Figure 9.26 illustrates the learning process with the learning rate of. Will a neural network work for my problem? 333. Figure 9.25 Neural network for iris plant classification. 0.01. Black dots here represent the input patterns and 3 spheres denote the weight vectors of the competitive neurons. The location of each sphere is determined by the neurons' weights in the 4-dimensional input space. Initially all weights of the competitive neurons are assigned the same value of 0.5, and thus only one sphere appears in the center of the input space, as shown in figure 9.26a. After training, the weight vectors correspond to the positions of the cluster centers, so that each competitive neuron can now respond to input data in a particular region. Figure 9.26 Competitive learning in the neural network for iris plant classification. A. Initial weights, B. Weight after 100 iterations, C. Weight after 2000 iterations. 334. Knowledge engineering and data mining. How do we know when the learning process is complete? In a competitive neural network, unlike a multi-layer perceptron trained with the backpropagation algorithm, there is no obvious way of knowing whether the learning process is complete or not. We do not know what the desired outputs are, and thus cannot compute the sum of squared errors, a criterion used by the backpropagation algorithm. Therefore, we should use the Euclidean distance criterion instead. When no noticeable changes occur in the weight vectors of competitive neurons, a network can be considered to have converged. In other words, if the motion of competitive neurons in the input space remains sufficiently constrained for several subsequent epochs, then we can assume that the learning process is complete. Figure 9.27 shows the dynamics of the learning process for competitive neurons of the iris classification neural network. The network was trained with two different learning rates. As can be seen in figure 9.27b, if the learning rate is too high, the behavior of competitive neurons may become erratic, and the network may never converge. However, in order to accelerate learning, we can still use large initial values of the learning rate, but as training progresses the learning rate must gradually decrease. How can we associate an output neuron with a particular class? How do we know, for example, that the competitive neuron 1 represents class versicolor? Competitive neural networks enable us to identify clusters in input data. However, since clustering is an unsupervised process, we cannot use it directly for labeling output neurons. In fact, clustering is just a preliminary stage of classification. In most practical applications, the distribution of data that belong to the same cluster is rather dense, and there are usually natural valleys between different clusters. As a result, the position of the center of a cluster often reveals distinctive features of the corresponding class. On the other hand, the weight vectors of the competitive neurons after training provide us with the coordinates of these centers in the input space. Thus, a competitive neuron can be associated with a particular class through its weights. Table 9.3 contains the final weights of Figure 9.27 Learning curves for competitive neurons of the iris classification neural network. Will a neural network work for my problem? 335. Table 9.3 Labeling the competitive neurons. Neuron. Weights. Dimensions of the iris plant, cm. Class of the iris plant. 1, 2, 3. W11 0.4355, W21 0.3022, W31 0.5658, W41 0.5300. W12 0.6514, W22 0.4348, W32 0.7620, W42 0.7882. W13 0.2060, W23 0.6056, W33 0.0940, W43 0.0799. Sepal length. Sepal width. Petal length. Petal width. Sepal length. Sepal width. Petal length. Petal width. Sepal length. Sepal width. Petal length. Petal width. 5.9. 2.7. 4.4. 1.4. 6.7, 3.0, 5.5, 2.0, 5.0, 3.5, 1.6, 0.3. Versicolor. Virginica. Setosa. The competitive neurons, decoded values of these weights and the corresponding classes of the iris plant. How do we decode weights into iris dimensions? To decode the weights of the competitive neurons into dimensions of the iris plant, we simply reverse the procedure used for massaging the iris data. For example, sepal length W11 and a quarter 0.4355, 7, 94, 3, 4, 3 and a quarter 5, 9 centimeters. Once the weights are decoded, we can ask an iris plant expert to label the output neurons. Can we label the competitive neurons automatically without having to ask the expert? We can use a test data set for labeling competitive neurons automatically. Once training of a neural network is complete, a set of input samples representing the same class, say class versicolor, is fed to the network, and the output neuron that wins the competition most of the time receives a label of the corresponding class. Although a competitive network has only one layer of competitive neurons, it can classify input patterns that are not linearly separable. In classification tasks, competitive networks learn much faster than multi-layer perceptrons trained with the backpropagation algorithm, but they usually provide less accurate results. 336. Knowledge engineering and data mining. 9.5 Will genetic algorithms work for my problem? Genetic algorithms are applicable to many optimization problems. Haupt and Haupt, 1998. Optimization is essentially the process of finding a better solution to a problem. This implies that the problem has more than one solution and the solutions are not of equal quality. A genetic algorithm generates a population of competing candidate solutions and then causes them to evolve through the process of natural selection. Poor solutions tend to die out, while better solutions survive and reproduce. By repeating this process over and over again, the genetic algorithm breeds an optimal solution. Case Study 7. The Traveling Salesman Problem. I want to develop an intelligent system that can produce an optimal itinerary. I am going to travel by car and I want to visit all major cities in Western and Central Europe and then return home. Will a genetic algorithm work for this problem? This problem is well known as the traveling salesman problem, TSP. Given a finite number of cities, n, and the cost of travel or the distance between each pair of cities, we need to find the cheapest way, or the shortest route, for visiting each city exactly once and returning to the starting point. Although the TSP became known as early as the 18th century, only in the late 1940s and early 1950s was the problem studied seriously and then publicized as a typical NP-hard problem. Danzig et al. 1954, Flood, 1955. Such problems are hard to solve by combinatorial search techniques. The search space for the TSP includes all possible combinations of n cities, and thus the size of the search space equals n. The factorial of the number of cities. Because the number of cities can be quite large, examining the alternative routes one by one is not feasible. The TSP is naturally represented in numerous transportation and logistics applications, such as arranging routes for school buses to pick up children in a school district, delivering meals to homebound people, scheduling stacker cranes in a warehouse, planning truck routes to pick up parcel post, and many others. A classic example of the TSP is the scheduling of a machine to drill holes in a circuit board. In this case, the holes are the cities, and the cost of travel is the time it takes to move the drill head from one hole to the next. Over the years, the size of the TSP has grown dramatically, moving from the solution of a 49-city problem, Danzig et al. 1954, up to the recent solution of a 15,112-city problem, Applegate et al. 2001. Researchers apply different techniques to solve this problem. These techniques include simulated annealing, Larhoven and Arts, 1987, discrete linear programming, Lawler et al. 1985, neural networks, Hopfield and Tank, 1985, branch and bound algorithms, Tees-Choke et al. 1995, Markov chains, Martin et al. 1991, and genetic algorithms, Potvin, 1996. Genetic algorithms are. Will genetic algorithms work for my problem? 337. Particularly suitable for the TSP because they can rapidly direct the search to promising areas of the search space. How does a genetic algorithm solve the TSP? First, we need to decide how to represent a route of the salesman. The most natural way of representing a route is path representation, Mikhailovich, 1996. Each city is given an alphabetic or numerical name, the route through the cities is represented as a chromosome, and appropriate genetic operators are used to create new routes. Suppose we have 9 cities numbered from 1 to 9. In a chromosome, the order of the integers represents the order in which the cities will be visited by the salesman. For example, a chromosome 1, 5, 6, 3, 2, 8, 4, 9, 7 represents the route shown in figure 9.28. The salesman starts at city 1, visits all the other cities once and returns to the starting point. How does the crossover operator work in the TSP? The crossover operator in its classical form cannot be directly applied to the TSP. A simple exchange of parts between two parents would produce illegal routes containing duplicates and omissions. Some cities would be visited twice while others would not be visited at all. For example, exchanging parts of the two parent chromosomes. Parent 1, 1, 5, 6, 3, 2, 8, 4, 9, 7. Parent 2, 3, 6, 1, 9, 8, 7, 2, 5, 4. Would produce one route with city 5 visited twice and city 7 omitted, and the other with city 7 visited twice and city 5 omitted. 1, 3, 9, 8, 4. Child 1, 25. Child 2, 65,376.97. 1, 2, 8, 4. Clearly, the classical crossover with a single crossover point does not work in the TSP. To overcome this problem, a number of two-point crossover operators were proposed. Goldberg, 1989. For example, Goldberg and Lingle 1985 suggested the partially mapped crossover, and Davis 1985 introduced the ordered. Figure 9.28 An example of the salesman's route. 338. Knowledge engineering and data mining. 7. Asterisk. Asterisk. Figure 9.29 Crossover operators for the TSP. Crossover. However, most operators are based on creating an offspring by choosing a part of a root from one parent and preserving the order of cities from the other parent. Figure 9.29 demonstrates how the crossover operator works. First, two crossover points marked by the character are chosen uniformly at random along the strings of two parent chromosomes. Chromosome material between crossover points defines swap sections. Two offspring chromosomes are created by interchanging the swap sections between the parents. In figure 9.29 asterisks represent yet undecided cities. Next, the original cities from each parent are placed in their original order, omitting cities present in the other parent's swap section. For example, cities 1, 9, 4 and 8, which appear in the swap section from the second parent, are removed from the first parent. The remaining cities are then placed in the offspring, preserving their original order. As a result, an offspring represents a root partly determined by each of its parents. How does the mutation operator works in the TSP? There are two types of mutation operators, reciprocal exchange and inversion. Michalowicz, 1996. Figures 9.30 A and B show how they work. The reciprocal exchange operator simply swaps two randomly selected cities in the chromosome. The inversion operator selects two random points along the chromosome string and reverses the order of the cities between these points. How do we define a fitness function in the TSP? While creating genetic operators for the TSP is not trivial, the design of a fitness function is straightforward. All we need to do is to evaluate the total length of the Figure 9.30 mutation operators for the TSP, A. Original chromosomes, B. Mutated chromosomes. Will a hybrid intelligent system work for my problem? 339. Figure 9.31 Performance graph and the best salesman's routes created in a population of 20 chromosomes after 100 generations. Root. The fitness of each individual chromosome is determinated the reciprocal of the root length. In other words, the shorter the root, the fitter the chromosome. Once the fitness function is defined and genetic operators are constructed, we can implement and run the GA. As an example, let us consider the TSP for 20 cities placed in a 1-1 square. First, we choose the size of a chromosome population and the number of generations to run. We might start with a relatively small population and after a few generations examine the solutions obtained. Figure 9.31 shows the best route created by 20 chromosomes after 100 generations. As we can see, this route is not optimal and obviously can be improved. Let us increase the size of the chromosome population and run the GA again. Figure 9.32 demonstrates the results. The total length of the route decreases by 20%, a very significant improvement. But how do we know that the GA has actually found the optimal route? The fact is, we don't. Only further trial runs on different sizes of chromosome populations with different rates of crossover and mutation can provide the answer. Let us, for example, increase the mutation rate up to 0.01. Figure 9.32b shows the results. Although the total distance decreased slightly, the salesman's route is still similar to the one shown in figure 9.32a. Perhaps we might now attempt to increase the size of the chromosome population and rerun the GA. However, it is highly unlikely that we would achieve a noticeably better solution. Can we be sure that this route is the optimal one? Of course, we wouldn't bet on it. However, after several runs, we can be absolutely sure that the route we obtained is a good one. 9.6 Will a hybrid intelligence system work for my problem? Solving complex real-world problems requires an application of complex intelligent systems that combine the advantages of expert systems, fuzzy logic, neural networks and evolutionary computation. Such systems can integrate 340. Knowledge engineering and data mining. Figure 9.32 Performance graphs and the best routes created in a population of 200 chromosomes. A mutation rate is 0.001, B mutation rate is 0.01. Human-like expertise in a specific domain with abilities to learn and adapt to a rapidly changing environment. Although the field of hybrid intelligent systems is still evolving, and most hybrid tools are not yet particularly effective, neuro-fuzzy systems have already matured as an advanced technology with numerous successful applications. While neural networks can learn from data, the key benefit of fuzzy logic lies in its ability to model decision-making of humans. Case Study 8. Neuro-fuzzy decision support systems. I want to develop an intelligent system for diagnosing myocardial perfusion from cardiac images. I have a set of cardiac images as well as the clinical notes and physician's interpretation. Will a hybrid system work for this problem? Diagnosis in modern cardiac medicine is based on the analysis of SPECT single-proton emission computed tomography images. By injecting a patient with. Will a hybrid intelligent system work for my problem? 341. Radioactive tracer. Two sets of SPECT images are obtained. One is taken 10 to 15 minutes after the injection when the stress is greatest, stress images, and the other is taken 2 to 5 hours after the injection, rest images. The distribution of the radioactive tracer in the cardiac muscle is proportional to the muscle's perfusion. Thus, by comparing stress and rest images, a cardiologist can often detect abnormalities in the heart function. The SPECT images are usually represented by high-resolution two-dimensional black and white pictures with up to 256 shades of gray. Brighter patches on the image correspond to well-perfused areas of the myocardium, while darker patches may indicate the presence of an ischemia. Unfortunately, a visual inspection of the SPECT images is highly subjective. Physicians' interpretations are therefore often inconsistent and susceptible to errors. Clearly, an intelligent system that can help a cardiologist to diagnose cardiac SPECT images would be of great value. For this study, we used 267 cardiac diagnostic cases. Each case is accompanied by two SPECT images, the stress image and the rest image, and each image is divided into 22 regions. The region's brightness, which in turn reflects perfusion inside this region, is expressed by an integer number between 0 and 100. Kurgan et al., 2001. Thus, each cardiac diagnostic case is represented by 44 continuous features and one binary feature that assigns an overall diagnosis normal or abnormal. The entire SPECT data set consists of 55 cases classified as normal positive examples, and 212 cases classified as abnormal negative examples. This set is divided into training and test sets. The training set has 40 positive and 40 negative examples. The test set is represented by 15 positive and 172 negative examples. Can we train a backpropagation neural network to classify the SPECT images into normal and abnormal? A backpropagation neural network can indeed address the SPECT image classification problem. The size of the training set appears to be sufficiently large, and the network can work here as a classifier. The number of neurons in the input layer is determined by the total number of regions in the stress and rest images. In this example, each image is divided into 22 regions, so we need 44 input neurons. Since SPECT images are to be classified as either normal or abnormal, we should use 2 output neurons. Experimental trials show that a good generalization can be obtained with as little as 5 to 7 neurons in the hidden layer. The backpropagation network learns relatively fast and converges to a solution. However, when we test the network on the test set, we find that the network's performance is rather poor. About 25% of normal cardiac diagnostic cases are misclassified as abnormal and over 35% of abnormal cases are misclassified as normal. The overall diagnostic error exceeds 33%. This indicates that the training set may lack some important examples. A neural network is only as good as the examples used to train it. Despite this, we still can significantly improve the accuracy of the diagnosis. 342. Knowledge engineering and data mining. First, we need to redefine the problem. To train the network, we use the same number of positive and negative examples. Although in real clinical trials the ratio between normal and abnormal SPECT images is very different, the misclassification of an abnormal cardiac case could lead to infinitely more serious consequences than the misclassification of a normal case. Therefore, in order to achieve a small classification error for abnormal SPECT images, we might agree to have a relatively large error for normal images. The neural network produces two outputs. The first output corresponds to the possibility that the SPECT image belongs to the class normal, and the second to the possibility that the image belongs to the class abnormal. If, for example, the first normal output is 0.92 and the second abnormal is 0.16, the SPECT image is classified as normal, and we can conclude that the risk of a heart attack for this case is low. On the other hand, if the normal output is low, say 0.17, and the abnormal output is much higher, say 0.51, the SPECT image is classified as abnormal, and we can infer that the risk of a heart attack in this case is rather high. However, if the two outputs are close, say the normal output is 0.51 and the abnormal 0.49, we cannot confidently classify the image. Can we use fuzzy logic for decision-making in medical diagnosis? Doctors do not keep precise thresholds in mind when they classify SPECT images. A cardiologist examines perfusion across all regions in the diagnosed image and also compares the brightness of the corresponding myocardium regions on the stress and rest images. In fact, doctors often rely on their experience and intuition in detecting abnormalities of the myocardium. Fuzzy logic provides us with a means of modeling how the cardiologist assesses the risk of a heart attack. To build a fuzzy system, we first need to determine input and output variables, define fuzzy sets and construct fuzzy rules. For our problem, there are two inputs N output 1 and NN output 2, ADONE output the risk of a heart attack. The inputs are normalized to be within the range of 0, 1 and the output can vary between 0 and 100%.